right, welcome to the third day of this very gathering in Bangkok. I'm excited to announce that the first session today is called Utilizing National IDs in the Ethereum Ecosystem. And we'll be gathering a bunch of speakers from across the world, from Florent, Hiroyuki, Michael, Nico, and Yanis. So, shall we get started? I'm going to do a group call and then we can all gather on stage. The session will cover a bunch of topics from Myna Wallet, Anonadar, Proof of Wallet, Proof Passport, and ZK Passport, where we were exploring the developing implications of government-issued IDs in the Ethereum ecosystem. So, without further ado, please give our guests a round of applause and welcome them to the stage. Are we all feeling good? Thank you very much.
All right, so we're the people mostly working with the Ethereum times like national IDs. So and then we're going to talk about like where our sorts, so like our experience, like our in past few years. So like, can you explain yourself first from the Yanis?
Yes, hello everybody. Super happy to be here today. I'm Yanis. I'm a developer and working at PSE and developing Anonadar. Which is, Adar is like one of the biggest identity program in the world. It's a residency card that is signed, and we are letting people generate a ZK proof that they are the owner of a legitimate signed paper.
Awesome, thank you. And Mike, please.
Yeah, hi, really great to be here. I'm excited about this panel. It's going to be really good. I'm Michael Elliott. I'm co-founder of ZK Passport, and we allow you to use your government-issued passport, scan it into your phone via NFC, and then because it's been attested to by your issuing government, you can generate zero-knowledge proofs to selectively reveal information about yourself to services.
Awesome. And Florent, please.
So nice to be here today. My name is Florent. I'm working on open passports, and kind of similar to what Michael just explained, we're working on making it super easy for people to scan the NFC chip in their passport, the real government-issued passports, and then to do zero-knowledge proofs of specific stuff. So for instance, they can prove that they are above 18 or 21, or that they are from a specific country, or just that they have a valid passport.
Awesome. And Hiro, please.
Hi, I'm happy to hear. I'm Hilo from Myna Wallet, and Myna Wallet is the smart account that operated by the government-issued ID in Japan, Myna Card. So, Myna Card, with Myna Card, we can sign on any data with tapping the card and enter the PIN code. So, actually, our smart account verified with Myna Card. So, yeah.
Awesome. And lastly, my name is Nico. So I used to work in the Myna Wallet, and right now I'm working with Open Passport, and I'm going to be the moderator for the sessions. Okay, nice to meet you. And firstly, I want to ask about like there is two different projects working on the passport. So like, what's the difference on your what's the difference of your two projects?
Good question. I think we kind of started independently, maybe Michael and Theo more in the Aztec ecosystem, and we were more like supported by like PSC and WorldCoin. We've been collaborating on everything we can, like sharing code basically, and making sure that we can like be in this very positive sum ecosystem. We're even like discussing like sharing the like registry for all of the certificates that the countries publish to make sure that we can have like the same base of truth for all passports. Yeah, we're fully open source. My guess is that you guys, from what I understand, have like open source some stuff, and maybe you're more focused on like Aztec and making a wallet on Aztec now, if that's accurate.
Yeah, there's a good summary for sure. So we actually started using Circom circuits 6 or so months ago, and now we've moved over to Noir circuits, and I believe Open Passport's also switching to Noir as well now. There's a big overlap with the two projects, and yeah, I think there's definitely an opportunity to duplicate work and kind of work together to share circuits. With ZK Passport, we've got a strong focus on UX, and that's kind of like one of our main driving forces. With regards to Aztec, it is sort of agnostic. Aztec have obviously developed Noir, but that's sort of decoupled from the Aztec network. And then we'll be using ZK Passport with Obsidian Wallet, and that's more so focused on integrating with the Aztec as a wallet. But yeah, I think there's definitely opportunity to collaborate, possibly even maybe we could merge at some point down the road.
Yeah.
Joint efforts, yeah.
Awesome, awesome, thank you. And I guess like ZK Passport and an add-on is like used to like issue, when you issue the Devcon ticket, you can get like a discount when you like have like nationalities of like Southeast Asia.
Yeah, that was a wonderful integration. I really enjoyed building that out.
Yeah.
We utilized some of Open Passport circuits with that, which is huge help. And essentially, if you were from Southeast Asia, you could get a discount on your Devcon ticket. And so the approach that was kind of going to be used was the status quo is you send a photograph of your passport in, which is a horrible UX. And so with this, we built out an integration. You could just scan a QR code, go through the flow. You would prove just your country. And if from Southeast Asia, then you'd be able to apply a discount voucher to your checkout and get a discount on your Devcon ticket.
Awesome, awesome. Thank you so much. So firstly, I'll ask you to Yanis, like how do you think about like why we need national IDs in the Ethereum ecosystem?
Yes, like if we go a level higher, I would say that we need a way to like privately signal ourselves like as human. Because like some very important primitive need anti-Sybil mechanisms. I would say that what we are doing with this project is one way to solve this problem.
Yeah.
I think that it should be pushed super hard because like there is a ton of signed data that is like again out there and that we can like snarkify and make it compatible with publishing it like on a public network such as Ethereum. So. Yeah, I think it's really important because for now it's like one of the most practical way. Maybe not the way that you can like have something that is global, shared by everybody in the world. Because like you have this requirement of having signatures.
Yeah.
But I think that with this logic we can tackle like maybe I don't know like a good chunk of humanity. So
I think as time passes, more and more governments are going to start attesting digitally over this kind of information and credentials. Like you mentioned the other day, things like university degrees, that's going to be a great one. If you have a bachelor's or a master's, that can be attested to and then verified in zero knowledge.
Yeah, but then the question is that can you trust them?
Hopefully the government can trust the universities and then you can trust the universities and there's like a chain of trust.
Yeah, but I would say that, yeah, in some places maybe you're not like because all our projects makes the trust assumption that a government will not use his private key to sign fake identities.
Yeah.
So it's a very strong assumption. It works like in most of the region of our world, but in some region it could not be the case. So you need alternative, like when you can't trust the government.
For sure, I think the advantage of e-passports, at least in this situation, is because it's being used by governments to protect their borders. You get that same level of guarantee. So if one government kind of just goes rogue or starts minting e-passports, it's going to be obvious to every other government, and they'll kind of be like, "What the hell? Like, what are you doing?" Which is kind of like a protection mechanism in that regard. But degrees may be less serious, so they could do that.
Awesome. Like you mentioned about like we can utilize like not only the national IDs, but like we have like a driver's license, like a national degrees, the college degrees. But like, do you have any idea like how we can integrate those IDs into one IDs, or like we can just use like those IDs in a separately, like like it depends on the situations, or like do you have any thoughts like we can just integrate or something? Yeah, Florent, you can.
Yeah, so I think the point that Yanis touched is like important, that we're all making these trust assumptions on the country.
Yeah.
I think that the problems that we're trying to tackle, like Sybil resistance, are actually quite hard to tackle. Like there's no really simple, straightforward way to make sure that someone is a real person online. It's kind of like the meme of on the internet, you can be a dog and nobody knows you're a dog. There are some teams that are trying to use biometrics, but it's still very hard because they have to ship their device everywhere because the current phones that people have are not accurate enough for biometrics. I'm not even really sure how much different attack vectors there's on all of this. So I think what's interesting about the work we're all doing is that we just take those existing signatures, we wrap them in ZK, and we make sure that they're easily verifiable on-chain and off-chain. And then we make this kind of bet of there's going to be a lot more signatures in the future. Governments are going to sign things. Companies are going to sign things. Universities are going to sign things. And maybe at one point we have enough attestations that we can start to have a really reliable identity layer or general like aggregated system in which if one actor starts like behaving in the wrong way, like a government like printing fake passports or like a university doing something, then it's not that bad for the overall system. A bit like Gitcoin passports, you might know how it works. It's like this system for stability resistance, for quadratic funding, for airdrops. You can add different like Web2 accounts and it gives you stamps. And that's kind of the way I think about it. It's like in the future, if the tech is mature enough and it becomes super easy, maybe thanks to ZK VMs, and we can like run them on phones and everything, that would be great. And it's like mature enough so that we can take all the signatures that are going to be emitted and use them. Maybe at this point we kind of can break the trade-off and have everything at the same time. Have CB resistance, privacy preserving proofs for everything, and still have the reliability that you would have, that you would need.
Sounds an awful lot like you were sort of, what you were saying there was a layer 2 for identity to some extent.
I'm not saying that needs to be a layer 2 or like, but like probably some kind of system that has a common standard. And we've had discussions about standards. I think it's kind of hard right now to know exactly what are going to be the standards because we're all like trying to figure out what's the best way to use those things. And I think the standards that's going to emerge is probably not something that will have been like discussed that much, but just the one used by the end user product that's going to work the best.
I think just to get in here quickly about the collaboration part, there's such an opportunity for a shared registry, whether it's like the certificate root registry, where all the country certificates are kind of combined and shared across like Raremo, Open Passport, ZK Passport, and other projects. It's going to be very helpful.
Awesome. Okay, so like Florent, you firstly mentioned about like compared to the world, like using the passport and national IDs, it could like less effort to realize a civil resistance. Like for example, in a passport, like how reliable, like when you prove the proof passport, like this is a civil resistance or
This is a very good question. So passports were originally not really made for that. We're kind of just taking them and reusing them for other things. So there's actually 2 levels of security in passports. Pretty much all of them support the basic level, which is there's an attestation in the passports, and you can read it and then you can verify it. The kind of problem with that is that anybody that reads your passport once can just take this attestation, store it, and then make proofs afterwards and like basically impersonate you, so that's not great. But a lot of newer passports now have this better security mechanism, which is active authentication, in which the chip inside the passport actually has a private key and makes signatures, so you can like send a challenge, make sure that the challenge is like comes from like a valid source, like for instance, it could be like RenDAO, Onchain, or something like that. And then you can make sure that the person really has the passport in hand at this point. You can even like challenge the person every 6 months or something, or every transaction. So that's something that we're excited about. It's kind of, it takes a lot of time for countries to ship that because, you know, like renewing your passport is not something you do every day. But maybe I'll add something. So even with this better security mechanism, you still can't make sure that the actual person behind the passport is the person who owns the passports. And one thing we're really excited about is trying to use biometrics, not exactly in the same way that World is doing it, but more like maybe having a kind of face ID that matches with the photo of the passport, because the photo of the passport is actually in the chip, and it's actually signed, which is really great. So if we can, like it's probably too early to use ZK with that, because ZK ML doesn't really work right now in terms of performance for client side. But if we can like have some kind of cosine similarity or like matching system with like convolution or something in the TEE, that could make, like that could be something that makes this all more reliable, and we're excited by that.
Yeah, so it'd be really great to be able to like check like a face fingerprint from your passport photo, and then you could scan your face with your iPhone, and then you could compare those two face fingerprints in zero knowledge to prove that you are the person on the passport at the time that you use the passport. Really exciting.
Yeah, okay. Yeah, okay, so like you mentioned about like active authentications. So like in the other ID system, like in the adult system, do you have any like those kind of active authentication features included in the adult system, or like?
No, well, no, like, yeah, so sometimes, I think it's the case for Myna, like the government is not signing like just the concatenation of like your identity attributes, but sometimes they're like giving you a key pair that they are attesting that it's yours.
Yeah.
And you can use this key pair to like authenticate and identify yourself. Like in the India stack, there is no such mechanisms. Yeah, but to go back to the theme question about like how can we rebuild like an identity? I think like with Anonadar we tried to. There is this app called DigiLocker where you can store all your documents, official documents like driving license, degrees. So we make the exercise to like try to figure out what could be like there is this idea about self-sovereign identity. So what could be like the snark's sovereign identity? How could we like use all these pieces of data and like use it? So it's very new. We developed like this circuit like in the past few months. Very exciting, excited about it. Like to see like what type of usage it's gonna be like unlocking. So yeah,
I heard like you are using like a QR code issued by the government, and you check the timestamp or something, and it can be like an active authentication or something, like.
Yeah, so it's not active authentication, because active authentication is like the fact that, as Florent described, like you can send a challenge to the user and he gives you back a signature. No, but so this mechanism can like you can make sure that the person behind the screen has like actually the document. And you can send like regular challenges to make sure he still owns the document. No, in the case of Adar, like the cool point is that inside of the signature you have like a timestamp of when the data was signed, and we are using it like as a time-based one-time password. So meaning that at the verifier level you can set it up and you can create your own logic, and you can say, oh, I want to verify your signature, like a snark proof of your signature, but I want like this data signed like less than 3 hours ago. So, like it's a proxy to know if the user has access to like the platform where he can generate his
so like it's not exactly the active authentication, but you can still check the like a timestamp when the signature is issued or something.
Yes, it's more like you want to make sure that the person behind the screen has the document and has access to like the official platform and has the credential and because like in India it's like mainly like OTP, so like a connection through SMS. So you can make sure that he is the owner also of the phone.
My understanding of this is to be able to get back your Aadhaar, if you've, so for example, lost it or you need it at that time, you can request one and the government will be able to SMS you a link to be able to get it again.
No, it's not only used for recovery, it's used like for authentication.
Right, and you leverage that to be able to prove that you are the person at the time.
Yes, so for example, like for the app we developed for the Devcon discounted tickets, we wanted to make sure that the proof was like generated less than 24 hours ago. Because otherwise, like a QR code, like I can drop my card like on the floor and I can like...
it's like a liveness check through one-time password.
Yeah.
Okay, awesome. And in the Myna case, you actually have like active authentications.
Right.
And like you use like also like so like for active authentication, they can actually do like make a signatures, and then you can like hack the features and they can make an account of Offchain wallet, right?
Yes.
So like, what's your experience about it?
First, I need to explain what is Myna card in detail. So Myna card is the NFC card, NFC type B card, and there is a secure element inside. So there is two RSA key pairs, and to sign with this card, we can tap the card and enter the PIN code like a credit card. So just this is so we can generate the signatures, and then we directly verify the signature on chain, like ERC supports RISC-V smart contract. That's why we can generate a smart account by this card. And also, as we talked, the government provide us kind of a liveness check API so that we can directly create create this transaction. Also, we have directly verify that the user is actually existing residents in Japan.
Okay, okay. And like you have like a AA wallet from that card, right?
Yeah, yeah.
Like how do you have any thought about like a privacy, or like how do you have any idea about like how those keys are used in a AA wallet?
Okay. So we leveraged the current PKI system for the identity verification of the Myna card. So to verify the signature from Myna card on chain, we need to store the part of the public key on the certificate in the Myna card on the smart contract. So actually, so this is a PKI system. We leverage the PKI system. The mapping of the electric certificates that includes the public key and identities. Government can relay that information. So yeah, actually the government can track the ETH users' activities on chain. So that's kind of a privacy concern. But Nico, you did the
I know. Yeah, so like basically the Myna wallet is like AA wallet, and like they generate their wallet address from the public key inside the Myna card. So like the government, as the hero told us, like there is a mapping, the public to the your identity. So like the government can track like kind of brute forcely, and they like brute force, like kind of brute force, and like they can detect, or like I'm using this wallet address or this wallet address. Like for our general public, they don't really have like the list of like a public key to like my identities. So like we can protect the privacy for the general public, but still the government can track our identities. And there is some kind of technique to hide our identity even from the government, but it only works for the RSA key, especially for the RSA some kind of padding scheme. But like in near future, like a Myna wallet will turn right now they're using the RSA, but they turned into like a ECDSA. And like in the ECDSA, we need to input like a random value to make a signatures. So like we cannot use like those kind of technique. So like we need to like in the current version we can think we can have like a solution to hide from the government. Like in the ECDSA, we need to figure out how we can achieve a privacy from the government. But I think you have a kind of thought should we actually need to hide our privacy from the government, or
Depends on the government, I suppose.
I'm sorry?
Depends on the government.
Yeah. Or maybe there is some people want it's okay to reveal privacy to the government, because there is another privacy wallet named the EOA. So it's fine as long as you're using the EOA. You want to be a private, and you want to do something with the government, or you want to pay tax or something. It's okay. You find I can reveal this government. So I think this is because right now the Myna wallet is generate their address from the public key, I guess. Yeah, right?
Yeah, it depends on the use cases.
Yeah.
Because if you want a private address, you can use your any EOA, right? But yeah, our solution, our product is for people, not for people like us, people here, because they can choose which address to, or which on purpose, which you can check, so.
So you're more focused on a more mass adoption, not really.
Right.
So firstly you just think about the mass adoption, and think later about privacy or those things.
Right.
Okay, awesome.
Just kind of zooming out from what we're talking about here, I think one nice way to think about it is everybody has their own FIDO, or even hardware wallet that's issued by the government, allowing them to sign over data themselves. But you've still got that chain of trust back to the government that's been, that's issued it to a particular person somewhere. Some are kind of weaker signatures, so the e-passports, the active authentication that Florent was talking about earlier, that's RSA 1024 bit, so you can only really use that for kind of very short time periods with a challenge request that maybe a few minutes. That was the intended purpose at airports, and we're leveraging that existing infrastructure. But you can still do that, but any longer and you risk people being able to break that through brute force attack on RSA. But the great thing about the Myna card here is that because it's like kind of like a national ID card issued just in Japan, they've used the same standard, which must be amazing, not having to integrate so many different signing algorithms, and you get this really cool functionality coming out of it that's the same across all of the cards.
Yeah. Okay. Yeah. Okay. So like, and do you have any thoughts about like, so right now you are verified RSA signature on-chain directory, right? But like, in near future, like Myna card turn to be like a ECDSA, like a 384 bits, and it's gonna be very expensive to verify an on-chain. Like, do you have any thoughts on like this one?
So one idea is to raise the kind of EIP something like that to at the
make a pre-compile. So like you are kind of stick to like a verify the low ECDSA signature on-chain, or like do you have any idea on like using the ZK or something?
Yeah, that's one.
One option. Okay. So I guess like also like creating a ZK proof for those kind of long, like a very like a heavy signature on the ZK proof, but like also like in the passport there's so many like a signature algorithm I use, and like there's so much variety, it's crazy, right? So like do you have any idea like currently like RSA is fine, but like the others, like do you have any idea?
Yeah, so client-side proving for ZK has always been kind of challenging. One of the main reasons is that teams that are working hard on ZK are often just optimizing for big beefy servers, because this is what the rollups are doing, and so this is what the incentives are. Because it's rollups, you got business tokens, things. But like we're doing kind of client-side proving on people's phone, because there's no way we're like sending people's like passport data or like personal data anywhere else.
This is a must-have. It must be all generated locally on the device.
Exactly. Yeah. So historically, CRCOM has kind of been the way to go. We've switched between different proving stacks, like the Polygon ID one, MoPro, that's been great too. I think Noir is becoming kind of more of, maybe it's going to become the new standard. And I think what's really exciting with Noir and really great for passports, for instance, is that all those different countries have different signature algorithms, and so it's super hard to support everything in CRCOM because you have to write a specific program, a specific circuit for each of them. But with Noir, you can have easy recursion. That's not too like that doesn't have too much overhead, or you can just delegate this overhead to a server that does not see the private values because you do smaller proofs locally. And so it's way easier to have a system in which you're going to split the proof into smaller like pieces that you can do locally that only have like small like requirements for RAM usage and for like bandwidth, and then recursively verify them like server side on a big beefy server, and then post them on chain or do whatever you want with them. So that's something we're super excited about.
Yeah, on mobile, you're really limited by memory, so you don't want to go beyond 4 gigabytes. And so the larger your circuit, the larger the memory requirements. And so the design that we've created in Noir is we have these sub-circuits, A, B, C, and D, and each sub-circuit is responsible for a different part of the verification process. So sub-circuit A, for example, verifies the authenticity of the, so it basically verifies the root certificate of the country has signed over the intermediate certificate. And then submodule sub-circuit B verifies that the intermediate certificate has signed over the e-passport data. Sub-circuit C verifies the integrity of the passport, and finally D discloses the data that you wanted to selectively reveal. And so this modular approach means that we can, if there's different signature algorithms for, say, the intermediate certificate, we can kind of, when we generate the proof client side, you can pivot through the different sub-circuits easily and kind of like route through to whatever the passport requirements are for the signature algorithm. Some countries even have a variety of different algorithms, and the biggest challenge we have right now is adding support for more and more signature algorithms to maximize compatibility. Yeah. So
what's the point? Like, what's the mostly the difficulties? Like you mentioned about the memory usage, or like the other things. Like, what's the like a bottleneck in a client-side proving, or especially the iPhone, like whatever. Like.
I think currently the two main bottlenecks are RAM usage and then load speed and everything. Because with like CRCOM and Grow 16, what we are using before, you need to download this huge file to be able to do zero knowledge proof. It becomes very tricky when you have like big circuits. But with Noir, it's kind of more manageable. And I think in the future, the end game of all of this is probably ZK VMs, and you might already know about ZK VMs. It's like very easy to use. You can just write your code in like some normal Rust.
Like Aztec?
Right,
like
Aztec. Yeah.
Yeah, I mean, yeah, like I'm thinking more about like ZK VMs like in Rust or something. But yeah, Noir is kind of similar to Rust, and Noir is like already easier to write than other like DSLs. But yeah, maybe in the future you could just like natively import your Rust library that does RSA, like literally the same one that's used everywhere, and then directly like verify, like do proofs on phones. But right now we kind of looked at the performance and it's not quite there.
Like I heard like your kind of experience with the SP1, which is ZKVM. Do you really think like ZKVM also be used for the client-side proving, or like?
One day.
One day.
One day. Yeah. Right
One
now
day.
it's a bit. Yeah. Right now it's challenging.
Yeah. They have?
SB1's great. It's a nice UX to be able to just develop natively in Rust and not even change the interface for your crates, because there's like pre-compiles in the SP1 crates. But because they're Starks, the memory requirements are way too large for client-side proving and mobile currently. So maybe S2 could reduce those requirements, but currently I think Snarks and Noir is the best approach.
Okay, awesome. And Yanis, are you also working with the Noir, or like you're turned into like Noir, or like you're just like what's your plan for like so like those like RAM problem or like ZK problem?
Yes, so we have the same bottlenecks, which is like client-side proving. So we are exploring like what could be the next step for client-side proving, because I think that this type of protocol, especially like in the case of India, like you want to like distribute them like broadly, and we want like have like the lighter prover possible, but also like a proof that is succinct, so we can use it on chain, because we think that the main use cases would be probably on chain, because it's there that where you need like the more privacy. We tend to see like from government side that you can have like they are like more listening to like privacy issues and selective disclosure. So we really want like to have like a light prover, but also have succinctness, so we can like prove on chain. And yeah, I think like main of the exploration, as Flora and Mike was speaking about, is that maybe one solution could be like to have like a proof that is very fast to compute on the client, but not succinct, and then send it to a server that can make things succinct without learning like what were the input of the computation. That's one way. And us, like on our side, what we are doing is that we are exploring. So there is no end game for now. There is no perfect solution. So we are trying to have our implementation in like a different language. Like for example, we did implement our circuit in Hello 2 because we know that some people are exploring like a Hello 2 GPU acceleration. So that could be like an interesting path.
Have you explored Noir?
Yes, Noir, and I think Noir is more like in the, Noir is committed to ship backend, so like it's more secure that to bet on Noir, because like you know that maybe if there is a new interesting backends, the team is dedicated and they will ship it. So yes, for now we will stick to Grow 16 because for us it's the best, but of course like we want to see like more exploration in the client side proving. I think there is a lot of money spent on server-side proving and trying to optimize ZK for server-side. But I think that for privacy, we really need like to have efficient client-side proving. Yeah.
Awesome. And you're talking about like mostly the use cases is like on-chain. Like it's also like our like kind of ID system can be used like off-chain, like eKYC things. Like, do you have any thoughts on like off-chain use case?
I think you need both. Like. As an application developer, you should be able like to tackle any environment where you want to check this proof. So
I think especially if you're revealing, like for example, your full name, date of birth, that's not something that you want to publish on chain for eternity. This is perfect for a back-end proof for some sort of service to verify.
Yes. UX-wise, it's hard, but yes. I mean, UX-wise, like. Maybe the end user like doesn't know like where he's sending.
That'd be horrible. Could you imagine? Just publishes it forever.
So yeah, that's why like no, it's an interesting question about selective disclosure, because on the case of Anonadar, we could have like implemented it like in such a way that the developer can set the prover to say, oh, I want you to reveal your first name. But as like we are very early, we were super precautious about selective disclosure, and only like our provider is only able like to disclose information that if you disclose all of them, you can be in an anonymity set that is like large enough to not be de-anonymized.
So you need to be selective about selective disclosure.
Sorry?
You need to be selective about selective disclosure.
Yes,
So to say.
that's kind of a security because like, you know, like it's quite early and we don't want like the chain is immutable. So we don't want like a developer messing up.
There's no
and like,
control Z on blockchain.
Yeah, yeah. So no, we need to be very precautious about that. Yeah.
Okay, okay. So like as I mentioned about the off-chain, like our ID system can be used in the real world, and recently like a Myna Wallet did some kind of real world experiment. So like, can you explain about like your experience with it?
Yeah, just recently we conducted a real-world demonstration Myna Wallet in a rural area in Japan, which is called Yamakoshi, Niigata, Japan. And Yamakoshi is very unique, where the DAO is actually working on regional revitalization. And in the demonstration, participants range from children to the people at the age of 18, and there we demonstrated a tap to pay by USDC, and actually there are people could make it to pay by Myna card using the USDC because they don't even know what's going on the background. They are using what the blockchain is working, or they are paying by USDC. But they have the mental model like tap to pay because its mental model is totally same as the credit card.
Yeah.
So yeah, in this demonstration we realized that real world use case is it's very important. UX is very important, and actually this is interesting because. Japan's Minister for Digital Transformation, Mr. Tyler, is actually very interested in our demonstration, and he actually came to our demonstration and created his smart account.
Okay, awesome, awesome. So like the Japanese our digital minister are interested in like our cryptocurrency or like Ethereum.
They are very
technology
open
or
to the
adopting.
new technology.
Awesome. So, so you have some communication with the government. So, like, do you have any pressures or government? Like, I heard like a very positive side. Like, do you have like any like a negative side from the government?
Yeah, negative side. I think they are very open to new technology. So we had a lot of conversation, and of course there's several regulations to utilize this card.
Yeah.
But they are so yeah. But yeah, we can talk and we can
Yeah. So like you have like more like a good discussion with the government.
Right.
Awesome. Okay. So like, if the government is like more friendly to us, like more friendly to like our like a ZK friendly or like Ethereum friendly, what do you want to expect, Florent?
So one thing I'm very excited about, but it's also very long term, I guess, is compliance in general. So right now, if you look at the compliance frameworks of most countries, you can't have any privacy, right? If you do KYC to create a bank account, to create an account on an exchange, you have to send basically all of your data, and it's going to be kept, it's going to be stored for monitoring so that the government can ask for any of your data afterwards. And when you think about it, it's actually really bad. Like there's
horrible
often,
UX.
It's kind of horrible. There's like often leaks that leak like all of the private data of everyone. It's like really sensitive data. You can do crazy things with it, like get SIM cards, bank accounts. And also it's not really secure anymore because now with generative models, you can just like generate whole databases of like fake people and just do KYC. So right now, it's not really like compliant according to the current like standards to do privacy preserving proofs, but there's some interesting explorations to do, I think. So for instance, one thing we recently prototyped is you can do a zero knowledge proof that you're not on the OFAC list. So you might know about the OFAC list. It's like the US list for sanctioned entities. They have names of a lot of people and everything. And you can like scan your passport and do a proof that specifically you're not in this list thanks to like non-exclusion proof in the sparse Merkle tree, and then send it when you do a transaction, for instance. And this could be integrated into like a DeFi protocol or even the base layer of an L1 or an L2. And what this would allow is to have this kind of system in which you know that the person, at least at the time, is not on the OFAC list. And I think this is all pretty much kind of like explorations now, but it looks to me like compliance sometimes can be a bit more flexible, and there should be a kind of like middle ground we can find in which for some transactions it's actually fine just to do this, and that would be great because, again, it's like breaking the trade-off. We get the privacy and we get the freedom at the same time.
Yeah, I think it's a journey. I think we're going to be able to like explore this and just sort of see how governments respond and how regulators respond to this. I think a really amazing use case for what Florent just described is you could have like a private USDC where you have full privacy, you can transfer it around, but every time you transfer this USDC on a private network, like Aztec network, for example, you're generating a proof that you're not on the OFAC SDN sanctions list, you're not from a sanctioned country, and you could even implement logic where there's this nullifier that's unique for every passport, and then it allows you to track privately that you haven't exceeded some super generous limit, like for example, 100,000 USDC per month. And that means that it's going to severely mitigate any kind of like bad actors from using this protocol and this token. And so when you come out to an exchange to off-ramp, users can sort of have this certain or guarantee or at least some sort of comfort that they're not going to be banned by that exchange, whether it's Coinbase or Binance or whatever.
Yeah.
And I think it's really going to help satisfy regulators that, yeah, this is really mitigating bad actors from using it, allowing people to have privacy, full privacy, and eat their cake and have it too.
Yeah.
Yes, yeah, I'm super excited like to again like push this idea forward, like distribute it like to a broader population, because then like maybe we can have like at some point like some voting at the scale of a government like using this primitive.
Yeah.
I'm also super like interested about like how you could like resolve a full identity, like all your documents, like boring use cases.
Yeah.
I had like to fill a visa file like recently, and everything was in my email. So maybe it could have been like a ZK email proofs.
ZK email proof.
Like yeah, like more like generally going toward like something like where you can compute something on your hand, and like just send like a succinct proof. Also, yeah, on the government side and like this technology, I think there is like 2 ways to see that. Like one optimistic way would be like, all right, so if the government can de-anonymize me, is it a feature or is it a bug? I think there is no like strong answer to this question for now.
Depends on the government, I suppose, again.
Depends on the government, but like you can imagine like then in, I don't know, 10 years, maybe we were going to have like airdrop from the government and like maybe like...
Yeah,
What
that's
happens
great,
sooner than
that's
you
great.
think?
Like,
yeah, like maybe just being able to identify and receive like CBDCs and like have like a universal base income is like, I think what we are building is like, could be like a base ground like to build that, so yeah.
Yeah. So do you think like a universal basic income happens? Like it could be like a paid in a blockchain, like it could be paid in a bank account.
It should be paid with CBDCs, yeah, and you just can, I don't know, sign a message or like just send a ZK proof and then you can redeem your money, yeah.
Okay. So like you live in Europe, right? And you have some kind of identity system in Europe, right? Like how the situation in Europe, like eKYC, like how those IDs are used in Europe or something?
Yes, so I think like last April, like the European Commission like voted on like the fact that zero knowledge will be like a solution in the future, like for privacy preserving identities.
Yeah.
So they did like a tender proposal where they like called every project that were interesting like to help them like build their identity wallet that they want to launch like around 2030, sorry. Yeah, so like Europe seems to be like listening to like all these privacy issues. I mean, it's Europe that basically did the GDPR, so yeah, we are like maybe slow on innovation, but good at regulating.
But I guess like Europe is like more interested in like a privacy things. Like they're more care about like privacy or like compliant.
Yes. And also like there is I'm sorry, I don't remember the project, but Europe also have like a project about their own blockchain. I don't know about it. I don't know if it's good. I don't know if it's bad. But yes, they are interested like into this technology for the good or for the bad. We don't know, but at least like if tomorrow we can sit on the table, they will know what we are talking about.
Okay. So and like do you have any idea that we can actually enable those IDs right now? Like, do you have any ideas for what kind of ID we can enable right now? Or do you have idea?
I think the most present use cases are stable resistance in general, whether it be for quadratic funding, for airdrops. Yeah.
Okay.
I think for us, we're excited about being able to have ZK Passport as this open source, public goods identity infrastructure. We're building out Obsidian Wallet to kind of dog food that, and we'll be integrating ZK Passport in as identity at the wallet level. So you'll be able to have it as a first-class citizen that exposes an API to dApps to be able to request identity proofs and compliance proofs. So you could have, for example, USDC token requests that you have these different compliance checks, and then the wallet, Obsidian Wallet, it then manages that completely and generates these proofs behind the scenes. So I'm excited about that kind of integration and being able to use it more and more with Web3 and dApps.
Awesome, awesome. Yeah, okay, so there is so many things we can consider about our wallet, our identities, and there's a bunch of use cases for those national IDs or for example civil resistance or listed on the alpha crest or whatever on the eKYC. So and there is a bunch of more national identities, the identities which is signed from some kind of organizations, especially of course in in the CEA area definitely, also in Europe definitely there is e-identities. So it would be great everyone working more more identities is coming to the Ethereum. Okay, thanks so much for our panel. That's all. Yeah.
Insightful conversation that we had. Thank you very much. I'll be throwing a few questions to Nico, and then you can distribute accordingly to our speakers.
Okay.
I'll be reading the most voted comments. You can also scan on the right to throw in your comments right now, and so I'll be reading it word for word based on votes. The first question that we have today, which is the most voted, is what are the business model for each of your projects? Government identity is typically a government service that people expect in exchange for paying taxes. Who would you like to take the first call?
I guess you can try again.
Yeah, I think we don't really have the same value proposition as government identity. Right now, we're mostly repurposing government identity for other stuff. Yeah, I'm not too worried about business model. I feel like if you do something that's very valuable and that's that has some kind of platform or network effects, you shouldn't be too worried. That's my take.
Yeah, maybe not.
Okay.
I was going to say, sort of answers the question, but one thing I think would be great to discuss is, if you think about thinking about identity in general, who would be the best entity responsible for attesting to your identity and your credentials and who you are as a person, your name, birth date, this kind of stuff? Is the same entity that issues you a birth certificate. And so if you change your name, for example, who do you go to? It's the government, as opposed to so it's like state-attested identity versus corporation-attested identity. Yeah.
Yes, and in the case of Anonadar, it's a PSE project founded by Ethereum Foundation, so we don't have any business model. It's a public good and open source. So.
Right. How about Myna Wallet? I guess it's
Myna Wallet is a wallet, so it can be kind of fee model, right?
Fee model. Okay. Fee model. Okay.
All right, heading to the next question, the most voted one as well. One of the challenges of presenting government IDs remotely is inherence, i.e. how to prove that the presenter is the same person the ID was issued to. How should we best do this?
One of the challenges of the presenting the ID name we want.
Yes, so in the case of Anonadar, it's the same mechanism we spoke about. We are using the timestamp to actually ask for the user to generate fresh data on the official platform. So it's a proxy that he has also the credential and the SIM card that is enabling him to authenticate. So that's how we are solving this problem.
I think the face fingerprint is also a really great way to do this if you have a photograph that's signed over by the government.
Yeah, so using the photograph for a timestamp, or if they have a signatures, can make active authentications. Also, maybe a name and address, correspondence, and you find a relationship. It's one identity have active authentication, and the other identity doesn't have. But we can have correlations between them from a name or address or something. Yeah, I think this is a
PIN code, I suppose, for Myna card.
Yeah, PIN code. Yeah.
All right, heading to the third question. Why should people use Open Passport if it relies on government data? People will stick to the current method, and it's more convenient for now. Is there a way that doesn't depend on government data?
Well, people will stick to the current method. What's exactly the current method? Like, for instance, if you want to do an airdrop or like CBIL resistance for quadratic funding, this is an actual issue that people have actually had, and I think most people know that even today, like on Gitcoin grants, you kind of see that some projects have come some have some like kind of weird behavior with regards to the like donations. So yeah, I think basically what we're trying to do is we take what's working right now, which is government ID, and we repurpose it so that now we can use it in a privacy-preserving way on chain. For the kind of things that we're trying to address, I don't even really see an alternative.
I guess it's also like they're asking about like our passport is used in the real world, right? But like how would they turn into open passport used in the real world?
What do you mean?
Currently, they have like some kind of infrastructure using the open, like a passport, right? Like, I guess they are asking about like how they start using the open passport instead of current infrastructure.
Like in the real world, like in like at airports.
Yeah.
Yeah. Yeah, I think the airport thing is a bit like compliance. In the future, if regulatory frameworks change, it could be just like compliance. You maybe could just do like a proof of a specific stuff. I do think it's like more down the line because like national security issues are like pretty, like not keen on privacy right now.
Yeah, I guess like the difference is like, it's like we are using a ZK, it's like we don't have to reveal all the data into the passport, but our current RISC system, we need to reveal all the things. So like it's a different.
Yeah, I think privacy is a very compelling.
Yeah, privacy. Yeah.
Wrapping it in ZK. Yeah.
Okay.
I'm going to squeeze in one more question before we do a final wrap-up of each of your minutes.
Okay.
The final question is, has anyone developed hardware, like a kiosk, for these forms of ID for users without devices?
I think here, you did? Okay.
No, but I was about to say that it's a very interesting area. Like I had like some chat with some hackers recently, and we had this idea about maybe for a hackathon project, could be cool like to recreate this airport gate, but with an anonymous proof. So you can scan it, and the hardware has like the verifier component inside of it. So yeah, I would say that there is a bunch of stuff to do like with hardware and ZK proofs.
Awesome. I think like a Hero did like it's like you previously, not before the Myna Wallet, you worked with like an NFT gateway or something, and also like you're using like kind of hardware with like a Myna Wallet, right? So.
Especially in Myna Wallet, this is an NFC card. So if the device can be communicated with like NFC, so it can be, we can build a kind of kiosk device. But in Myna case, actually the specification of the NFC card is not open source because this is under the NDA.
Yeah.
So we can,
Kind of like we reverse engineered the Myna card, and like we are using the card, right?
Before we start, there are several people too.
Several people did, and there is some document about the Myna card that you were using those documents. Okay, awesome. Yeah, okay.
All right, as a closure to the session, I'd like to do a 1-minute wrap-up for everyone else. Perhaps we'll start with Yanis and go all the way to Nico to do a 1-minute wrap-up of your projects, your takeaways, etc.
Yes, so at PSE we have a Discord, so please pass by the PSE website, go to our Discord. We have like a proof of citizenship channel. If you have like, if you see some chip on your identity card, if you see some QR code somewhere, try to scan it, try to read it, see if there is a signature. That might be a high chance that your identity could be snarkified. And like, please reach us, and we can help you. Yeah, that's it.
Yeah, I think it's very important for this trust infrastructure to be, non-profit, credibly neutral, open infrastructure that everybody can access. And yeah, I think that's what we're building out with ZK Passport. I'm very excited about that. And yeah, we also have a workshop at midday today in Classroom B, I believe. So if you want to check out what we're building, please come by, bring your passport if you have it. If not, that's okay too. And we're going to be going through our SDK and showing you how you can essentially recreate the Devcon integration that we made, where you can request, specify which credentials you'd like to request from users, and then the entire flow is taken care of, and all you get back is a zero knowledge proof that you can then verify and use however you'd like.
So yeah, same thing for us. We have a workshop today if you want to come by and see how the whole flow looks like, if you want to try out the SDK or the app. I'm super excited by the future of what we're doing. I think one thing that's kind of been underexplored is there's a lot of different ID systems now. I think some in like Brazil, some in Malaysia, a lot of them also in Southeast Asia that also have signatures and for which the public keys for some of them might also be available, but this is just something that looks like nobody has really explored deeply. And I think the more of those government standards we can snarkify and the more conversations we can have with regulators about making those standards more ZK friendly and more open and more like common across countries, the more this is all gonna accelerate.
Thank you for coming today, and yeah. So I couldn't tell about a lot more about detail about the Myna card or Myna Wallet. So we have the kind of session at AHAB 4 p.m. today. So if you're interested in it, please come to join us.
Yeah. Okay. And lastly, so like I worked in the Myna Wallet, and also I'm currently working on my Open Passport. And from my experience, like there's still some problem because like those government IDs is not issued as supposed to used on the blockchain, like as supposed to used on the ZK. But there is still space we can work on a lot, and it could be like useful. Like it's definitely like a future. Like in the future, like we need some ZK like privacy, those technologies we needed for those IDs. So like it's kind of early right now, but it's not early. But I think like we have a lot of things to do, and we can have like many things to experiment. So yeah, like there's more like ID systems. So like if you're interested in like please ask us or like just like do it, whatever. Yeah, thank you so much.
Thank you.
Thank you, everyone.
Thanks.
Thank you so much.
Thank you.
Thank you.
And that's a wrap. Thank you. If you have any questions, feel free to see them after the stage as well for a personalized Q&A. We'll be taking a short 3-minute break before we start our next session about Quark ID bringing South America on-chain with SSI and account abstraction. Our presenter today is Diego Fernandez with a presentation. Thank you very much. And if you have any questions, feel free to open the Meerkat app, open the Q&A, upvote your questions, and I'll be the one selecting the most voted questions to bring to the presenter and the panelists. All right, our next session is about to begin. The topic is Quark ID bringing South America on-chain with SSI and account extraction. Our presenter today is Diego Fernandez. Quark ID is a self-sovereign identity protocol bringing millions of South American citizens on-chain. Now, if you give Diego the rest of the attention for 30 minutes, we'll go through it very briefly, and I'll do a wrap-up of the Q&A. Thank you very much. Please give a round of welcome to Diego.
Well, hello everybody. Thanks so much for being here. Let me share with you my name is Diego Fernandez. I'm the co-creator of Quark ID. And let me start by showing some hard facts about what Quark ID is. First, it's a self-sovereign identity protocol. It's open source under Apache 2.0 license. It's a digital public good enrolled in the Digital Public Good Alliance. It was launched in October the 21st in Buenos Aires City with 3 million inhabitants, and we onboarded almost 165K users in less than 1 month. And we have 80 million users in the confirmed pipeline, and that comes from 3 cities in Argentina and in Mexico, 4 subnational states, both in Argentina and Mexico. We're doing 2 pilot projects with national governments in El Salvador and in Argentina. And we have onboarded also 2 major banks, which is Banco Macro, the second biggest retail bank in Argentina, and Banco Santander, as well as one of the biggest telco companies in America, which is Telmex, with more than 100 million users. Why did Buenos Aires City started the Quark ID journey? Our vision was, first, governments should pay the friction to create highways of trust, because it will bring enormous value to society. And that highways of trust should be open, non-permission, and available without any government oversight to everyone. And that should give users the ability to decide how, when, with whom, and what information to share. And we did this in collaboration between governments and startups. And we found and we discovered that that creates a thriving Web3 ecosystem that we believe will bring prosperity to the society. What were, in my perspective, the 3 key decisions that we needed to make? Well, the first, decentralized versus centralized. The second, open non-permission versus private permissioned. And the third, open source versus proprietary. And this is pretty important because governments, unfortunately, usually choose the downside of these options: centralized, private and permissioned, and proprietary. And we believe that that sort of waves are starting to change. And of course, we chose decentralized, open, non-permissioned, and open source. Very briefly, what's Quark ID tech stack? Quark ID, again, is a protocol which runs on top of the ZK Sync stack, which uses Ethereum as a security layer. But when you're planning to deploy a system to millions of people using decentralized, non-permission technology, you face an evil dilemma, which is users use today centralized Web2 applications which have an amazing UX. And when we migrate to Web3 world, when we're very familiar with that, UX is so terrible. Just claiming an NFT requires you to go back and forth in wallets and signing transactions is so hard, so hard. UX rules the game. If we don't have a simple approach to UX, there will be no adoption. What is the evil dilemma solution that we found? Well, we give users the choice. You can download the open source wallet from GitHub even and compile it yourself, or you can download it from the App Store. It's an open source, non-permissioned, self-custodial wallet. But we implemented Quark ID technology within the government application, which is running on decentralized railways, utilizing ZK Sync Era and Ethereum, but it's a self-custodial wallet for users which are not so used to deal with this type of technologies. Our way of thinking is, hey, what application will use my 85-year-old mother? When she wants to download a new application in her iPhone, she calls me and says, hey, son, this application is safe. That's the level of users that you need to understand that will be a substantial part of your user base. So we need to give users the choice of having a very simple custodial solution that runs, again, on decentralized railways, or you can go full decentralized encrypted. That's your choosing, not ours. And it's always the use case. And I think that we as a community need to understand that people don't buy technology. Decision makers in governments and institutions, they don't buy technology. They mostly don't care about technology. They buy use cases that solve real-world problems. We need to think, and that's my perspective, as technology, we need to think in technology as a tool, as a means to an end, not an end in itself. From real-world decision makers, if we have the use case, which is pretty simple, a policeman, and that is happening in Buenos Aires today, a policeman, instead of asking you for a piece of plastic, shows you a QR code, you scan it with your wallet, and that gives the policeman the proof that you're able to drive in. For decision makers, for a major, a governor, the president of a bank or whatever, 99% of the decision relies on use case. Of course, we use Ethereum as a security layer, CK Sync to provide CK proofs. We have native account abstraction, and I will follow up on that because it's pretty important. And users control their information, not institutions. But decision makers will see use case. We love technology. Decision makers make decisions based on use case. And the question is, how do we get billions of people on chain? Today, according to statistics, we have almost 600 million of people. There are 8 billion people in humanity. How do we solve this problem? I like to think that the Quark ID mission is adoption, adoption, adoption. This is a very famous quote that Steve Ballmer gave once in this champion all over the place. We probably all saw that. And of course, he was saying developers, 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 and many of us are developers here, and of course, developers are crucial. But when Steve Ballmer was saying developers, 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 his company, Microsoft, had 95% of the user base using Windows. So then it's easy. He already had gained adoption. We, as a community, haven't yet, and we need to get there. And in my perspective, and this is kind of radical, but we need to try and horse the system. And I don't mean this in a bad way. We need to find a way to gain adoption through the system, not against the system. And I am positive that that Trojan horse, that positive Trojan horse, is self-sovereign identity using account abstraction. And why is that? Because, let me go back there. Account abstraction is crucial because each user, when she or he gets an identity minted in Quark ID, they are using account abstraction and they have an account in CK Sync era. It's as straightforward as that. And that enables a lot of use cases. And I was discussing the other day, next year, Buenos Aires City will be piloting the chance of giving subsidies. I mean, the city gives out subsidies to several different things, something like $35 million a year to different types of beneficiaries. But Buenos Aires is evaluating the chance of giving subsidies using their identity wallets, using a token. And there is a great advantage when you're dealing with subsidies. And that is being done because of account abstraction. So that's a great opportunity. And why are governments so important? Because they provide us, or they may provide us, with a reverse adoption life cycle. If governments can help to create the necessary railways of trust, we as an industry should help governments to achieve this goal. And for me, that is crucial. We need to focus on that. We need to understand that there are champions, there are government champions, there are institution champions out there that share the same ethos that we share, that believe in a future with self-custodial basis, decentralized, non-permission, censorship resistant, and they need help from our side, and we should provide their help. I firmly believe that a decentralized, non-permission, open source future is possible, and I'm convinced that we need to do that with governments and with institutions and not against them, and that's our goal. Thanks so much. That was quick, man. I got 10 minutes left. We can do a lot of Q&A.
We can definitely do a lot of Q&A. Well, feel free to send all your questions here, but let me go to the first one as well. How does the open source nature of the project impact business model and perhaps monetization for you?
No, there's no business model for Quark ID. It's an open source protocol, which is being used by several governments. It's not a business.
I see. Okay. Going through the top questions, is it possible to interoperate with other protocols?
Yeah, definitely. I mean, two things here. Of course, over here? Great, thanks, sorry. So, of course, we have two things there. First is the W3C standards, which define DIDs, which is decentralized identifiers and verified credentials, and that gives you a level of interoperability. But, and I'm happy to say this is the first time in any Devcon that we have a specific workshop of self-sovereign identity, and all of us in the industry are meeting today, this afternoon, in order to precisely work on interoperability with the guys from Privado and so on. And we think that there's a bright future in doing that.
All right, next question. Why Buenos Aires? Why start there? And I can recall that you are planning to expand to Argentina, Mexico, and Colombia. Perhaps you'll talk about the country expansion plans and the different regulation challenges in each jurisdiction as well.
I have a very particular view on regulations. First, why Buenos Aires? Buenos Aires is an extremely crypto-friendly city. You have a great pool of talent. Many of the most important projects in the Ethereum ecosystem and in the crypto ecosystem came out from Buenos Aires, just to mention a few: Open Zeppelin, NAMI Foundation, I don't know, Crecimiento and Aleph, and so on. We have very, very important projects coming out from Buenos Aires. Decentraland, one of the founders of Sandbox, and I could keep on mentioning a lot of projects. So Buenos Aires has this amazing talent pool. We are so focused in the crypto industry. And when I, as my former role of Secretary of Innovation of the city, made a call out to the startups and to the innovators in Buenos Aires, everyone started collaborating, and we came up with this solution, which we're really proud of.
Okay. Crypto-friendly city. Where else besides Buenos Aires?
Well, I mean, Buenos Aires is a crypto-friendly city, of course, and we are working as a community very, very strongly, and now Milagros from Crecimiento will share that with you. We think that Buenos Aires and Argentina could become one of the first, if not the first, crypto country. We're struggling to do that when we're sort of working to do that, and of course we will need your help.
All right. Can you describe your level of partnership with other protocols? Maybe some strategic planning, maybe other companies that you're looking to collaborate with?
Well, I mean, of course, and we shared that yesterday in a panel that we were with Evan and Anthony from Privado ID. Something like 3 to 4 years ago, there was basically nobody speaking about identity but Privado and Disco XYZ by that time. And our vision is there are 8 billion people in the world. I mean, there's so much space that we should work together.
Okay.
There's a question that I would like to ask.
Sure.
The answer there is, where are the credentials stored? On-chain or off-chain? Mm-hmm. If on-chain, how do you handle privacy risk? No, not on-chain, not on-chain. Never, never, ever, and never, ever, ever you can put personal information on-chain. The technology behind the standards of digital identifiers and verified credentials work this way. What you have anchored on-chain is a digital identifier. That's the only thing which is anchored on-chain. Credentials are minted and stored off-chain. So just to give an example, you have the DID of the city of Buenos Aires or any other government or institution, and you have your own DID. So when you want to mint a new credential, and those are anchored, in our case, in CK Sync Era, and when you need to mint a new credential, you ask the issuer to give you that credential. That happens on a peer-to-peer basis using a protocol which is named Devcon. And what you are doing is you're signing a JSON digitally signed by this DID in favor of this DID. And that is stored in the personal device that the users have in their hand. So when you need to verify that credential, what you do is you check that the credential is valid, that it's not you, that it's not void, and that it was signed by the issuer in favor of the holder. So you rely on on-chain security, but the data is stored off-chain. How does Quark ID plan to maintain its technological advantage in the long term? Well, basically, as any other open source protocol, expanding our user base, generating interest. The amazing thing is that when you do this, again, reverse adoption life cycle, and you start to have millions and millions and millions of users, developers start to build on top of it. And we have several startups and several companies building on top of the protocol and even expanding it. Just to give you an idea, when we were involved in this is a very small thing, but it's quite nice. When we did the Aleph pop-up city in August, the passport for entering Aleph was a credential minted in Quark ID. And one amazing guy, his name Tule, he's not over here, I guess, did this extension of the protocol, connecting it with an Arduino device in order to open a door. So when you access the hub, you scan that, show your credential, and the door got open, which was so nice. And that is, I mean, the community building and developing.
Can we squeeze in a question about competition? How is this project different from Provido ID or Polygon ID?
I don't know in such a detail the stack of Provido ID and how they are working now with Disco XYZ because they recently merged. But again, we, of course, believe in competition and we respect each other very much. And as I said before, I don't think you need to have the technological basics that you need to implement. But this thing is not about technology. This thing uses technology to gain adoption. So what's our focus? Adoption, adoption, adoption.
And perhaps on the final question on adoption, since we have a few more minutes remaining as well. Can Argentina's adoption by both its government and citizens serve as a model for other Latin American countries?
I wouldn't say serve as a model, but when we're dealing with such border innovations, and the other day I was thinking, isn't there a more obvious case where innovation is needed than identity? We are sending or trying to send rockets to Mars. Elon Musk is catching rockets falling out of space in midair. We're discussing artificial general intelligence models, if they're going to rule or not the world. And when we need to identify ourselves, we pick a piece of plastic and start doing like this on camera. My God, that's so stupid, so stupid. We need to change that. Now, of course, it's identity. Institutions can feel fear, and finding some governments and big institutions as Banco Santander and Macro that were able of taking the first steps, of course, makes every other one in the place say, hey, come on, take a look at those guys. They did it. Why don't we?
Alrighty. So that concludes our session. Can you do a quick wrap up about what you do, a key takeaway, maybe a high-level description, and for the audience before we conclude the session?
Yeah, of course. I mean, for me, the most important part is if we are going to achieve what we think is the ethos, and we feel the ethos of this community, of having decentralized, non-permission trust and value being exchanged over the Ethereum network, identity is the way to go. Governments and institutions are the adoption path for going from 600 million to 7, 5, 6, whatever billion people in the next 4 to 5 years. And Quark ID and my team is trying to achieve that or help to achieve that with all of the other players in the industry. Thank you so, so much.
Thank you. Please give a round of applause to Diego. That is Quark ID, bringing South America on-chain with SSI and account abstraction. Now we're going to resume our session at 11:30 sharp with a topic called Argentina's opportunity and the case for a special economic zone, presented by Maria Melagros Santa Maria. So we'll see you shortly in about 9 minutes. right, we're about to start our next session, Argentina's Opportunity and the Case for a Special Economic Zone, presented by Maria Milagros Santa Maria. She'll do a 5-minute Q&A, and we'll top it up with a 5-minute presentation as well. So first, please give me a warm welcome applause to Miss Maria.
Hello, everyone. Thank you so much for being here. I only have 5 minutes, so I'm going to speak super fast. I'm actually not. I'm going to try to make the most of this 5 minutes. So I'm going to talk about Argentina's opportunity and the case for a special economic zone. So let's divide this by topics, which is what is this economic and technological opportunity, how Argentina is related to it, special economic zones, and where we're at. And I think that all of us here, we can agree on something, which is that technology is one of the strongest drivers for human progress. Therefore, so are tech companies. But do tech companies thrive everywhere? Technology can be created anywhere, but for tech companies or startups to be able to develop, they tend to go to the places with the best conditions. Therefore, blue zones. Why would they stay in a place where they pay maybe too much taxes or that the government's not stable enough, right? So there's going to be this tendency for big important companies to go where they want to develop best. Therefore, there's this idea that economies need to improve, but they also compete between each other. And here we can see a table. This is mostly about tech companies, not only crypto. That's already related to where is best to be. And we can see some countries like the US, we can see as well. We can see Japan, we can see Singapore. But when it comes to Argentina, it's not so pretty, is it? We can say over here when it comes to learning and exploration, but when you're already on pre-seed, you start itching your legs and you kind of want to leave, which is sad. Because when it comes to Argentina specifically, we got a lot of talent. We got talent when it comes to tech. We got talent when it comes to crypto. We got talent when it comes to AI. It was Diego Fernandez with Quark ID, which is a great example as well, that mentioned Decentraland, MakerDAO, Open Sapling. And it's not only that the companies are there, it also means that the community is also there, the talent is there. If you look at other protocols in the world, you're going to find 1 or 2 Argentinians walking around. We're pretty nice, you're going to see where we're going. But as well, there's also the adoption. It's one of the countries in the world with the most Web3 adoption. Now, the thing is that even though this is the case, Argentina is not yet the crypto nation, international crypto nation that we want it to be. But there is no international crypto nation for countries to be at. I'm a lawyer by background, and when it comes to the structure that a company would want for fundraising or token deployments, you'd make a mix between Cayman Islands and BBI and Switzerland, depending on your budget, but there's no specific jurisdiction that can help you with everything. And that's why we started talking about Argentina's opportunity, this perfect storm that comes from bottoms up, top to bottom. The community is there, the talent is there, the will and the necessity of certain market fit products is also there, and also top to bottom help and support from the last government. If you look just on facts on the last year in Argentina, I'm talking about 11 months actually, there's been the most regulatory development that helps the industry on Web3 than in the last 4 to 8 years on the past governments. Therefore, the intention is there. What we're trying to show is that the necessity on the market is also there. These are economic problems that several that Argentina has, right? And these are the different ways that through crypto-related startups or products, there can be a difference that fixes it. We just need the amount of startups that want to come and stay to actually make the difference. And that's when we start talking about the necessity of longevity. Therefore, a special economic zone that can help this happen. Because even though different jurisdictions in the world have had their own way of trying to make nice little environments for development, none has been the top of all of them. And we have seen through history, because special economic zones are not new, that there are different ways of changing your economy from scratch. Therefore, we want to provide longevity. We want to give the top support for businesses, many times supported by common law as well, for the attraction and retention, especially retention as an Argentinian, for talent and investment, right? Therefore, there are different ways that we can do this. Either we do nothing and we just stay and we just look at everything burn. I know that more than one people here might be a nihilist, but let's try to avoid this option. Or we just change a bunch of laws. This takes time, this takes effort, people don't really trust there's going to be change. Or maybe you just change a bunch, you make it more globally friendly, but the amount of difference and benefits that you could have with the special economic zone, which we're working on for the creation, is a very different kind of flavor that you would give it because the benefits are different. What we're trying to show over here through Crecimiento, which is the entity that we work with, is to provide Argentina for an opportunity, not only for Argentinians, but for the world, to become the crypto hub for Web3 startups to be able to not only develop, but thrive. Therefore, we're already working on a regulatory sandbox, public affairs with government and regulators, and the creation of the special economic zone. So please, this is us. This was only 5 minutes. I still have got 13 seconds left, so I'm very proud of myself. I hope you guys got to understand everything that I was saying. And we still have got 2 more minutes. Meanwhile, if you guys want to connect, please feel free.
Alrighty. We're going to do a few minutes of Q&A. I'll start with the top question that we currently have from our audience. What stage is Argentina's SEZ? What will be the incentive for startups to relocate there?
Okay, so stage is the following. Currently, Argentina's legal framework does not allocate for the creation of special economic zones. So what we're doing is drafting what we call a layer 0 for the permission of the creation of them, while we also start drafting what we call a layer 1, which would be the first digital special economic zone, as the intention would be not to have this kind of benefits that come from tax, that comes from customs, that come from capital markets, and that also comes from labor laws, for them to be just arranged to one physical space, right? So the benefits for startups would be to find in this special kind of zones the kind of economic conditions that make or break a business, which is one of the reasons that a lot of people like Cayman Islands because of taxes, right? Or why a lot of people rather go to Switzerland because of the reputational law that they have, or the reputational conditions that they have when they deal with different kind of investors.
All right. What trade agreements or partnerships are in place that could benefit tech companies operating in the zone?
Trade agreements. Oh, okay. So in this particular case, there is 2 different kind of views that you could have, from a national perspective and from an international or business perspective. From a national perspective, what we're doing is working with Congress, working with the federal states in Argentina, therefore for them to understand what we're doing and what we're trying to do. In this case, it has to do with training and also with the public affairs teams that we have, and also and especially with regulators. If you have a Web3 project, you're most likely going to be touched upon by the Argentine version of the SEC, Central Bank, and FinCEN, which is CNV, Central Bank, and WIF, working with them as well for the creation of this sandbox that should be launching by next year, and with the assistance that would require to make it work.
One final question I'm squeezing in. What are the next steps in the regulatory sandbox? And then I'll ask you to do a wrap-up of the session.
Amazing. So the next steps are the following. We already made a joint presentation to the regulator with the Argentine FinTech Chamber. What we did was put the basic characteristics that a good sandbox would need for the ecosystem to do better. Because it's not sandbox, yes, sandbox, no. It's most likely bad sandbox, bad for the ecosystem, good sandbox, good for the ecosystem. So right before I took my plane here, we had a meeting with my team and the members of the CNB that are drafting the technical table, they call them. They're drafting what would be the fine line. And they asked for our support when it comes to the comparative analysis with different sandboxes in the world to see what works and what doesn't, and what should be applied in Argentina. So what we're doing is helping them with the fine line. So after they're okay with it by end of this year, they could start doing the approval and incorporation or launching for next year. And as a wrap up, the opportunity of Argentina is the following. It's an opportunity that shows that the community is there, the talent is there, the necessity of product market fit is also there. But as well, we have the government that is opening an opportunity, is opening a window for change to happen. And at the same time, the necessity of the global international market to find a place to thrive, and how both of them combined could find a solution with Argentina.
Love your speed and energy. That's a wrap up of the session, guys.
Thank you.
And if you have any questions, feel free to follow Maria later and ask about Argentina's opportunity for the special economic zone. Thank you very much. In a couple minutes, we're going to start the dynamic duo, Juan David Reyes and Romina Sejas, on the topic of Ethereum in the classroom, teaching Solidity to high school students in Buenos Aires. So stay tuned, hang around for a couple minutes. Thank you very much. Hi everyone, technical hiccup right there. Our next session is a 10-minute session covering Ethereum in the classroom, teaching Solidity to high school students in Buenos Aires. Please give a warm welcome to Juan David Jerez and Romina Sejas. Please feel free to come on stage. We'll do a quick presentation and then a Q&A afterwards where I'll be asking the top voted questions on Meerkat. Take it away.
Well, hi to everybody. Thank you for coming. This is our first time as a speaker in Devcon, so we are super happy. And we will start with a quick introduction. Well, what is Kipu? We are a foundation. We are grantees from the Ethereum Foundation through the Ecosystem Support Program. We are a group of people from different countries from Latin America, and we work together to strengthen the Ethereum ecosystem through education and cooperation. We have different work areas. One of the most important for us is education, but we have to keep stakers, keep impact, and we have a special area, IT Latam. Every year, we organize an annual conference in different countries. The last edition was this year in March, and we were in Honduras. And we noticed a significant change, a lot of young attendees. For us, it was a unique experience that made us rethink, approach our events and our courses. So last August, we approached the Ministry of Education in Buenos Aires with a proposal to hold an event for 200 students from high schools, and was a success. The girls and the boys were super happy and interested in blockchain. And for us, this became the starting point for launching a pilot program to teach Ethereum in high schools. So please continue.
Thank you, Romy. This was one of my most scariest moments, but also one of the happiest, because I was in front of 200 people that maybe they were forced to be there, not as you guys. We are all grown-ups who want to be here. We are convinced about this. And what we have learned through the pilots that we are doing with the Ministry of Education is that we first develop the content, and that's what we are doing with our Solidity course. We are doing an online program. We also are filling a gap, which is how to take that knowledge and teach that to the trainers that potentially will replicate it on their high schools. And maybe you are here because you want to learn about what is going on in the classroom. So we got the spotlight of the global community with this tweet of Bankless. Argentina is leading the way because we are taking Solidity to the high school curriculum. And we want to share some of our insights so far. The program is called Prácticas Profesionalizantes. You can translate that to professional practice programs, where we have 24 students from 7 schools that are coming to a lab. They are taking our Ethereum developer pack, and they are building a product. This has been 2 years of creating an open source content with 5 modules, but we are not yet there to include that to the high school curriculum. So what we're doing is having a hands-on experience, because kids are super smart. They already know what they want to do, so we're giving the tools, and Ethereum can shed light to opaque process. And in Argentina, they have something called cooperadora. Parents put some money on a fund, and they have to decide maybe by the end of the year to do a trip or buying some equipment for the classrooms. But sometimes there is some a suspicious use of the funds. So with a smart contract that they are developing, they want to create this product. We are having an MVP. We are documenting all of this. We have 2 teams. So we have the non-technical students, like people in design, advertisement, and also we have the programmers, and they are working together. We have 3 insights so far that we want to share, and we are documenting that. First, you have to give ownership to the students, because they're super smart. They already know what they want to do, and if they have autonomy, they will come with an answer. You also have to remain flexible. So with the Ethereum Developer Pack, we are adapting that every day. And we are also replicating some real-world experience. They are communicating through Discord, documenting on GitHub. They are having sprint reviews. And I want to have a call to action. If you're seeing this talk back home, scan that QR code, and let's keep in touch, because we want to share that with the whole world. We want to start with Argentina, then move to the region, and if you are in Africa, Asia, we would love to share that with you. And finally, this is a provoking questions. How will you teach Ethereum to your 15-year-old nephew? How we can take all this sophisticated, complex technology to them and inspire them to build a new future. This is what we are all about, and if you come with an answer, let's keep in touch and let's get Ethereum out there and spread the good that Ethereum is taking to the world. Thank you so much.
Great talk, folks. We're going to start with one question that we have and a few more that we prepared as well. How can these experiences become composable in the region?
Great question, because Ethereum is all about composability. Actually, we have our grants program. So there are a really talented group in Colombia. They are developing a plugin for Moodle. We have our campus on this open source platform that has plugins. So we are doing attestations. So our courses are being attested on using the Ethereum attestation service, and we are creating these like synergies with products that already exist and that are being integrated crypto-native tools.
All right, this question is packed with several responses as well. Who are the teachers? Firstly, describe them first.
The teachers, after having like this spotlight from after the tweet in Bangladesh, we were overwhelmed about like 30 people wanting to collaborate. We have amazing developers, and I think this is the spirit of Ethereum. People learn something and they want to share it with the world. So usually they are developers that are specialized in really niche use cases, and we are taking that knowledge, going through the framework that we have developed, and we teach them how to teach, because they're already great, talented coders, and now they want to become teachers.
And are these sessions online or offline?
Online, we are documenting that. We are uploading that to our campus, so people can also learn how to teach about these topics.
Can you mention any Web3 usage of crypto in Argentina, perhaps a student project that you're very proud of?
The one that we mentioned, the Cooperadora, this is like our MVP and the thing that we want to share with the world.
Okay. Our audience asks, if we wanted to host educational events in our local area following this curriculum, how can we replicate that?
Great question. Our content is open source, so we have that on Gitbook, on each module is on GitHub, so you can make a PR, and we can get in touch, and we are more than happy to share the knowledge.
Thank you. That wraps up the Q&A. Before we conclude the session, perhaps 1 minute to do a key classic concept, takeaway, final message for the audience.
How can we spread Ethereum for good? I mean, sometimes we are up in the clouds in the ideas, and we need to make it tangible. And as Rami mentioned, that was one of our main takeaways this year. Like, we are having young and the new generation coming to our events, so we need to think about context and like student-friendly content for them. So we need to get on board like the new generations of builders to Ethereum.
Thank you. That concludes the session on Ethereum in the Classroom, teaching Solidity to high school students in Buenos Aires. Thank you very much for your time. And in the next session, we'll have the ripple effect of Devcon with Julio Cesar Arango, starting in a few minutes at 11:50, 2 minutes. In our next session, we'll be talking about the ripple effect of Devcon and how Colombia and Latin America are now growing local communities and having new perspective about social impact and blockchain. Please give a kind, warm welcome and applause to Julio Cesar Arango. Take it away.
Hey everyone, thank you so much for being here today. I'm going to talk about what's been happening after the Devcon 6 we had in Bogota 2 years ago. I am Julio Cesar Arango. I am a blockchain education manager. I'm part of the Ethereum Colombia and Ethereum Bogota teams as a volunteer. I'm part of the ETH team on the educational logistics side, and I'm co-founder of EducaETH and SEAL, that are projects aimed to improve blockchain education in the region in Latin America. So 2 years ago, we had Devcon 6 in Bogota. It was an event that brought thousands of minds to the city to get together and start improving the ways that we did things before Devcon. So in Devcon, it was a fantastic gathering in one venue, a big venue that we have in the city there in Bogota. It was a place where we were able to meet in between and start working together. A lot of things started at that moment in the whole region with leaders from every country of the region. And it sparkled, it started something that was joining together more community in the different cities of the region and having community events that brought a lot of people inside the different countries. There were a lot of new steps on how to bring blockchain education to the region through different methods all over the place, all over the different countries, starting using new programs to involve developers in the Ethereum ecosystem. And it started growing through alliances with universities and networks of universities. This was something that wasn't happening a lot before the Devcon, but afterwards it started to pop up in different places all over the region. And it happened more through hackathons and these alliances with universities. And it just came all over the place. So right now, between all the different communities around Ethereum in the region, we have onboarded over 2,000 developers, mainly Web 2 developers into the Web 3 ecosystem and the Ethereum ecosystem itself, to different programs. And it's people who, before Devcon, they had no idea of what was going on in the industry, but now we have this new sense of consciousness of what are the possibilities, and mainly taking the message to the people in the region that it's not an industry only to be a user, but you can be a builder. And it's something that it's been made to attending 3 main points, that is community, education, and development. 2, alliances, events, and production. And it is growing and growing. There's more and more alliances happening all over the Latin region between the communities and universities, other different communities, social places, and in general, the actors of the ecosystem, like putting everything together to make things happen. And right now, there has been a great improvement in the ways to do and to bring the education to the people through online programs and putting together developers and students from all the region together, developers and non-developers who are starting to build in this program. Have we had some impact? I'm just going to mention a few cases of the students that we have had that I don't know, 18 months ago, they had no idea about the industry, and now there's the case of Neil, who's at his 17 became a Devcon 2023 scholar, and he was able to travel to Turkey and share his experience as a new developer with developers from all over the world. And also, after this time, Christian and Juan Diego, who are here today, they, after taking these courses and joining to these processes and giving time to it, they have been able to find jobs in the Web3 industry and go to, they used to work at a call center before that, and now they are part of the industry, and they were able to travel here to Devcon. So what needs to go next? We need regional coordination. We need to nurture an environment of trust between community builders and community users, so we can take all this to a next steps after the education and create spaces in common between the different actors of the whole region. So we need to push to encourage frequent blockchain interaction within the different communities and find places where we can share hackathons, opportunities to work open source, and bring this to a next level. Before the end, I just want to mention into this great impact that has been in the region, there's have been also very difficult times. He was Emerson David Silva. He was part of the Ethereum Colombia leadership, and he was assassinated by the war, this terrible war we have in Colombia. So we lost him this year in March 27, and I asked myself, why can't I do, Emerson, to preserve and honor your legacy? He's present every day in my thoughts, and the community and the leadership thoughts. We want to make his legacy to go further. So we need to support Emerson's family. So if you scan this QR code, we have a Give It project. So we are trying to get funds to help his family and to keep on helping on the operations on education in Colombia and Arauca. So thank you very much. It's been a pleasure, and thank you.
Thank you. We're going to do one quick question of Q&A. You mentioned you onboarded 2,000 developers to the ecosystem. How did you estimate this number?
This number is estimated between data that we have from the different organizational processes that is being taken into the region. So we have, it's more than 15 organizations onboarding new developers, so this number comes from what has been done in the latest 18 months.
And what do you think are the best next steps for the students that just learned about Ethereum?
The next step is the most important thing, because we need them to take what they learn through the different educational processes and apply that into hackathons, working in open source, working together, meeting other people, and this is something that we are pushing right now.
Thank you very much. That concludes the session, everyone, on the ripple effect of Devcon by Julio Cesar. Thank you very much for your time.
Thank you.
The next session will start in approximately 1 to 2 minutes. The role of culture in shaping technology, the case against tech neocolonialism by Fatame. Thank you. The final session for this morning, we have Fatime presenting the role of culture in shaping technology, the case against tech neocolonialism. Please give us a warm welcome applause to Fatime. Thank you. You may take the stage.
Hello, everyone. Thank you for being here. I'm going to talk to you about QtAC, but before I start, there's the session QR. If you have questions, I'm not going to take questions, but I want you to use this to put comments or anything else that you want to flash on stage after my 5 minutes. I'm going to talk about QtAC and the role of culture in shaping technology because this is my latest obsession. And it has like QtAC has a lot of mimetic power that I hope will catch on with you. And why am I talking about QtAC? I'm not going to describe you what QtAC is because I think you have to feel it and I think you all can relate somehow with it. I'm going to talk to you about why I actually think it matters and why I care so much about this. And this is because we're going through, I think the world right now is going through a war of meaning about like what is good and what is bad. There is a lot of weaponization of what is good or bad, these notions to actually do harm or to impose bad things on good people. And we see also within our industry the fact that cypherpunk is seeing a revival, that Ethereum wants to make it cypherpunk again, and the whole track in Devcon about cypherpunk. But I am actually worried when I see how we idolize cypherpunk technology or how we are idolizing privacy and also the projects and the people that are involved with this one particular set of technology, because cypherpunk does not necessarily mean good or bad, right? It's kind of the end, the technology that is being birthed, but the whole process that leads us to this technology is not necessarily a process that is grounded in goodness or that has some values that goes with it. I think it's very similar to having a kind of like single issue approach to things, and we saw that with the US elections where politics have been supported by our industry, although there is actually nothing, I think, cute about this politics, and maybe it can serve our industry in the short term, but I don't think that if we imagine a utopian future, then there is gonna be these sets of politicians in it. So cypherpunk is not enough, and I think that we need to put the bar way higher and not just be content with cypherpunk technology and not just be idolizing or having cult of personalities around people involved in cypherpunk technology if there is not this goodness that goes with it, and if actually the way they are building and the means that they're using toward this end is good and something that we want to be associated with and we want to see in the world. Yes, another cat. So yeah, cypherpunk needs to be grounded in goodness, but how can we actually ground it in what is good? Like what is good, what is bad? Like I cannot tell you what is good and what is bad because I have my own opinions, but I don't think that these are universal truths. And I think history proves to us that too, like what was good or bad in the past is not necessarily good today. What was bad in the past may even be desirable today, and with the same logic, things will change in the future. So there is no one single universal truth within time, and our technology is kind of transcends time, right? And we cannot make this decision today of what is good and bad and have it stuck for the future. But at the same time, it transcends space as well. Like what is good or bad in a specific culture or for a specific person is not necessarily the case elsewhere. People have different priorities and different values. So absent the possibility of rationally coming up with what is good and what is bad, how can we conduct ourselves? Because I still think that we should not give up on grounding cypherpunk in goodness. And when we see that fascism and hatred and violence is accelerating in the world, while we're living in this world of actual abundance, or we have democracy, we have a lot of toolings, we have amazing technology like internet, blockchain, distributed consensus mechanism, AI, and despite this abundance, there's a lot of negative things that are accelerating. And I think that we need, on the other hand, to accelerate positive culture, and this positive culture acceleration must come through cuteness and cute acceleration. And I think that this one sentence that someone told me yesterday about it summarizes really well. This fuzzy feeling that we all have experienced when we're faced with cuteness is actually very powerful. It takes a lot of space within us. It removes space that could be used to do harm, or like removes tolerance for harm as well. It promotes collaboration, promotes motivation. Feeling good is great. It has value in itself, and I think that we should all be cute accelerationists. Thank you.
Thank you for the lovely presentation. We're going to have a few questions here based on the most top voted comments. What visual symbols and imagery could help the cypherpunk model move to be grounded in goodness?
So, I don't know, this is up to all of you, but I actually forgot to mention this. I'm wearing this little toy that is swag from the DIAC day that you should go check out. And this is exactly an example of like a really cute, useful swag that does accelerate goodness, because it's useful, and you can find out more about it at their booth.
And more of a serious question. So multinationals, corporations play a huge role in shaping the tech landscape for developing countries. So what do you think about this on a global scale? How might this impact local cultures and economies for you?
Yes, I mean, this is a big problem, right? And that's what I call tech neocolonialism, when like a set of like a few entities and people and technology are actually imposing our online realities to the whole world. And then it does impact a lot culture, and I think culture is becoming more and more harmonized the more we're moving and the more we're interconnected. But I think by bringing in cute act again, we can actually have this critical view of technology and decide whether or not like it's cute and whether or not we want to promote it or even relate to it. Like, is surveillance cute? I don't really think so, right? Like, there are so many things that I think we can navigate through this lens. There was no troll questions. I invited you to do something.
Any final questions from the audience? Otherwise, if you have any follow-up or detailed questions, please shoot the Q&A and then we can have it all. Perhaps we can maybe give it to the audience for one final special edition before lunch break. Cannot. But you can always follow up with Fatima later. So this will conclude the session on the role of culture in shaping technology, the case against tech neocolonialism. We'll have our next session in approximately an hour from now at 1:10 p.m. Thank you very much for your time. Oh, 1:10 ไม่ใช่เหรอ
โอหรือพี่โอมนะคะ
โอครับโอ
โอพี่โอก็
โอเค Hello and good afternoon to you all. Welcome to stage one. I hope you had a good lunch. I'm a local myself. I had lunch here, had food here. I'll tell you, like, it's amazing by my standards, so please enjoy it. My name is Anut. I work for the Devcon team, actually, but for the next 2 hours, I will be your MC for this next session. This section is all about core protocol, where we'll share the latest research findings, EAP slated for implementation, and suggestions for the Ethereum roadmap. This section will last about 2 hours, 4 talks, and all about core protocol. And a reminder again, please scan the QR code to access the Meerkat, scroll to the bottom right to join the Q&A and upvote the questions or create the questions yourself. You can also collect attendance card there and also give speaker feedback within the QR code that we present to you. Without further ado, I'd like to introduce you to our first session. Right? A lot of discussions in the Ethereum ecosystem has always been about the protocol layer, but the network layer is also very critical to the Ethereum's decentralization. Is it resilient enough? Do we have a proper methodology to test it? We have with us today Daniel Knopik from Ethereum Protocol Fellowship, and also Pop, Ethereum Foundation researcher, and they'll be talking about simulating an Ethereum network at scale. Everyone, please welcome Daniel and Pop.
Hi, my name is Pop. I'm a researcher at Ethereum Foundation, and this is Daniel, our Ethereum Protocol fellow. Today we are going to talk about network simulation. Before talking about the network simulation, we have to know first like why we do simulation at all, right? From our experience, we usually have like 2 common use cases. Like the first one is like, for example, if you have like the protocol idea and you are not sure like if it's good or not, right? And maybe you want to test it first. So you have to run the simulation. The second one is like, for example, if you have the hypothesis that okay, maybe you have the illusion that it's good already, but you are not quite sure yet. Maybe you want to run the simulation like to confirm your idea. Right? When you do the simulation, usually the input usually be like you have to have the protocol implementation first, right? Otherwise you cannot simulate it. The second one is like you have to have the network topology in mind, like how much bandwidth each link have in the network, right? Or like how much is the latency and like how much is the packet loss rate, right? And you have to make the network topology like as similar to the real world as possible. Otherwise, like the simulation doesn't make sense at all, right? And the output of the simulation, what you usually want from the simulation is like you want the metric like the number of reoffs or message propagation time, and in fact it can be anything that you want that you are not sure that what it will be like before the simulation. Before talking about like how we do the simulation, I want to talk about like how we do the simulation like previously. And previously, what we usually do is like we run the client inside like the physical machine, and then we use something like NetM to emulate the link. Like maybe you want some like bandwidth on your link, like you just use NetM, or maybe you have the latency that you want to just use NetM, and you just run it in the physical machine. And that doesn't work, right? Because it doesn't scale really well. Like when you run like a lot of nodes inside a secure machine, they will compete for the CPU, right? And that is bad because the timing will be like inaccurate, right? Yeah. And like I think you can just run a few nodes like inside a single machine. So what you will do instead is like you have to look to have like a lot of machines to simulate, right? And that is like a problem because it doesn't scale. There is something called like discrete event simulation. The discrete event simulation is like instead of running the client inside the machine like directly, you run it inside a simulator, and the simulator will process and create the event. Like first of all, when you send the message to network, right, and that's a kind of an event, and when you receive the message from the network, that also the event is like instead of running it in the machine, it will just capture and process the event. It's good because the clock in the simulation will be independent from the real clock. So yeah, I will tell how it works like later. Yeah, because the node don't have to compete for the CPU anymore, so you can run like any number of machine inside a secure machine, and you will get the quite good simulation result. And we have a problem with the existing discrete event simulator because yeah, like NST or Omnet, when you do the simulation, you have to call the library of the simulator. And that's a problem because when you have to call the library, you cannot implement the protocol like in any language, right? You have to implement it in a supported language that the simulator support, right? Because you have to call the library. Like calling the library to send the message and like receive the message, something like that. Yeah, but we found that there is a great simulator called Shadow that doesn't have this problem. The Shadow is instead of forcing you to call the library, what it does is like it will intercept the system call that the client make, right? And like so by doing this, you can implement your protocol like in any language because and then run inside like Shadow. Yeah. So for the example of the system call that it will intercept is like the send system call or receive sender call. Yeah, and that's as I mentioned earlier, is a kind of an event. And another important thing is like the get time of the day, because we intercept the get time system call as well. So so you can tell your client like what time it is, right? So that is why the clock inside the simulation is independent from the real clock, because Shadow will tell your client like what time it is. So that's quite great. Yeah, so in short, Shadow can simulate like a lot of nodes, right, with the real client software, because you don't have to implement like in some specific language. You can implement it in any language, and then you just run Shadow with your client, and then in fact you don't have to modify the client at all. You just use your client and let the Shadow intercept the system call. And we implement something called like each Shadow, because Shadow work with like any kind of software, but not specific to the Ethereum client. So we create something called each Shadow to let you run the simulation like easily. You just like tell what client you want to use and like how many nodes, how many like yeah, and then you just run it easily. Yeah, the next is we are going to talk about like each Shadow. Let Daniel talk about it.
Thanks, Bob. Hi, I'm Daniel. And over the past few months, we've worked on ETH Shadow, which makes it really easy for anyone to run Shadow simulations, including Ethereum clients. So in one sentence, it is basically a configuration generator that makes it easy to simulate Ethereum networks in Shadow. It has a couple of features. First of all, it has a rather simple YAML configuration format, so you don't have to learn anything fancy. It allows you to simulate realistic geolocation and network reliability. It supports Geth, Lighthouse, Teku, and Reth right now, with more planned. Hopefully soon, or at some point, supporting all clients. It allows us to capture client metrics, which is nice for analyzing the simulations after they've run. And it allows you to run your own programs as well. If you want to simulate some malicious nodes or some attack scenario. Finally, it scales well. So you can run simulations with over 100 nodes on your laptop. So Ethereum, as you know, is a huge distributed network, and it's globally distributed. Yeah, there are like a lot of nodes in Europe and North America, but also a few in Australia and East Asia and South America, etc. And for simulating such a network, to figure out future changes to the Ethereum protocol, it is important that we can simulate the fact that we are distributed across the globe. So here you can see a configuration sample of ETH Shadow. On the top, you can see we define the first node, which is located in East Asia. It also sets a reliability, which I'll get into soon. And on the bottom, you see that we define 10 more nodes in Europe and NA East, and also North America East, and it will distribute those 10 nodes across these locations. Yeah. Home stakers are very important to Ethereum. Like, we want to be decentralized, so we want people to run actually nodes and validators at their homes. But the problem, or the fact with that, is that those nodes often have not as good of a network connection like something running in a server farm. And we can reflect this in the simulation by specifying a reliability. The top node is marked as reliable, which has a gigabit of bandwidth, no added latency, and no packet loss. But the bottom 10 nodes are home nodes, and they have restricted bandwidth, a bit of added latency on top of the geographic latency, and also a tiny bit of packet loss. Yeah, you can define your own reliabilities and locations if you really need them, or just use the predefined ones for convenience. Clients. As mentioned, right now we support Geth and Lighthouse, which is like first-class support right now, and there's also support for Reth and Teku, which is currently in testing, and it's pretty easy to run mixed client stacks. Again, we extended the configuration. On top, you can now see we have Reth and Teku, and on the bottom, we use Geth, Lighthouse, and the Lighthouse Validator client. And that's all you need to do for ETH Shadow to configure these clients and distribute the configured validators across the validator clients in the simulation. We also support some other software. For example, in the bottom, you can see Prometheus, which will automatically be configured to receive all the metrics from the consensus layer clients. We have a purpose-built blob spammer because I did some simulations on PeerDAS, and for that we needed a blob spammer. So yeah, it's also pretty easy to use, but omitted on the right here. And also, you can configure your own program. So if you have a modified version of Lighthouse, for example, which does something malicious just to test, you can configure it as well. Supporting more clients. Well, to be a really useful tool, it would ideally support all the Ethereum clients. However, this is not currently the reality, because unsupported clients use an unsupported Linux system call, like unsupported by Shadow, or get stuck in a spin lock, which Shadow can't really cope well with, or it uses a supported Linux system call, but the implementation in Shadow is a bit different than the actual implementation in Linux. And Shadow supports currently 186 of approximately 375 Linux system calls. That's a lot of system calls, and only 4 of approximately 80 socket options that you can set when you are opening a TCP socket or UDP socket. And to support all programs, we would have to implement all these system calls and socket options perfectly accurately, which is really hard to do and not really feasible to do on short notice. So we need to kind of pick what we need. We could also just modify the clients that are running in the simulation to avoid those system calls, or do not set this socket option, but that is also not kind of nice because we don't want to maintain forks of clients indefinitely to support them in Shadow. So yeah, we have to implement these missing features in Shadow instead, which will take some time. Simulation size. So our claim is that we can run simulations with over 100 nodes on your Linux laptop. But before we get to that, let's look at small simulations. Small simulations with under 10 nodes, for example, run pretty quickly. Like on my system, they ran faster than real time because, as Pop mentioned earlier, Shadow can also manipulate like the get time of day calls or something like that to pretend that time is running more quickly than it is in real life. And as your simulations get larger, of course, the CPU time gets congested and simulations will run smaller. Here are two examples. On my system, I usually run simulations with 38 nodes, which nicely fit into my 28 gigabytes of main memory with REST Lighthouse and a Lighthouse validator client per node. And for me, it took like 45 minutes per 30 minutes of simulated time, so 1.5 times slowdown, which is rather nice. On Pop's system, we tested 100 nodes with Geth, Lighthouse, and Lighthouse Validator client, 16 gigabytes of memory, and to simulate that many nodes, you will need swap space, so we used 32 gigabytes of swap there. This took far longer, 11 hours for 10 minutes of simulated time. So it is possible to run those, but you should probably start with a small simulation to confirm that everything is well, and then just let your laptop run overnight if you really want to have a larger simulation. You can also run really, really large simulations with over 1,000 nodes, as we tested. And for that, I rented a server, and that had 1 terabyte of memory, and that took, for 45 minutes of simulated time, 4.5 hours approximately. It kind of varied a lot at that point. And also at that point, what I want to note is that at that point, memory speed becomes the bottleneck. So we can't just throw more virtual cores at it and hope it gets faster. No, as Shadow has to switch between these processes a lot, we just exhaust the memory bandwidth to our main memory, and we can't really get faster by having more cores. Finally, I want to point you to another presentation that I held yesterday, where I also present some experiments that I ran with ETH Shadow. So if you want to see what ETH Shadow is capable of in practice, how it can enhance your testing workflow, feel free to scan the QR code. I'm going to leave it on there for a few more moments. And after that, Pop also has something to say.
Yeah, thank you. And actually, the EF research is like looking for a P2P network expert. So if you are interested to apply, you can like go to our EF job website over there. And for the ETH Shadow, you can also pay with ETH Shadow like at Ethereum/ETH Shadow. Yeah, that's it. Thank you.
Yeah, okay. Yeah, simulate 100 nodes on a single laptop, also in a single YAML file. That's pretty cool, right? I like that. Next time you think about simulating Ethereum network, check out, as you see before, GitHub ETH Shadow. Next up, the Q&A. Please scan the QR code, open Meerkat, right? Go to the bottom right. You'll see the live Q&A there. So click in there. You can create and upvote questions here. So we'll go with the first question. Ooh, okay. The first question is, can you scale Shadow horizontally by adding more workers?
I guess the workers mean machine, right? Currently you have to run Shadow inside like a single machine. Theoretically, it's possible that you can run it inside many machines, but it's an open research problem, and we cannot do that now.
Okay. The next question is, what is the difference between ETH Shadow and kurtosis?
I think kurtosis is like a Docker compose, right? And like you have to like when you run many nodes inside a single machine, it will compete, like it will share the CPU. And if you run too many nodes, it will like, yeah, it will be like too slow, and like the simulation will be like inaccurate. Like, yeah, I think you can just run like a few, like less than 10 nodes like inside a machine, I guess.
Okay. How do you handle the client's memory and storage requirements when running a lot of them on the same machine?
The storage is not a problem because we don't have like the EL state, so we don't have to have like a lot of storage. But in terms of the memory, yeah, as Daniel talked about it, like we use like a 1 terabyte memory machine to run like 1,000 nodes. Yeah, so you have to have a lot of memory.
If I may add to that, we also start with a fresh genesis state, so with a new DevNet, and nodes running on an basically empty state use way less memory than a mainnet node. So like that, we can, like if you think about it, 1,000 nodes on 1 terabyte is 1 gigabyte per node, which is very, very small, but it's possible because we have this empty state.
Okay. The next question is simulation able to capture some edge case flaw in the protocol?
I'm not sure what edge case means. Like, yeah, I'm not sure like what case, maybe.
Well, yeah, I think it is, because I just mentioned my other presentation. You can also find it in the Devcon schedule. I used it actively to find issues. Well, with the issues with the protocol, it would be also possible to find it there. If Shadow, in my opinion, is more suited for network-related things, because yeah, it really puts its focus on the network layer. But it's possible that you can configure some attackers that find some edge case in the protocol through their attack, for example. Yeah.
Oh.
Go ahead.
No, next
okay. So
yeah.
the next question is, does East Shadow support logging capture?
Yeah, I would like to answer this question so much that I think this is an important thing that I didn't mention in the presentation. Like, yeah, you can see every STD out like of every node, every process, and like you can also see like STD out, STD error, and you can see every file that the clients produce like in every node. Yeah, that's quite cool.
Okay, cool. We have 1 more minute for Q&A, so please keep the questions flowing in. The next question is, do you support DVT such as SSV or OBOL, I guess? And what about eigenlayer AVS?
Not yet. I mean, theoretically, you could configure it kind of yourself. However, it's likely that those clients also won't work within Shadow without some added work in Shadow. Yeah.
Okay, 30 seconds. Is it complicated to add other clients?
Yes. That's why we hope that we can like get the core developer community interested in this, because it's a lot of work, especially in Shadow. So, for example, Teku support Anton Nashaturev from Consensus helped us a lot with this. If you are interested in adding your client or some other piece of software to ETH Shadow, approach us. We'll try to get you started.
All right. So unfortunately, time is up. There's a lot of upvotes there. So one more question then. How do you define the simulation to run? Just submit the list of transactions to a network?
If you want to send a list of transactions, you can do that. You can just spin up a special node and then run the software to submit the transaction to some node, and the transaction will be included on chain and everything, and you can look at everything. Yeah.
All right. So unfortunately, time is up. I think Daniel and Pop will be hanging around. So if you have more questions, feel free to reach out to them, probably down the stage. For this session, thank you so much, Daniel. Thank you so much, Pop, for the session.
Yeah, thank you so much.
Yeah.
Thanks.
So next up, we have gas limit and block execution, and the talk will start at 1:40 p.m. So see you again very soon. Thank you. Right, and then on to our next session. Gas limit has always been a hot and contentious topic for so many years, right? Do we increase the gas limit and push out the smaller validators that are unable to keep up with the hardware specs and backtracking Ethereum decentralization? What are the challenges around raising the gas limit? Today, we are happy to have Marek with us here, and he'll be speaking about gas limit and block execution. Please welcome Marek.
Test. Okay. Hi, I'm Marek, Ethereum card developer from Nethermind team. Today I'm going to focus on gas limit and block execution. There are some voices saying that we've either given up on L1 execution or we need to move Ethereum to data centers and eliminate solo stakers to make Ethereum successful. I disagree with all of these statements. I don't want to focus here on suggesting a specific gas limit value. Instead, I want to show that there is a significant untapped potential on execution layer, and this potential will have to be unleashed on some point of time. At the same time, I will point out areas where we need to be careful considering increasing gas limit, and I will mention challenges and potential solutions. All right, let's begin. So in 2021, Elon Musk was interested in cryptocurrency and claimed to know how to scale blockchains. He mentioned that he discussed with Dogecoin devs to increase block sizes by 10x and decrease slot time by 10x, which would supposedly scale Dogecoin by 100x. Sounds easy, right? Just change one or two variable and we are done. So can we do the same for Ethereum? Increase gas limit 10x and reduce slot time 10x? Yes, we can, but of course it's not that simple. Gas limit is a powerful variable. Increasing it leads to more transactions, more applications, generally greater crypto adoption. However, it has to be adjusted carefully because it might impact decentralization and security. So there are a few areas when we need to consider when increasing gas limit. Disk usage, this stems from two things, history grow and state grow. History grows much faster than state. However, there is a straightforward path to remove it with EIP for force. With the current gas limit, state doesn't seem to be a significant concern. However, we need to observe it closely with potential increases. Networking, so larger blocks are more challenging to propagate and allow for more transactions, so potentially it will increase load on mempool. Other things, so increasing gas limit affects syncing time, RPC, proof sizes for the future light clients, size of archive nodes. However, today I want to focus on block execution a little bit with isolation from other topics. Block execution is the main contributor to other hardware requirements such as CPU or disk speed. Okay, but first of all, who control gas limit? So validators, of course, can vote for the desired gas limit. However, the block gas limit cannot increase or decrease by more than 1/1024 of its parent block gas limit. So whenever you propose a block, you can move Ethereum in your desired direction. In other words, if you think that 35 million is the correct gas limit for Ethereum, you can set this value in the config, and in every block, you will move slightly in this direction. However, other validators can counteract it, bringing it back to 30 million. And this fact was used in EIP proposed by Giulio from Erigon team. He suggested modifying clients in the way that there is very small increase in every block. Thanks to that, we have a better control what's going on in the network with increases. So the control over gas limit can be divided into categories: local block building and external block building. Approximately 9% of validators are local builders. In this case, execution client teams can set their default gas limit in the config, which can be overridden by node operator. Most of the blocks are externally produced, and around 91%. And in this case, consensus client teams can set the default gas limit, which can be overridden by validators. However, this is not enforced. So builders should follow this, but they do not have to. So we can say that builders have the final control over this value. So I have seen a Twitter conversation about increasing gas limit and that we should increase hardware requirements, or we should make EVM much faster and parallel and scale one in this way. Of course, we should try to optimize things as much as possible. There are many reasons to do so. Future potential of L1, L2s, RPCs. However, let's analyze the block execution performance on my mini computer Intel NUC 11. So as you can see on the charts, this device can execute blocks with the average speed around 330 megagas per second, and blocks are being validated in just 50 milliseconds on average. So if we consider higher hardware requirements, let's take a look at much more expensive machine, 4 times more expensive, used by one of my colleagues. And as you can see, blocks are being executed almost 3 times faster with the average speed 950 megagas per second, and execution time is around 17 milliseconds. So at first glance, the discussion about hardware requirements seems relevant. Mini computers are 3 times slower than the high-end consumer machine. And there are many machines in between that could be considered. However, let's pause for a moment. Ethereum slot time is 12 seconds, and we are talking about average execution in just 50 milliseconds. So what's the point of using much higher hardware when we are not utilizing slower machines? So this suggests huge potential for mainnet. And however, we know that if everything would be that easy, we would already have much higher gas limit. Earlier, I mentioned that I'm talking about block execution a little bit as isolation from other topics. And those other things are more concerning, like state growth, history growth, networking aspects. However, even in block execution, there are challenges. First of all, if we have 12-second slot time, it doesn't mean that we have 12 seconds for execution. This is an obvious thing. And even if we ignore networking aspect entirely, nodes need to be able to catch up with the tip of the chain. What's more, RPC providers must be able to process new blocks while processing heavy if calls and other requests. And lastly, there is a consensus mechanism. So let's take a look at the diagram on the slide. Ethereum consensus requires strict timing for block execution. The attestation deadline is 4 seconds. However, ELs have much less time to process new blocks. First of all, there is lightweight validation on CL side, and blocks need to be propagated across the network. Moreover, blocks often aren't revealed at the beginning of the slot due to timing games. And the solution to this is to reorganize Ethereum slots in such a way to allow for more time for execution, with 2 solutions under consideration: EPBS, enshrined proposer builder separation, and APS, attester proposer separation. While the main goal of those changes is related to block building and MEV space, there is additional nice benefit on the execution side that we will have much more time for execution. I will use EPBS as a primary example. However, both solutions will reorganize the slot in more optimal way. So in EPBS, attestation deadline is set at 3rd second. However, attesters will have even up to 11 seconds to execute blocks without affecting consensus rules. So this is very useful in context of worst cases. Okay, other thing that we should consider is, of course, state grow. So with the current gas limit, state doesn't grow rapidly. In the last 3 months, it has increased 4 gigabytes in Nethermind database. If you want to read more about state grow, there is an excellent research from the Rev team. However, the worst cases of most of the operations is essentially function of block size. So the bigger the block, the more operations you can fit in. However, in case of state, we need to be mindful of state database as well. So in other words, the bigger the tree gets, the slower state access may become. So clients spend a lot of time trying to optimizing things related to state. So here is example from Nethermind, and operations are dominated by sload and ssstore. Another example from Bezu, and similar situation. And Rev seems to be occupied by state root calculation. And other thing related to state is that we know that we will eventually need to transition to another tree, either Verkle or something post-quantum secure if there is sudden breakthrough in research. So we know that this transition process will be complex, and it will be easier with a smaller tree. So we need to be careful to not make this task too difficult with increasing gas limit too aggressively. However, everything needs to be put in context of data, and as Julia from Oregon team has shown, even if we double gas limit and ship Verkle in 4 years, the transition will take additional 13 days, which doesn't sound like a very bad solution. Long-term solution for Verkles is, of course, state expiry, and recently Vitalik wrote the blog post about it. Block execution is strictly related to gas pricing. Gas pricing represents the time it takes to execute the blocks and other resources required to do so. So we need to take into account state contribution to state grow and history grow. And recently, Vitalik proposed that we should increase gas prices for hashing function, as blocks that are heavy with hashing are harder to prove than average blocks. So we benchmark different operations, and you can see it on the table on the slide. We filled the block entirely with one of the operations, and as you can see, the differences in gas pricing can be substantial. For example, if we fill the block with RIPMD precompile, it executes with the speed 1 gigagas on very slow machine. If we do the same with simple if transfers, the speed is around 700 megagas per second. However, other operations can be even slower. EC recover, 80 megagas per second. Point evaluation precompile, 65 megagas per second. So this is important because the slowest operation should be treated as a bottleneck for increasing throughput rather than relying solely on average execution. So let's talk more about worst cases. Client teams are improving and being better and better on executing average transactions. However, Ethereum security must account not just for average case, but for worst cases as well. And by worst cases, I mean situation when optimistic parallel EVM encounters as many conflicts as possible, when caches are being missed, when attacker found some slow operations in EVM and crafted the block in the way to disrupt the network. So let's take one more look at execution times of my Intel NAC 11. As you can see, the performance on different blocks can vary significantly. I marked a few spikes with red rectangles. So the average execution is 50 milliseconds, but the maximum is 425 milliseconds. The known worst case in all execution clients that are observed on real networks are mining contracts. So those contracts works in this way that they are doing a lot of storage writes and sets values to 0. And by setting values to 0, they are getting refund. And thanks to that, they can feed the block with excessive state access. So our team member, Ben, proposed an EIP to prevent such situation. EIP 7778, prevent block gas smuggling. So slow blocks can affect consensus. If attesters won't be able to meet attestation deadline, it might impact, they will miss attestation, and it will impact chain health. What else? Slow blocks can affect block production, so the timeout may occur, and it might impact aliveness of the chain. And of course, the slower the operation, the more probability for DDoS vulnerabilities. And I'm not saying that we have an immediate concern here. We need to analyze our worst cases. We need to understand them. We need to optimize them. We need to reprise operation that could be a bottleneck for increasing throughput. The long-term solution for gas pricing issue could be a Vitalik proposal for multidimensional gas pricing. All these challenges are important, but there is other side of gas limit. Gas limit hasn't been increased for a long time. The last increase was done in April 2021 from 12.5 to 15 million. The increase from 15 to 30 was related to introduction of base fee mechanism. So while gas limit is higher, the gas target is still the same. In the last 3 years, hardware improved. So it could be an argument to increase gas limit. However, even stronger argument is that Ethereum client software improved massively. So to summarize, taking disk space aside, which will be solved with EIP for Force, I don't think that the discussion about hardware requirements is relevant. Ethereum can be run on mini computers, and it will stay in this way even if we increase gas limit a little bit. I see challenges. We cannot forget about state grow, about history grow. We need to reorganize the slot. We need to migrate to another tree. However, all of them seem to be solvable and are planned for in Ethereum roadmap. We need to ask ourselves what data we need, what other problems we need to solve, what the correct gas limit should be. I don't think that we given up on L1 execution, and execution is not a bottleneck for scaling L1. Of course, I agree strongly with Vitalik's vision that Ethereum mainnet should be a strong base layer, and definitely it shouldn't take hyperscaling approach or make any shortcuts. All the improvements in the clients and in protocol as well will benefit L2s, allowing them to take hyperscaling approach and use the full potential of EVM, while Ethereum L1 should stay to be a strong, secure, and decentralized base layer. And that's all I want to say. Thank you, everyone.
Okay, thank you, Marek, for a great summary of all the factors that can affect gas limit increase. So we have extra time. Let's go through the first question. Please scan the QR code here. Go to the bottom right. You'll see the live Q&A button there. Click there. You can add questions. You can upvote. We'll go by the most upvote first. First question, what do you think about REST saying they are fastest? Is this relevant?
That's a tough question. So actually, I discussed it with Georgios yesterday, and he got the same question on his presentation. And he said that actually Nethermind is the fastest now, and they are kicking our asses, so we need to work harder. And yeah, that is my comment about this. I hope it make sense.
I run Nethermind on my validator. Will parallel EVM ever become relevant for L1 nodes?
I think so, but I think it will take time. So if we have multidimensional gas pricing that controls state growth, we could allow for more execution with parallel EVM. What's more, parallel EVM might be important if we cap the transaction, so we will allow, for example, only 30 million gas transaction, and then worst cases are better, basically. So yeah, I think maybe on some point of time.
Okay, the next question is, what's your opinion on pipeline state roots being calculated with 1 block delay?
I think it makes sense, but I'm not sure if for L1. For L2s, yes, but for L1, I'm not sure about consequences for light clients.
Next question is, what tooling does Nethermind use to measure and benchmark mega gas per second on a node if the node is not in sync with the chain?
So if the node is not in sync with the chain, I'm not sure about this, but generally Nethermind uses the tooling that monitors new payloads. So we measure the time it takes to execute new payload in Nethermind, and once we have time and we know how much gas was used in this block, we can calculate the speed.
Maybe you can use ETH shadow for that. I'm not sure. Next question would be, why gas per second if each operation have different gas use? Did you think opcode per second makes more sense?
Why gas per second if each operation? No, I think there is a problem with gas pricing. So ideally, gas pricing should represent the correct resource usage, but we have, as I shown in this presentation, we have operation that doesn't follow that. So yes, I think we should still use mega gas per second, but we should maybe improve our gas pricing in EVM.
Cool. We have about 3 more minutes, so if you guys have more questions, please feel free to submit. But the last question we have here is, what do you think about increasing time spent on signature aggregation to allow faster finality instead of gas limit increase?
I don't know. Sorry for not answering this question. Signature aggregation. I have no opinion.
Cool. We have 2 more minutes left. Any other questions? Please submit to Meerkat. Going once, going twice, and all right. So, oh, okay. Okay. Do you want to answer that question? Maybe not. No.
Let's skip that.
Yeah. Okay. So if no more questions, thank you so much, Marek. Thank you so much for everyone for listening, and see you next session. Next session will be how long non-finality could kill Ethereum. It will start at 2:10 p.m. See you again. Okay, now on to the next topic. Today, Ethereum finalizes in 2 epochs, so that's roughly 13 minutes. Not ideal for many critical use cases in the near future. We have had a couple of non-finalities before, and we prevailed, but will we always prevail? We are glad to have Devcon here to talk about how long a non-finality could kill Ethereum. Everyone, please welcome Devcon.
Hello, hello, and thank you. Let me drop the water. So hello, everyone. I'm Devcon, Ethereum core dev at Consensus at Sigma Prime. And today I'm going to talk about how long finality could kill Ethereum, or some healthy dose of fear-mongering to get all the core devs here to care a little bit more about this issue. So just to start, let's get everyone on the same page. This talk is not labeled as an expert, so we'll start with what the hell is finality. So Ethereum has a strong crypto-economical guarantee where if a block is finalized, it will not get reverted unless 2/3 of the stake, so an insane amount of money, gets destroyed. For the purpose of today, what you have to know is when we finalize something, everything that descends from it is a possible block or state. Everything else we don't care about. So when the network fails to reach finality, in other words, 2/3 of the chain agree on something, then this section of blocks and states just keeps growing because the finalized checkpoint doesn't get updated and it just keeps going in the past and in the past. So today we're going to run through an experiment. I'm going to show a hypothetical failure mode of the Bitcoin chain on non-finality, and we'll talk on all these possible concepts and how they tie together into something that could actually kill Ethereum. So let's start with some finalized checkpoint, and here some descendant block A. But this is a longer chain. I'm just representing here shortly for succinctness. Next, oops, some client has a bug with more than 1/3 of the state, say like a consensus issue where they reject a block that they shouldn't. And this causes a chain split. So the faulty client cannot produce on top of A, so it just goes on its own fork and mines B prime, X prime, so on and so on. Everyone else stays on the majority fork, so B and X. And with these 3 dots, I'm representing a long chain. If we're talking about 1 day of non-finality, this could be 7,200 blocks, so quite a lot. The first thing that happens is most clients spend, not significantly, but a decent amount more this space during non-finality, as the amount of blocks and states that they have to keep for fast access is higher. Then, now it's when things get interested. Let's assume that one of the faulty clients, for some reason, be another bug, or some network problem, they lose out of sync or they crash. And they think that B prime is the head. They will act on it and produce this block, X prime prime, which forks from B prime. This block is very expensive to process, and we'll show now why. And everyone else must process, everyone in the fork X prime and everyone in the fork X. So these blocks are expensive because in Ethereum, states are not only dependent on the parent, but also on time. When you want to process block X prime, you have to load the state at B prime and perform something that's called a state advance. You have to run this code, which is relatively expensive and increases linearly with state size, a lot of times. So in this case, if it's 1 day of non-finality, you have to do this 225 times plus hashing. So I don't know the numbers, but we are talking a few minutes, potentially. And we can have many of these blocks, and these blocks are very expensive, and what they can cause is that now some nodes get overwhelmed. They trigger resource exhaustion. So let's consider now one of the non-faulty nodes at X. They have to ingest these expensive blocks, and now they also fall out of sync. So they start to produce these annoying blocks that, again, are expensive to process. And here you can start to see how things spiral out of control. Now that we have a decent amount of forking, this space really shoots up. Because again, we are extending the space of possible blocks and states, not only in the dimension of time, but also in the dimension of forking. And now clients can start, again, depending on the client and how they run, to run out of space. if a client has no space, it stalls, it cannot progress, it needs manual intervention. So because of that, let's consider one of these forks now doesn't have enough participation because clients are losing disk and going out of sync. Then you have reorgs, which are expensive. And another interesting failure mode is that some ELs cannot handle reorgs past a certain depth. If that happens, they stall because they don't have enough state to process the chain. So more clients going offline, yada, 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 yada. Also, other things to consider, clients could crash with OM depending on how their state cache on memory works. And again, triggering sync issues. So in these accidental failure modes, any sort of bug can spiral out of control as it causes resource exhaustion, which causes faulty blocks, which causes resource exhaustion, and so on. And this behavior is quadratic with time to finality. Like the longer finality goes on, the more expensive these operations can become. But that can be triggered by an attacker. All of this so far has been accidental. And accidental failure mode is problematic because it has a lot of stake. But if an attacker wants to exploit this and has significantly less stake, potentially like some 100 keys, it can truly wreak havoc. So the problem, as I was saying, is these very expensive blocks that do a lot of skips. And you can create a lot of objects that exploit this. So for blocks, you need stake. You need to have a valid proposal signature. But you can brute force valid proposal slots. If you have maybe like 100, so like the Crusader, the low-carb Crusader, could easily attack the chain in finality of like 1 day and create about some hundreds of blocks, which again, consider each one takes 1 or 2 minutes to process. You can DOS the network like that. Aggregated attestations also require stake. You have to brute force the aggregator duty. And unaggregated attestations, you don't require stake, as you can just produce an invalid attestation, and it will still force nodes to compute the shuffling. The good news is that we are fixing this last attack vector on Electra, and you will also require stake. So look at some history. We have had some issues with finality in the past. The most relevant one happened in 2023, where we lost finality for about 4 epochs. What happened is something very close to this failure case, where some nodes considered to be synced, and they propose a very expensive, not as expensive as the ones we're talking about, but some attestations that take some time to process. Unfortunately, Prism had some caching issue where it did this work over and over, and it didn't have a well-structured queuing system to protect themselves against clogging. So any relevant work to progress the chain, like blocks and attestations, just didn't happen, and that resulted in the loss of finality. Also, Medalla is the quintessential event of non-finality. I'm not going to talk in detail here, but we can talk it later. Also, Goerli suffered a very brutal death with a bunch of cascading effects. And funny enough, the PRDAS DevNet that we ran recently had a massive reorg of 130,000 blocks that triggered this edge case where none of the ELs could continue because they stalled without state. So yeah, what's worrying about failure modes regarding non-finality is that it's very spirally. Things cause things, and it gets pretty out of hand. So far we have talked about accidental issues that relate to client bugs, network partitions, these sort of things. But the worst case that we should consider is what's the possible longest non-finality that we could see on the Beacon chain? And that's related to this failure case, where say that we have supermajority Geth, they have a consensus issue where they mint infinite ETH. So it's not a fork that we can canonize. In that case, if they finalize the wrong fork, they will be stuck there. So on the correct fork, in this case chain B, we will have to wait for them to leak out. That's going to take a long time. So if Geth is like 70%, we are looking at 32 days. So that's, in my opinion, that's the worst case that we should aim for. And this is realistically something that could happen if, for some reason, Geth gets a significant amount of market share. So what can we do? What can we do? Easy, just don't do bugs. Just don't release clients with bugs, then we don't have non-finality, and easy, not a problem. Now for real, there are no strong mitigations, it's just we need to harden the client. So don't run out of this space, don't run out of memory, don't get exhausted. And third, we're gonna look and explore if we can actually reject some of these useless network objects to protect against the most blatant cases of those. And yeah, all of these solutions, they work on this. It's not actually a trilemma, but it's a trade-off space, where in Ethereum, we work really, really hard to preserve liveness. That's why we have this hybrid consensus mechanism, where the chain goes into this non-finality mode just because we want to preserve liveness. We don't want to be in a situation where node operator intervention is mandatory to recuperate the chain. At the same time, we don't want to die, and we want to process everything in a timely fashion. So the first point, and the most dangerous, is running out of disk space. Here, there are a bunch of easy rules that I think most clients follow. I think Lighthouse is one of the ones that don't follow all of them, but we are working on that. And in Lighthouse, we are now introducing this very interested optimization, which is storing everything as diffs. That's commonly known in consensus folklore as 3 states, and that's going to be rolled out in the next version, but it only affects the freezer database. What we want to do next is apply the same principles, but for unfinalized states. And that's going to be massive, because now every time we want to store a state, instead of spending 200 megs, we can just spend half. And we have really good compute and apply times for a bunch of different diffs. How this is going to look like, we'll have this hierarchical diff structure, where if you want to recuperate, say, the state in red, you load snapshot, and then iteratively load the diff, apply, load, apply. This is very, very efficient in terms of disk space, and as you saw the numbers here, it's actually pretty fast and even faster than replay. The complication with the unfinalized section of the chain is that we have moving finality, which complicates a bit the design. But if we just extend the diffs into some finalized range, keeping at least 1 per layer, the design works. And pruning is not that complicated. For memory, there is not much you can do. You just have to make sure that your state cache doesn't blow up in these circumstances. And again, 3 states, memory helps a lot. And this is already in production in Lighthouse. And the last one, and I think this is the most important, you need to have some strong queuing system where you don't let yourself get exhausted from this garbage that can come from the network. Looking at the Medalla, the mainnet incident that we talked about, if instead of having this queue, you split it into sections, one that has higher priority for things that are useful to you, in this case, let's say the sending of heads, and then everything else gets processed with lower priority, we should be safe in this case. Lighthouse at the moment is working on revamping all our queuing system, and we're going to do something with this, also with fairness, so P0 doesn't exhaust P1. And the last point is, okay, we know that these blocks are really bad. Can we just ignore it? That would be really nice. And unfortunately, no. If we want to preserve liveness, there are a lot of edge cases where if we start to ignore blocks, then the chain could stall. So I think this is the only one I've seen that I like, and it's on Prism in production. This is by POTUS. If you get things that extend something previous to justify it, it's more complex than this, but just to simplify, you can ignore them. And this would have protected Prism from the issue that we saw before. Unfortunately, this is just one of the many failure cases that the chain can have, so it's not like a bulletproof. So, what are the next steps? Well, testing, 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 and testing. The issue with non-finality is that we have to do Pectra, we have to do PRDAS, we have to do so many things that unfortunately dealing with non-finality just goes like priority number 3 or 4. I talked with the Ethereum DevOps team, the Panda Ops, and what we should do is have some cyclic tests, either continuously or maybe like quarterly, where we test non-finality. We want to uncover these bugs ahead of time and not when finality dies either in an important devnet or mainnet. Also, in Sigma Prime, we have a tool that we have been using with great success in this source of attack nets, and it's insanely good at killing networks. So we are, with Michael, in the process of revamping this tool, and we'll definitely use it in these tests. So, yeah. But yeah, I mean, just to not be too fear-mongering here, the Beacon chain has been exceptionally stable through its lifetime. And the only time it lost finality was for 4 epochs, which is nothing. We have a robust set of operators who are very diligent, hands-on. The same for core devs. We have triage and fixed issues really quickly. So again, we have to work on this. It's my mission as a core dev to make sure that Ethereum never loses liveness. But yeah, we've been doing great so far, and we should be proud of it. Thank you.
All right, thank you so much, DapLion. So Q&A session, there's QR there on the right. Please scan it, go to the bottom right, and then click on live Q&A, right? And you'll get to the Meerkat Q&A platform. A lot of questions. Okay. First one, assume there is a network partition and multiple long non-finalized chains are produced. What would happen when the partitions heal?
So when the partitions heal, hopefully we finalize. That's the hope. And then everything gets pruned during the finalization routine. Otherwise, yeah, I think that's basically what healing means, I guess, in this context.
The second one, okay. Second one, will single slot finality solve all the mentioned issues, or something will remain?
That would be epic, but no. No, it's going to be the same and probably worse, because now we will get used to have one slot in the node, and then suddenly when we don't finalize, we go back to like 3 weeks. So I think it's going to make it worse if we're not smart about it.
Okay. Next question, why are full nodes forced to keep considering the forks? Can't they know after a few blocks when a fork doesn't have enough participation and prune this?
No. So this is what we call a heuristic. A heuristic is usually you pulling this and putting your finger in the air. Unless you can do a consensus proof that this is safe, you should not do it, because anytime we try to do clever things like this, someone comes along and shows us how in some specific network conditions, ignoring some fork could let nodes to get stuck in some random chain, and then you have a permanent partition that requires manual intervention, and that's exactly what we don't want for liveness.
Okay. Next question, what is your opinion on increasing the non-finality threshold from 67% to, for example, 80%?
That's an interesting point. I've seen some literature about it, and I don't think it's a bad idea. It has its own pros and cons, and I don't think it would affect everything we talk about here directly. Because as you can see here, on the happy case, the network is really stable. So we have 99-point-something% participation continuously. Anytime it drops, it's because of some bug. So we would definitely be more sensitive. But if I recall, like having higher thresholds have benefits. But sorry, it's not on top of my mind now.
Since it happens rarely, how do you feel the loss of finality can be predictable? If it is not that predictable, why do we need to worry about any exploitation from attackers?
Right. So one of the attacks I described today is an attacker exploiting an existing episode of non-finality. So when you don't have finality for a long time, these DOS attacks are insanely more powerful. So it doesn't make too much sense from the attacker point of view, but you can think about it. You have a bot that's ready to kill the network when you have non-finality. Then you just wait, and whenever a client has a bug and you have non-finality, then this exploiter just goes on a rampage and destroys.
Quick reminder that we have plenty of time for Q&A, so if you have more questions, feel free to submit to Meerkat. Next question, do you know any of coordinated or network level fuzzing effort against clients to ensure predictable resource consumption?
Yeah, so there's a lot of fuzzing going on, but I'm not sure if it's targeting these failure modes specifically. I think having a sustained network that tests non-finality specifically, and then we just run tools on it, it's going to be much more effective than trying to set up fuzzing. Like it's so complicated, and you need an actual network to test these things.
Okay. Next question, can an incentive layer ever be implemented to help balance the client diversity?
Unfortunately, no, because there is no way to reliably know which implementation you're running. And if we put money on the line, people will exploit whatever measuring system we have. So I think the best is to have something that's done on top with some subjective criteria. In my opinion, the most successful program so far has been the one from Lodestar, where they incentivized running Lodestar, but they have some off-chain system to predict if you were actually running Lodestar or not. And I think they were using Blockprint and some other algorithm that tries to qualify if a block is Lodestar or not. But if anything that you want to do on chain has to be like perfectly mathematic, and it could be, yeah, we don't have a way to do that.
Does ePBS help?
I don't think so. No, definitely not. Non-finality is independent of ePBS.
What are the odds of another non-finality event in the next year?
I don't know. No idea. Hopefully low. That's a hope.
Why is fork expensive with respect to loading the forked blocks?
Yeah, so when you are connected to a network P2P, you can get any sort of block, any sort of attestation that builds on anything that's not finalized. So as we were showing before, if you want to process a block, you need to recover its pre-state. So you need to have that pre-state available somehow. One option you could have is have absolutely no cache whatsoever. You just keep the finalized state and all blocks. So whenever you get a new block, you just go, oh, this is the finalized state, and then replay potentially thousands of blocks until you get the state. That's a valid approach, but that would be very expensive from a point of view of CPU time, and it could potentially like exhaust the resources of your node. So you want to have some strategy to make that faster. For forks specifically, there is nothing that makes them more costly. It all depends on how you structure your cache between memory and disk, and these trade-offs, like what states do you keep and how much CPU time are you willing to spend to recover a specific state.
Right, next question. Given a long network partition, what if it's long enough for inactivity leaks to make both partitions finalized independently?
Then we're fucked. Yeah. Hopefully that never happens. In that case, everyone that finalized one of the chains, they can no longer go back to the other one. So yeah, they will leak out from that one forever.
That takes quite a long time to do that. How would Ethereum behave during long global network distributions? I guess disturb, yeah.
Disturbance, okay. The most dangerous one are partitions. That's what's a true problem. Because a partition would look like the case that we talked at the beginning, where one block divides the network into A and B. If a partition goes on for too long, you can have what happened in the previous question, that each partition finalizes different things, and then we are fucked. So, yeah, network partitions are really dangerous, but the P2P layer is pretty robust. So I think they should be unlikely to happen. Why that lion? So as you can see, I'm a lion, and the lion name was taken, so I had to put something at front, and why not apps?
If non-finality is more expensive than normal operation, how do we ensure validators have enough resources to handle non-finality?
Why lion? Isn't it enough descriptive? So if non-finality is more expensive than normal operations, how do we ensure that validators have enough resource to handle non-finality? The point of this talk is that we don't. That's why I'm here shouting in the void. We don't really know. So the best we can do, again, is do tests. We should test realistic networks that have sufficient size and long enough non-finality, and then make sure that they can handle. And it's not only about like resource exhaustion and how they are provisioned enough for that case, is can they handle non-finality plus attacks? And what type of attacks? So it's not that clear-cut. We just want to be in a position where in most realistic attacks, some section of the network will survive, and then we should be fine.
All right. Please give a hand of applause to that lion.
Thank you.
Yeah. Next session will be at 2:40. The title is Fork Choice and Forced Inclusion List by Julian Marr. Right. Next up, negative externalities to Ethereum block production are increasingly a threat to the Ethereum network, especially with the increasingly centralized block production supply chain. And a potential solution to solve that is inclusion list. Today, we have Thomas Thierry from Robust Incentive Group at the Ethereum Foundation to talk about fork choice enforced inclusion list. Everyone, please welcome Thomas.
Hello, everyone. Today I'm presenting Fossil, which is our inclusionist design that we're proposing to be implemented into Ethereum protocol via ERP 7805. So you may have expected Thomas here, who is the lead on the Fossil project, but unfortunately he couldn't make it. So I'm Julian, I'm one of his teammates at the Robust Incentives Group at the Ethereum Foundation, and I'll be presenting our joint work with Thomas as the lead, Francesco, me, Barnabe, Terence, who is here as well, Jacob, and Jihoon. So first of all, I'll give a bit of a high-level introduction to what are inclusion lists and what are we actually trying to achieve here. So the inclusion list design philosophy is that Ethereum has access to centralized agents and decentralized agents, and we want the decentralized agents to have some inputs into centralized block construction. So inclusion lists really leverage the decentralization in the validator set that we've gotten from proposer-builder separation, and it's the first design of its kind to do so. And having inclusion lists is necessary to obtain the core property of Ethereum, which is to provide chain neutrality. Chain neutrality we define here as any valid and pending transaction that pays the prevailing base fee is included within the block unless there is no space anymore. So the basic idea of inclusion list is that there are some lists of transactions that constrains how a block is created. And usually you would say that this list of transactions must be included in the block in some way. Fossil doesn't change this basic idea. It's more about who creates the list and how is the list enforced. So what is Fossil? Fossil is fork choice enforced inclusion list. So the fork choice enforced part says something about how it's enforced, and Fossil allows multiple validators to provide inputs into block construction, achieving this core property of increasing the credible neutrality. So here you can think about censorship resistance, whether this is for transactions that are being censored because of regulatory reasons, for economic reasons, or by chance, as happens today. And then there are some other design goals, which is robustness of the system. We want Fossil to be used, and we want it to be only used to provide these, this increase in credible neutrality. And another design goal is extendability. So we want Fossil to be very future compatible, yet we need inclusionists today, since block construction is so centralized. So Fossil is a recurring architecture that we see in multiple designs that we're considering for other use cases like pure DAS or other economic benefits. So now I'll go over on a more specific level how Fossil actually works and how these inclusion lists are created, distributed, and enforced. And later we'll do a bit of a recap again. So I said that Fossil allows multiple validators to provide some inputs into block construction. In this EIP specifically, we're saying that there are 16 validators that are randomly selected every slot to become inclusion list committee members. And what these committee members do is they each propose a single inclusion list by themselves, and these are then later aggregated into one complete one. So committee members, they observe the mempool and see transactions in whatever way that they see them, and they construct their local inclusion list, which is a list of transactions that they sign over, which is then distributed. And each inclusion list is at most 8 kilobytes, which should be around 20 transactions on average. So 20 times 16 gives you 320 average transactions over all of the Fossil inclusion lists. And a block on average has about 200 transactions. So we allow Fossil to be used as like a block template. All transactions in principle could be included via Fossil. With some extra overlap, because these agents might, the inclusionist committee members might not be coordinated agents, so they may choose similar transactions, so there needs to be some overlap. So now that these agents make their own inclusion lists, these inclusion lists have to be created, and they need to go to the proposer, who needs to include them, and the attesters who enforce them via the fork choice. So first we'll look at how these inclusion lists are distributed to the proposer. Each IL committee member distributes their inclusion list over the global topic. This is the peer-to-peer part of the network where all participants listen to. Attesters who enforce the inclusion list, which we'll see in a bit, freeze their view of the available local inclusion list at second 9. So what they do is all inclusion lists that they had seen before second 9, they will enforce. And inclusion lists that come in later, they do not enforce, but they still propagate them to the block producer. And this is essential because this time difference is there to prevent split view attacks. A split view attack is when an inclusionist committee member is trying to split the view of the block producer and the attester. So the person who has to act on it and those who have to enforce it. You could imagine that if the attesters think that there are more inclusionists than the proposer, then the proposer can't adhere to the rules of the inclusion list because it simply doesn't know what's available. So we give the block producer 3 more seconds to act on it to prevent the split view. So if the block producer doesn't have inclusionist at second 9, the attesters can still propagate it to the block producer. The block also doesn't have to be entirely rebuilt. Inclusionist transactions can be appended to the block, meaning that it can be done fairly quickly. So then on to enforcement. So I've hinted at this already a bit, and it's in the name, of course, enforced via the fork choice. The attesters enforce whether the proposer did indeed adhere to the inclusion list conditions that were specified. So the attesters only vote for the block if the inclusion lists were indeed adhered. And how it works specifically is the attesters have been listening to the global topic where the inclusion lists have been propagated, and they freeze their view at second 9 of the inclusion list that they're going to enforce, and they take the union of all transactions that they had seen in these inclusion lists and check whether any of these transactions was not included in the execution payload that they received. So they check whether a transaction from the inclusion list was not in the block. If this is the case, they check if the block is full or not. So if the block is full, then obviously you can't include the transactions anymore. So if the tester is happy, so the block contains all of the transactions or the block is full, then the attester votes for the block. If the attester is unhappy, so the inclusion list has more transactions and the execution payload misses a view, then the attester does not vote for the block. So the property that we're getting at here is if the block producer does not adhere to the inclusion list, its block will not become canonical because attesters enforce it. So this is the full fossil mechanism. We have 16 validators randomly chosen that make inclusion lists. They propagate them. The block producer receives them. It includes all transactions in its block. And the attesters then enforce that the block producer did in fact do this. So the core property that we're trying to get at here is the censorship resistance property. And the idea is that if there's only one honest inclusionist committee member in the committee, it can include the transactions that are most likely to be censored by the block producer and include them in its inclusion list, meaning that the block producer has to include them in the block. If we have a network observation that there's a conservative estimate of 6% of solo stakers, then there's a 63% chance that in this single slot there's at least one inclusion list committee member who's a solo staker. But again, inclusion lists are not only about regulatory censorship, they're very much about economic censorship. There's been some observations of builders strategically underfilling their blocks, perhaps because they want them to be lighter in terms of the bandwidth that they consume, or maybe perhaps because they play some games, or they simply haven't seen some transactions. So inclusion lists are here for all of those sorts of transactions. The idea is that we're boosting the signal that solo stakers provide while not relying on economic incentives here because they complicate the mechanism and it adds a lot of protocol complexity. So now I'll go on to show how Fossil is designed to be as robust as possible. And robustness here refers to robustness against consensus types of attacks, like the split view attack and equivocation. And it also refers to execution layer types of attacks. So people using Fossil for other reasons than for censorship resistance, but for example, as a vehicle to extract maximum extractable value, MEV. So first, the consensus layer attacks. We've talked a little bit about the split view, but in fact, there are two split view attacks to consider. First of all, there's the split view that inclusionist committee members ensure that the block producer would have a worse view of the available inclusion list than the attesters, and this is bad, because then the block producer can't produce a block that becomes canonical. So we prevent this by giving the block producer 3 extra seconds in which the attesters have already frozen their view. And then secondly, there's a split view attack that's related to IL equivocation. So you could imagine a committee member signing 2 inclusion lists and sending one to the block producer and one to the attester set if it would have control over that. And how we prevent any bad things from happening here is we say that if there are 2 inclusion lists, so if an attester or a block producer receives 2 inclusion lists from the same committee member, then they do not impact how the block is constrained at all. So what this means is that if a block producer receives 2 inclusion lists, it doesn't know how to act. Now it knows, okay, I do not have to adhere to this. This is a weird case. It should not be happening. And the testers also know this. So they don't enforce inclusion lists where there are 2. Testers have 4 seconds after the block is produced to receive these inclusion lists. So here again, we prevent the split view. Not enforcing any inclusion list when 2 are sent is a deliberate decision, because this should only happen either if the node is configured incorrectly or if it's an attack. And realistically, it has the same impact as someone sending no inclusion list. So if you said no inclusion list is enforced. If you send 2, also no is enforced. And the other inclusion lists from the other committee members are still enforced, of course. So then there's transaction invalidation. So transactions in the inclusion list may be invalid at the time that the inclusion list committee member propagated them towards that the block producer must include them. There are 2 reasons for this. Potentially, the inclusion list committee member doesn't know the right head of the chain, so it's building on some other head. And the second reason is that the block producer could include transactions before the transactions from the inclusion list. So the inclusion list committee member cannot possibly know what the block producer is going to do since it acts before, so transactions could be invalid. To prevent free data availability, which is a problem that arose with a previous inclusion list EIP, testers only check where the transaction could have been validly appended to the execution payload. So if a transaction is invalid, then clearly it cannot be validly appended, similar to how if a block is full, a transaction cannot be validly appended because it would raise the gas limit over the maximum. And inclusion lists are never written on chain. It's only the execution payload that's written on chain. So this prevents free data availability as well. Then if there can be invalid transactions in the inclusion list, this may lead to some games that you might think of. So it could be that someone knows that it will make the block at second 12, and it tries to flood the mempool with transactions that it will invalidate in its block later on, meaning that it floods the inclusion list with transactions that will be invalidated, therefore not really constraining its block too much. So first of all, this is a difficult attack to pull off in practice, because usually the MEV boost builders only know that they're the builder close to the 12-second line, or maybe even past that. But we have like a defense and debt strategy here to prevent this. So how we do it is inclusion list proposers are free to choose whatever inclusion rule that they like. So they're free to construct their inclusion list however they like, and clients can be an agent for them. So potentially one client prefers the way of creating inclusion lists by priority fee. Others may prefer to make inclusion lists based on how long transactions have been pending in the mempool. And others might use some sort of heuristic that they think is most valuable to create inclusion lists. If people create inclusion lists in various different ways, it's more difficult to attack them. So if, for example, one client includes an inclusion list mechanism that says, I want to make my list based on how long transactions have been in a mempool, just ordered, you'd need to flood the mempool long before your slot, making it potentially a lot harder to know that you can invalidate them. So this is really a defense and debt strategy. It's unlikely that this will happen. The gain is quite limited, but even then, we're trying to prevent it. So then you could think of commitment attacks. So an inclusion list is some way to constrain the value that a block producer could extract. So an inclusion list committee member could say, if you pay me, then I include something in this block. Or if you don't pay me, or sorry, if you pay me, then I exclude something from my inclusion list. So the latter is an extortion attack, the first is an inclusion attack. And this is mainly a worry if there's only one committee member. We try to prevent this by having multiple committee members, making it economically less important, and second, less likely. So then, taking commitment attacks to the extreme, you could think of Fossil as a vehicle for MEV, but we try to prove that this is incorrect. We do this via a concept that we call uncrowdability. So the inclusion list cannot be crowded out by other users than simply providing this censorship resistance property. So we don't want inclusion list proposers to sell their rights to make inclusion lists. We argue that Fossil is robust against these sorts of MEV boost-like markets that you might think arise if you would believe that it's valuable to sell inclusion list proposing rights. We say that Fossil is not very useful for this because there are no ordering guarantees. Inclusion list doesn't tell you where in the block your transaction lands. There is no private order flow possible because any inclusion list is publicly propagated over the network in order for it to be enforced. There are multiple inclusionist proposers, which prevent some of the inclusion and extortion attacks that we talked about briefly. And the inclusionists are created 3 seconds before the block producer acts. So the block producer has more information about the external states of the world than those who make the inclusionist have. And this means that no individual inclusionist proposer has the right to include, order, or exclude transactions, which is like the canonical definition of MEV. So Fossil is specifically designed to be as robust as possible against MEV markets for inclusionist proposing rates. Second is extendability. And here we argue that Fossil is a great step in the right direction. We feel that it's very necessary to have some form of inclusionist today, since there are only 2 builders. And we see that Fossil is a recurring architecture in different products that we're trying, I guess not products, ERPs that we're imagining. And so here I'll present 2 possible extensions. You shouldn't take these as part of Fossil, because they're not in the ERP, but they are things that could be built on Fossil without changing the underlying architecture. So first is making some transaction fee mechanism to incentivize censorship resistance. So the design philosophy behind Fossil is to boost the value or boost the signal of those that already provide censorship resistance to Ethereum in a way that doesn't cost them anything, but it doesn't gain them anything either. Potentially, for some use cases, you want these inclusionist committee members to actually gain something from providing this censorship resistance service. And what you could think here is an ERP 1559-like mechanism where the priority fees are given to those who create the inclusion list, potentially subject to how much they contributed to individual transactions being included. The general idea is to make it a lot more expensive to censor transactions. You could do this via this transaction fee mechanism, and you could also change the way that tips work in Ethereum, potentially by having separate tips for inclusion list inclusion and block inclusion, or by having a conditional tip that was popularized by Elijah Fox, Matt Resnick, and MashPy. And then secondly, we're looking at Fossil for blobs. So ERP 7805 currently doesn't support blobs, although it could with some small changes potentially. But taking it a step further and looking at full data availability sampling, enforcing inclusionism becomes a bit more difficult because those who enforce it need to know that all of the data was indeed available. They need to know that the block producer could have included all of these transactions. So then we could extend Fossil with some extra condition where the attesters have a good view of whether the data is available or not to, again, prevent split view types of attacks. The important thing here is that this fully builds upon the architecture that we're proposing within Fossil. So Fossil is very future compatible. Fossil architecture is basis for many more extensions. These are just 2 examples, but you could go crazy with this, and I think it's a very interesting design space. So to summarize, Fossil allows 16 validators to contribute to block construction, which is currently very centralized and mostly in the hands of 2 builders. The main goal is to increase the censorship resistance of Ethereum right now. And the side goals are to provide robustness against consensus layer and execution layer attacks. Consensus layer attacks, again, being the equivocation split view, execution layer attacks being crowded out by MEV types of markets. And the second side goal would be to be very extendable. So we want Fossil to be future compatible and unlock a new field for Ethereum that we cannot imagine now. So the next steps are ERP 7805 is available. If you're interested, please scan the QR code and read through it. We're trying to move towards implementation in clients. And my call to action to you is that please reach out to us if you have any questions about Fossil. If you think that Fossil could be used as a vehicle for MEV, so this is the thing that we're explicitly designing against. And if you think that you'd like to use Fossil on your layer 2 to provide censorship resistance there. So that was it. Thank you very much. And I'll be open to any questions.
Okay. Thank you, and also big apologies for calling out the wrong name. So this is Julian Marr from Robust Incentive Group at the EF. So let's get into the Q&A. Julian, please maybe, feel free. So the first question, the IL committee introduces for the first time a duty for validators that require mempool access. Are there any concerns with this?
Yeah, that's an interesting question. So currently in Ethereum, validators need to have access to the mempool anyway, because sometimes they, in principle from the Ethereum protocol, they are asked to construct blocks. Most of them outsource this via MEV-Boost, but currently validators have access to the mempool. So now we're introducing some way that this is necessary, I guess. Even If there's a very strict reason why you don't want to have access, you could also just propose an empty inclusion list, and then again, we rely on that there is at least one person willing to make an inclusion list. I think this shouldn't be a problem. Validators, if they want, they can run a version of the mempool that's well suited for them. Yeah, so I don't think this should be a big problem.
Next question, how does the validator access the mempool and how does it select transactions?
Yeah, so I'm not sure if this is like more of a dev side of a question or a research question. Coming from the research side, I'll answer it as a research question, I guess. So how does it select transactions? This could be to maximize some objective function that they have for themselves. Maybe they want to include transactions because they think that regulatory censorship is very bad, or maybe they want to include transactions because they don't want people to mess with how their favorite application works or whatever, for economic reasons. In principle, inclusionist committee members are free to construct their inclusion list as they like. And since there are no rewards for this, there's no reason why you wouldn't, for example, order them by priority fee. On the dev side, potentially like catch us later. Terence is here as well. Yeah, I think that will be better to do later.
Right. Next question. Will there be PBS-style marketplace for forming for inclusion lists? It seems to be just another block space consumption design from that perspective.
Yeah, so we're very aware of this, and Fossil is designed explicitly to not foster such a market for outsourcing. Some key observations here are that MevBoost relies on economies of scale. There are high barriers of entry because of private order flow, and the economies of scale come because it's very difficult to construct a very valuable block. And this makes that it's individually rational to outsource my block construction to some MevBoost builder. For Fossil inclusion list, this isn't the case. So constructing inclusion list is very easy because you just select transactions based on some heuristic that you like. They're not that big. I mean, you could include 20 average size transactions, and you don't have any ordering guarantees over this, so you can't run sophisticated algorithms to say what value can I extract from these transactions. You have to commit 3 seconds before the block producer, so doing any arbitrage is basically impossible if it were not already impossible because of the ordering. There's no private order flow because any inclusion list is propagated publicly, otherwise it's not enforced. So this makes it that it's not individually rational to outsource block inclusion list production. I guess the question here is that we're very convinced of this, and we've talked to builders and searchers, and no one has come up with a way to use inclusion list as a vehicle for MEV. If you do find a way, I'd be very interested in trying to contradict that.
Is this proposal compatible with 4-second block times?
So the person who asked this question probably thought no, but I think it's actually very compatible. The interesting thing about inclusion lists is that the timeline doesn't necessarily depend on the block construction timeline. So when inclusion lists are created and propagated, which is the largest part of the timeline, can be completely parallel to block construction. Inclusion lists don't have to depend on the head of the chain. They could be made, for example, in principle, they could be made whenever early, let's say 3 blocks early or something, and then they could still constrain the current block. And since this timeline is very, very easy, as in the block producer must receive them, for which it could have a very long time, and the enforcement is done by the testers, it doesn't add like additional time delays. That being said, if you make them very far in advance, the inclusionist is more likely to hold invalid transactions, which may not contribute much to censorship resistance.
Next question, how about the integration of Fossil with ePBS and single slot finality? They should be aligned coordinately.
So we're proposing Fossil separately from ePBS or single slot finality. I think this is important because I don't see an inherent tension between these. As I explained in the previous answer, the Fossil timeline can be completely parallel from other timelines. So in my view, it's very compatible with both, and they don't have to be implemented at the same time. They're proposed as different proposals.
Does it mean transactions from inclusion lists will always be at the bottom of the block?
So first of all, transactions aren't necessarily from inclusion lists. Transactions in the mempool are seen by inclusion lists and then included in the block, but the block doesn't contain a section that's like, this is for inclusion lists. So some transactions that, I guess you could just see them as transactions in the mempool. Mempool transactions currently usually are not put on the top of block because this is a very valuable spot. Maybe someone can extract some MEV from being at the bottom of the block. So I'd expect them somewhere to be in the middle. There are no ordering or properties of like where in block it should be.
Should equivocating committee members be slashed?
So in our design, we don't slash committee members. We do this because there is no reward scheme. We want to incentivize as much participation as possible. So slashing could be caused because you have a bad node setup and you accidentally sign something twice. You don't want to do this. You want to prevent it. But if it happens, we don't want to penalize for it. Slashing in equivocating on your attestations is important for finality to give some economic weight behind the transactions that land on chain. Slashing for double signing a block already is different. It's not related to finality. But it does cause a bit more stress on the chain. Equivocating with your inclusion list doesn't cause anything. It just means that your inclusion list isn't enforced. It's equivalent to sending no inclusion list. So that's why we don't slash for it.
Right. So unfortunately, we have run out of time again. There are many questions left. I think Julian will be behind down the stage for answering more questions. Thank you so much, Julian, for speaking. So please give a hand of applause to Julian, please. All right, so that concludes my session for MC. So the next session will be at 3:10. It's going to be about staking on power efficient and low cost hardware from ARM64 to RISC-V boards. Thank you.
Hello, hello, good morning. Sorry, it's not good morning. I was trying to say GM, but then I realized it's the afternoon. Hi, I'm so sorry for botching that introduction. We are here now in the afternoon session. So kicking of us today is going to be Avagachi 1 and Harag coming on and talking about staking on power efficient and low cost hardware from ARM64 to RISC-V boards. Before you bring up, I have one last thing to say. There's going to be a QR code that comes on screen. You're going to scan that and ask questions throughout. And at the end of it, that's going to be how we take questions, upvotes, send hearts, stuff like that. So keep that in mind, but I'll let you guys take the stage.
Hello, hello. It's nice to see some friendly faces here. I'm Haurok. I'm a physicist turned software engineer and now full-time in Ethereum, but not associated with any project.
Hello, I'm Avagachi1. I'm a software engineer as well. I'm an Ethereum hobbyist, and for the past few years, I've been trying to make Ethereum work on various and exotic hardware that we'll be talking about. Thank you for being here.
So when we did this presentation, prepared it, we were thinking, okay, there's two kind of audiences here. It's home stakers. They might be interested into power efficient hardware, how to get their setup started. But there's maybe also some software engineers here who are interested in the RISC-V platform. So we will talk about that as well. And how this came about, in last summer, in July, Avagachi made a call, hey, who wants to bring consensus clients and execution clients onto a RISC-V platform? I knew him from before in Discord. I joined him, and since summer we started compiling clients, running them on these platforms, and then we saw that also the Ethereum on ARM team is working on this possibility, so we teamed up with them a bit. So it's Diego and Fernando from the Ethereum on ARM team. There's also Leonardo Arias, he's associated with Flashbots, who was part of it, and then it's the two of us who are independent of any project. So let's get started with ARM boards. Why would anyone want to use ARM boards? Actually, they're quite nice because they're all on one board. So you have the RAM on it, you have everything on it, it's just one simple device. They're low power consumption, and it's a well-balanced hardware if you choose the right one. So it's a good CPU, enough RAM, and you can get running. The problem is it's a steeper learning curve getting Linux to run on them. It's a software support and generally is not on par compared to Intel NUCs or anything like that. And sometimes the availability is a bit difficult, so if a new board comes out, it might be sold out for weeks or even months. Most people think about the Raspberry Pi. It's a nice ARM board. It's good. It's available in almost all the shops. It's cheap and has very good Linux support. The problem is they don't have enough RAM. The CPU is just barely fast enough. And you need an additional board to attach an NVMe SSD. So it's possible to run a node on them, but not the best choice nowadays. The good ones are the ones we use, and also Ethereum on ARM suggests to use. They have all the same RK3588 CPU. They have either 16 or 32 gigabytes of RAM. It's Orange Pi 5 Plus, Nano PCT6, or the ROG 5B. Somewhere between $120 and $220, depending where you get them. Important thing, always buy an official power supply, because the ones you have at home, they most probably won't work, and that's a pain. You'll have to add an SSD, which has the right size, and please also use a Linux specifically made for these boards, like the Ubuntu from Joshua Reeks or Ethereum on ARM. CPU performance-wise, you see a small comparison here. We have Intel and AMD CPUs, which you might have at home at the bottom. Then you have the Orange Pi Plus in the middle, which is about 2 to 3 times lower performance than these high-power ones. The Raspberry Pi 5 is another factor of 2 slower. And the Raspberry Pi 4, yeah, as you can see, we probably shouldn't use that one. I ran a validator on it, a validated node on Ethereum mainnet. Without the validators, we saw the node used about 5 to 8 watt. The CPU usage was about 25% at peaks. And yeah, RAM was about 50% filled, so it was 8 GB was filled. When I directed a few nodes and a few validators to it, power usage was slightly higher, but more or less the same. CPU usage increased to about 40%, and RAM was pretty much the same. Interestingly, when I looked at attestation efficiency over the day which I used it, it was pretty much the same as on my high power node I had before. So you can totally run an Ethereum full node on one of these devices. So with this, I give it over to Abegotchi.
Thank you. So some tips and tricks. First of all, the ARM boards and also the RISC-V boards are fragile. They will always come without a case. You need a case to protect against dust and other unwanted electrical short circuits like your hands. An active cooling, it's always required because the CPU will spike most of the time, and you'll get better performance and actually better power usage, including the small power usage of the actual active fan. So you'll not lose in power performance. Also, an important part is the NVMe. For these small boards, just take the good enough NVMe SSD. Do not go overboard. Always check that the PCI controller is on the exact PCI controller that the NVMe supports. If you buy a, I don't know, a PCI Express version for NVMe and you put it in a PCI Express 2 controller, it's a waste of money. Also note that the PCI Express 4 and 5 are very, let's say, power hungry. They need better cooling. And also note that if you have a 4 terabytes in the future, that also will need better cooling because the chip surface, it's directly proportional, so it's twice. Also, related to overclocking the CPU, it's worth it. But just make sure that most of the time, if you increase the frequency by 5%, you will basically increase your power consumption by a factor of 2, maybe 10%, maybe more. So just make sure that you take that into consideration. Also, an important part, the ARM boards have CPUs that use the big little architecture. So for example, the Orange Pi has 8 cores, but 4 are performance, 4 are low performance / efficiency. So in some cases, you might want to pin the consensus client on the more performant CPUs, because that one will be used more than the execution layer. Day 2 operations. Okay, I have it all running, all installed. What to do next? So it's important to choose a very good distribution like Ubuntu or Debian-based. Also to have a well-maintained staking framework like DAppNode. ETH Docker is my favorite choice because most of the time the base OS that comes from the manufacturer has very low capabilities, low set of libraries. So if you have Docker, you basically borrow everything from the community via Docker. So that's why I'm very fan of ETH Docker. Also, make sure every time that you firewall-proof your system if you have an at-home staking rig, because you might have a public IP without knowing it. So if you actually have a public IP, you need to find out if you have it and firewall it, making sure that it works. Also, I have there are kernel live patching that is very important to sleep well at night. For example, Ubuntu supports it is free for up to 5 machines. Also, VPN for management. WireGuard is a very cool Linux technology. It can create very fast, very efficient peer-to-peer tunnels. Also, Tailscale or OpenVPN is good. If you have enough RAM, monitoring with Docker makes sense. Also, if you have a lot of boards like I have, it's worth to invest in a small UPS. Also, if your electrical grid is failing you, it's worth the investment is worth. So the summary on short. I'm using it also as a solo home validator on ARM64, but I would suggest to start first using them as a fallback node, a normal Ethereum node. You can run multiple testnets on them. It's just a matter of RAM sometimes. And of course, play with hardware before investing in a very big staking rig. It's best for that. Let's go to the RISC-V boards. So RISC-V has quite a, let's say, young history. It was it's a young alternative to x64 ARM64 instruction set. The standards are already in place, and the most important part is that it's free open source. So everything there comes royalty free. It's collaborative, and in theory, it should achieve a way faster innovation rate, which for us means lower prices in the future. Lower prices, better efficiency. So we are somewhere in the middle at the moment. What's hard has been already done with the RISC-V foundation and all the standards that are already in place. And important is that we are at a big effort. So a lot of hardware, software companies need to come together and make it as performant, as efficient, as available as the ARM64 and then the x64. The mainstream usage will come at a stage when you will be able to move any workload from x64 to ARM64. You can almost do it for ARM64, x64 right now, and then to RISC-V. So basically, you'll have 3 alternatives. That would be the goal. Okay, so we started with the Litchi Pi 3.8 this year, Banana Pi F3, 16 gigabyte of RAM, ballpark $150. And then, okay, can I run a staking node on this board? Can I? The answer will be given in a moment, but you can see that there's a long way till it will see parity. So currently, these are the most advanced boards on the market, or the advanced CPUs, which are affordable. Thank you.
Perfect. So then I continue what we did. We tried and built all the clients that are available. I don't go into all the details, but I pick a few. It's like Geth, the execution client. It's just beautiful. You build it on RISC-V. It works. It runs. No code changes necessary. What we did with the consensus client, like Nimbus, it was good to see. We just had to change 5 lines of code, maybe. Or added a target, it compiled, it ran. Code is now upstream to the main branch, and it's in there now for 2 months, so anyone can build Nimbus on RISC-V boards. Another one is Lighthouse. A lot of libraries are not compatible with RISC-V, but we made them work with a few hacks, which we have in local forks of the repository. We didn't upstream it back yet, all of them, but we can run it locally, the stuff. But so, as you see, many other clients are just in different states of non-working, so there's still a lot of work to do. But the nice thing is there is progress. For example, last Friday, Peter Silagi tweeted out that Geth has now a target added, so they build a Docker image for RISC-V now regularly. Then we ran the clients on various networks. We used Ethereum mainnet, Holeshki, Sepolia, testnet for Ethereum, and also the Chiado testnet, which is a testnet for Gnosis chain. We first ran the clients on both clients on one board, like Nimbus Geth and Lighthouse Geth, and as you can see in Ethereum mainnet and Holeshki, it's kind of, they can't really sync up. They might sync up to the tip of the chain for maybe a few minutes, lose sync again, and then not in sync for half an hour, and then sync back up again. Nice thing is, Sepolia works. Syncs up, is stable, perfect. Unfortunately, we can't run validators on there. It's a permission set. So we went to Chiado testnet and tested it there. We ran a validator. It was stable enough. We can see it later on. When we did the split clients, so like only one client on the RISC-V board to see if it runs better. If you only run the consensus client on the RISC-V board, you see in the lower part of the table, it's actually the same picture. So it seems like the consensus client is a bit limiting. But the nice thing is, if you run Geth on the RISC-V board, you can easily sync Ethereum mainnet when the consensus client is on another board. So it looks like consensus clients are the limiting factor, especially on large networks. So if you have the validator set is huge, these boards are limited. And here is an example for a validator on the Chiado network. What you see here in these graphs, it's the CPU performance, CPU usage over time. On the left side, it's just normal operation of a validator node. You have some spikes, which are most probably epoch boundaries. And if you have a sync committee, you have the CPU usage goes up to about 50%. It's very stable, and it uses about 5 GB of RAM. And overall, it's about 4 to 5 watt of power used for this operation. So as you can see, it can do all the duties, and the most beautiful part, that's from the block proposals we did on the Chiado network, continuous block proposals, no outages, nothing. And if I look at the rewards we get, they are comparable to what other validators get, so the attestation efficiency is great on these boards, on the testnet. But what we need better hardware. Companies working on that. In the next 1 or 2 years, we'll get there where we need it to be. We need to get the clients ready. We need a node setup tool like ETH Docker and Setch ready, but obviously they're only working on that once the clients are there. And more importantly, for software engineers, we need to get some of the cryptography libraries implemented in assembly for RISC-V, which is a nice task if you like this kind of stuff, because it's not very often in your lifetime as a software engineer that you can get the chance to start from scratch in this kind of assembly code. But a little bit further in the future, what could be amazing is like ZK VM. They're mostly designed to run on RISC-V instruction set architecture, so depending what kind of path we take in the future, one could imagine that these kind of ZK VMs run natively on the RISC-V CPU, which is would be amazing. So to summarize for the RISC-V boards, if you want to run an Ethereum mainnet node, don't do that, it doesn't work yet. If you want to run a testnet node, it kind of works. Maybe not the best choice. But if you want to play with hardware, if you want to improve the clients, if you want to write code for RISC-V, or maybe have a glimpse into the future, it's amazing to play with them.
Thank you. So here is a Ethereum future that might affect the small validators, the small boards that we are trying to make work. So the 4 terabytes requirement might be coming sooner than later. So that might, 4 terabyte means double the price, almost the price of the board itself. Also, Verkle, from the discussions at this conference, I understood that Verkle might put strain on the CPU. So the CPUs that we already have that are already working with Verkle might not work anymore. We need a lot of testing to do it, to actually confirm or infirm this thing. Also, if and when the staking requirement will become smaller, that will be a boon for this kind of home validators. So it will be great. Also, if the maximum Ethereum balance for a validator goes up, then it will be less chatter on the network. Again, they will work better. As a conclusion, for now, there is quite a large set of boards that work. They are working in production. They are already working for 1 year or 2 years already. And some of them might fit a home staker needs today. We are waiting for the next iteration of ARM64 and also RISC-V to see where this goes. Again, contributions are welcome for the work that needs to be done, mostly in the assembly implementation of the crypto primitives. That's, in our opinion, that it's why the RISC-V cannot sync Ethereum on all nodes. And of course, it would be great to verify more RISC-V boards. Thank you very much. We have a set of links on the presentation, if you download the presentation.
Okay, cool. I'm going to push you guys this way so I can join you on stage and we can handle questions. Okay, thank you again so much. We'll start from the top. Again, QR code here. You can also collect a card to indicate that you've shown up here. But first one, how much disk is necessary to contain the Ethereum blockchain for the next year?
So currently is borderline on 2 terabytes. Of course, it depends on each client slash so execution slash consensus layer clients. So I think without.
Sorry, I'm getting asked to push you guys more.
So without the Verkle implementation, we'll expect it in 1 year or 2. Maybe faster. It depends also, again, on the Ethereum usage, right?
Okay, perfect. In your experience, what's the biggest factor for missed attestations? Network, SSD, or CPU?
I can continue on that. I saw a direct example on ARM64 is the CPU. Basically, if I overclocked a little bit the CPU, it worked perfectly. So yeah, from my experience, CPU.
Obviously, it depends on the node setup you have. Yeah. When I support node operators, most issue these people have is with the SSD, which then, yeah, influences attestation rates, but sometimes in a weird way, so it's hard to track down. But it really depends on the setup where the bottleneck might be.
Yeah, if you have any good enough NVMe slash network slash CPU, that's no issue at all. Depends where the borderline is. So.
Okay. How important is 32 gigabyte versus 16?
Shall I take it? Okay. 16 is perfectly enough for normal operations. If the network is non-finalizing and you run the Ethereum mainnet node, it's your main node for staking, you might be part of the problem because your node might go down. As a fallback node, that's most of the time no issue. So 16 gigabyte might be enough depending on what exactly you do. Otherwise, I'll go to 32.
So I mentioned also in the presentation, if you want to have performance monitoring and other, let's say, small utility stuff there, 32 is way better because you will have a lot of more space to put more applications that can help you on the long term.
Okay. What possible avenues can one explore if they want to contribute to ETH compatibility on ARM or RISC-V platforms?
That is a very open-ended question. It really depends on your skill set, what you want to do, and in which part you want to contribute. Like, there's all the clients, most of them have issues. So it's different programming language, different kind of issues. For some, it's, as far as we understand, issues with the Linux kernel, which needs to be changed specifically for these boards, like for RETH, you have to do that. For other ones, it's probably implementing assembly code stuff. If you like to do that, one can do that. Yeah.
There are also more powerful boards, but they are prohibitive in price. They're like $1.5K that might be able to run it at this moment, like making abstraction of that there's no assembly code for the crypto primitives. So if someone can has access to that kind of hardware, it would be great to know the results. The code already works.
Okay, I just got a sign that said time's up. So thank you guys so much for joining. If you have, there are additional questions here, so feel free to meet them on the side. There's actually also a function on this to give speaker feedback, so do that and watch out for that too. Thank you so much.
Thank you.
Thank you.
Thank you.
Cool. So I think we have a 5-minute break until our next session at 4:10, which is going to be from pure DAS to full DAS towards massive scalability with 32 milliblocks and beyond. Okay, hello. Time for your next session. We will be introducing Francesco, going over single slot finality and the future of staking. As I said before, if you're new to this room, there will be a QR code for you to scan, ask questions, and collect feedback, collect a card for. So give it up.
Hi everyone, I'm Francesco, I'm a researcher at the EF, and I'm here to talk to you about making Ethereum finalize faster and how this relates to the future of staking, to potential staking changes to come. So first of all, let's recap, what are we actually trying to achieve with single slot finality or generally faster finality? There's actually one goal is faster finality in itself. So we don't want to have a UX and security trade-off. You're not supposed to need to choose between waiting for finality or and getting higher security, or accepting something confirmation faster but at a lower security. And this is also not just for regular users, but for rollups whose interrupt speed is essentially bottlenecked by the finality time on L1. But this is not the only motivation actually for a faster finality roadmap. One reason is also just to generally improve the consensus protocol that we have and kind of fix some essentially security problems that exist in it. Not really critical security problems, but more basically going from the current security properties that we have, which are suboptimal, to really like optimal, like provable security properties. And yeah, one question that should come to you is, why don't we just do it immediately? And the main reason why we can't in the short term is that we just have way too many validators. We have 1 million plus validators. I think it's almost like another 100,000 on top of that. It's just way too many to just consistently aggregate in each slot. And it's, yeah, this essentially is a lot of verification time for the signature and a lot of bandwidth to propagate them. The thing is, we don't actually have 1 million validators. We have maybe 10,000 nodes. It's the exact number is not clear, but something on that order of magnitude. And we already know that we can handle more than that per slot. So we already have committees of around 30,000 validators per slot. So that load we know we can deal with. Yeah, so one thing that's coming up that's going to help us is MaxiB, the ability for validators to have up to 2048 ETH and to allow for consolidation. But okay, so we have MaxiB in the next fork. What else do we need? So first of all, we need a protocol that actually is like fast finalizing and still has all of the properties that we want, which are many, and we have like a quite unique sort of model that we operate in. And then the other thing that we need is validator set capping. So we don't want to, let's say, go from 1 million validators to 30,000. Then we are comfortable that we can handle this load. We turn on single slot finality or faster finality, and then we round trip all the way back to 1 million validators because more small stakers come in or deconsolidate or something like that, and we're back to square one, and the system actually breaks. And yeah, the first part of this, just the consensus protocol part, we actually have a lot of progress in already. There's been a lot of work in the last 2 years, and we essentially have protocols that we're quite happy with in theory. The second part, it's a bit fresher area, but I'll essentially talk to you about both parts in the rest of the talk. So with the first part, I'll focus on a specific protocol which we've called 3-slot finality. So yeah, single slot finality is a bit of a meme. It doesn't necessarily mean single slot. It really just means like we want to have faster finality. And yeah, so what does roughly this 3-slot finality protocol look like? It's more or less much like the current protocol. We are really reusing a lot of the same, at least like conceptual components. So it still has a what we call a dynamically available component, which is essentially like a lambda ghost, which is what we have today. And this is the part that's supposed to keep working even if we cannot finalize, for essentially extra resilience. And then we also have Casper5G, this finality gadget that eventually gives us economic security as long as 2/3 of the validator set is online. And the other, another component that's quite different from today is that, well, first of all, we would be able to finalize fast, but specifically we would be able to finalize in 3 slots with finality being pipelined so that you need multiple voting rounds for finality, but these would be essentially pipelined over multiple slots, so that we can still have blocks coming in between these rounds. So yeah, this is what it would look like. We have a first slot, a block comes in, just like today. We have a first round of votes. At first, votes, just like today, have three components: a source, a target, which are Kasper-FFG concepts, and a head, which just says, this is the thing that I believe to be the head of the chain. At first, we would only care about this head vote, which would be for B, in the ideal case. And then we would move on to the next slot. New block comes in, B prime. Now the head vote would be for B prime, so we've moved on to this next block. The target vote would now be for the checkpoint BT. So just like today, we have this concept of checkpoints that are essentially blocks and epochs for Kasper-FFG, and these are the objects that we essentially do finality over. Here we would have these like block slot checkpoints. So a vote for BT as a target would essentially be trying to say, I think that B is ready to be finalized, or to enter the finality pipeline, essentially. Then we move on to the next slot. We get a B double prime. Again, this gets a head vote. Now the target is the one from the previous slot, so B prime T plus 1. And then the source is BT. So now this source vote is essentially saying, I know that that B is justified and is ready to actually be finalized, and we're kind of getting to the end of the finality pipeline for B. But as you can see, there's three things kind of going on at once. B enters the finality pipeline at the beginning, then B prime enters in the middle slot, and then B double prime. So all of them are in kind of different stages of the finality pipeline, and you can that's reflected by the kinds of votes that they receive. And yeah, essentially, this pipeline for B would look like this. Already after the first round of voting, we could confirm it. At this point, we have no economic security, but we already have very strong guarantee that it's not going to be reorged. After the second round of voting, once we've gotten these target votes, B would be justified. And after the third round of voting, after we've gotten all of the source votes, it would be finalized. And yeah, actually, we don't even need to think about the blocks, B prime and B double prime existing in the middle. We could also just focus about the votes that are relevant to B, so the head vote, the target vote, and the source vote. If we really just want to focus on essentially the finality pipeline for B specifically, and even if B prime, B double prime, like these other blocks in the subsequent slots were to be missed, for example, the proposer does not show up, the protocol actually guarantees that B can still complete its pipeline, essentially. That like no matter what, if the proposer of slot T is honest in the way it creates B and sends it in a timely manner, then B will successfully go through this whole pipeline and be finalized. And yeah, I didn't go into more details of why this is the case, but you can check out the paper or blog post for that. And now this is there's this other part to this whole discussion, which is the one that's a bit less understood, like more kind of earlier research, which is validator capping. So the problem of making sure that we always maintain a kind of constant load that we know how to handle, and we don't do this round tripping of reducing the validator set through consolidation and then going back up to like an unsustainable validator set, essentially. And specifically, I'll focus on a quite recent idea called Orbit. That's one way, one point in the trade-off space of how to handle this problem. But I'll try to also introduce the problem in general. So this is from Vitalik's one of Vitalik's many latest posts on the future of the protocol, in particular the one from about the merge. So you can kind of see essentially this spectrum of possible ways to handle this problem. On the right, all the way on the right, you have this Tendermint style kind of small validator set, maybe a few hundreds, or in the context of Ethereum, this could be a few thousands. And these are really, large validators with a lot of stake. So there, it's quite simple to do. For example, in Ethereum, we could say that there's 30,000 validators. As we already said, this is a number that we know we can handle. And so we could just say, okay, we only have space for 30,000 validators. That's the most that we can do if we want to have faster finality. But this means that each validator would have to have like a very high balance, not incredibly high, but a couple thousand ETH or 1,000 ETH, which is much, much higher than the barrier to entry that we have today of 32 ETH. So that's kind of one extreme that would significantly change the barrier to be a staker. Then the other extreme is that all the way on the left, which is essentially we just do random sampling of a committee. So we say there are no barriers to entry. We could even say you can be a staker with 1 ETH, or maybe we don't even have a minimum. But then we sample. We do like random sampling essentially of a committee. And the issue with this is that this committee size is fixed. So if the total validator set is much bigger than the committee size, then the committee will inevitably have like a very small amount of stake. Like if only, today we have 1 million validators, only 30,000 can participate in each slot, then about only 1/30 of the stake will exist within each committee. So essentially very low economic finality. So that's like kind of all the way on the other end of the trade-off space. Somewhere in the middle of the trade-off space is a solution where we do sampling in a somewhat different way that's still trying to ensure that we have a fixed size committee, but it is trying to take advantage of existing heterogeneity in the way that the stake distribution is. So today we have 1 million validators, but many validators are actually clustered in staking pools, even though the protocol does not actually know about that. And so there is this natural concentration of stake that already does exist, and it is a natural thing to occur. And we can try to actually take advantage of that to find a point that's somewhere in between these two extremes. And just to call it out, this, though there it says Tendermint style, in the context of Ethereum, more likely what this would look like, it's what has been called sometimes rainbow staking, so where maybe we essentially split up staking into 2 different classes of validators, one which are responsible for essentially finality or attesting, and are more restricted or like have this higher barrier to entry of having a higher amount of ETH, so that we can essentially limit the number of these entities, whereas there could be like a lighter class of stakers that are still responsible for things like making inclusion list or even block proposing, or essentially other parts of the staking pipeline that don't really have this like technical limitation that attesting does. But yeah, so that's one possible way to go about it, but I'll discuss this kind of middle one that we call Orbit. So what is Orbit? There's this, Orbit essentially is a technique for sampling a committee in a particular way that tries to achieve these 2 things, of having the committee being of a fixed predetermined size that we can handle, and of having a lot of stake. So let's call T the maximum effective balance, which is becoming 2048 ETH as of the next fork. Once we select this committee, we'll take a, so let's look at how does a staker with S stake, so this could be 32 ETH or 64 or et cetera, how does it get into the committee? It is selected with probability S over T, so proportional to stake, and it gets rewarded when it is in the committee. So if it is actually in the committee, it is participating, it's attesting, it gets rewarded with some constant reward that does not depend on stake. So this is sort of the opposite of what happens, how you normally do this, where the selection is random, so you don't make the selection proportional to stake, but the rewards are proportional to stake. But because we still have this proportionality in one of the 2 terms, you still get that the expected rewards per validator are still proportional to stake, as they of course should be. And so what does this look like in practice? On the top, you see a representation of a validator set with different sizes of validators. For example, validator with the size T would be like 2048 ETH. And then there's the same amount of stake split up in different ways, like T over 2, T over 2, or 4 validators of size T over 4. And then you see this kind of projection down to the Orbit committee. This projection is essentially trying to tell you what is the expected outcome when you're sampling from the validator set on top and you're getting an Orbit committee. Expected here is really like in the probability sense of expectation. So let's start with the one on the left. The staker with T stake, 2048 ETH, for example, will be selected always with probability 1. It's always going to be in the committee because, as we said, the probability was S over T. So T over T, just always in the committee. We move next to the T over 2 and T over 2 stakers. They're selected with probability 1/2. So they'll only be in the committee half of the time. And so when we think about expectations, essentially we expect that one of the 2 will be in the committee, but only one of the 2. Of course, it can be that it's both or none, but that's just the expected case, let's say. And 3/4, same thing. They're all selected with probability 1/4, so that we expect one of them to be in the committee. And this way of selecting has essentially this interesting property that no matter how you split the stake, so invariant to the stake distribution, the size of your orbit committee is always the same. So you can see, on the orbit committee line, it doesn't matter if we split the stake as T or T/2 and T/2, or the other case, the expected case is that we always get one validator per T stake, essentially. And so this is essentially what gives us validator set capping, at least in expectation, but then this is easy to turn into actual validator set capping in practice because the variance is low, basically. And we can just cap it and yeah, it's not a big deal then. So yeah, more concretely, with a bit more dramatic effect of looking at a much a more out of proportion kind of way of splitting stake, we have still this like 2048 ETH validator, this like max balance validator. Again, it gets projected down to a single 2048 ETH validator itself, so it's always selected. When we take the look at the picture on the right, it's the same amount of stake, but split up much more dramatically in however many it is, I guess 64 validators of 32 ETH each. So this could be solo stakers, just completely different entities. And again, when we project down, we only get one validator. So what does this mean? That just on average, each of those will participate only once every 64 slots, essentially. So that still the expected contribution to the orbit committee is just one. And again, to repeat, like, what does this get us? First of all, what I've tried to argue in the previous slides is it gets us validator set capping, basically out of the box. So if you say that D is the total deposit size, so today this is just the total amount of stake, which today would be 35 millions, this potentially means that the expected size of the orbit committee is D over T. This would be basically, with these parameters, around 17,000. So before I said, today we handle exactly twice as much of that, 34,000 each slot. So we already know that this is something that we're perfectly able technically to handle. And then it gets us, if we have enough consolidation, like if we have staking pools and so on, consolidate enough, it gets us the possibility of having high economic finality immediately. Like a single orbit committee might be small, it might only be 17,000 validators, but it should contain most of the stake, essentially. Like most of the consolidated stake will always be in it. And then another aspect that I did not touch on is that in principle, it could mean that it's more plausible to lower the minimum effective balance. So this is the 32 ETH threshold for entering the set, which is not being touched in the Maxi-B upgrade. This could in principle be actually easier to reduce with something like Orbit, just because the mechanism isn't really sensitive to the minimum effective balance. If you notice, I never actually brought it up in any of the arguments before. And yeah, one important question here is, so this sounds like a big change. You're changing who's participating, the way they're chosen to participate. What does actually, what changes? What does home staking in particular look like in this world? So let's first start from actually from what stays the same, which is the frequency of participating in block construction. So proposals and inclusion list proposals, once we do have inclusion lists, which hopefully is soon. This is not going to change at all. Like this does not depend at all on the way you're sampled to a test. Because essentially there's no technical limitations on, there's only one person proposing each slot. There's only maybe a few people making inclusion lists. This has nothing to do with, we don't need to restrict this any further, essentially. And another point that I'm not going to be able to get into is that actually the influence of home stakers, or any stakers for that matter, on LMD Ghost, on basically the regular fork choice that comes before finality would completely stay the same, but I'm just not going to be able to explain exactly why that is the case with the time that we have. And now, what changes? So one important point is that you attest less often. So if you go back to the picture that we had before with the 64 small validators with 32 ETH, they're only chosen once every 2 epochs, essentially, like once every 64 slots. And so but it's less often than consolidated validators, but it's more or less as often as today, just half as often as today with the parameters that I said. Instead of once an epoch, you only attest once every 2 epochs, but the rewards are changed in such a way that you're not earning less than other consolidated validators. And another point that it's maybe more important is home stakers would generally have less influence over finality because, again, if you think about that picture from before, you have these 64 small validators, they're kind of compressed to one. So only one of them will actually end up in the set. So even if home stakers have, maybe 10% of the stake, the amount of stake that they will have in the orbit committee might be compressed. One point there is, so this is probably, I would say, the most contentious part of this proposal. But yeah, one point there is that it's already kind of the case. There's already very little influence that they have over finality because there's only maybe 5 to 10% of stake that actually belongs to home stakers. And yeah, I mean, this was just bringing, just showing you why this compression happens again. And one last point is we would probably want to ensure that we do have enough consolidation, since this is an important part of how we get better guarantees from this mechanism. How do we do so is probably to have consolidation incentives that essentially go down to 0 once we reach a certain amount of consolidation that we're okay with. So maybe 75% or some other amount that we're happy with. And yeah, when we're outside of this regime, you have basically this incentive, if you're a staking pool or so on, to consolidate. And yeah, what's left, essentially for the consensus protocol part, we have to spec it and prototype it. For the rest, a lot of it is really like having these hard discussions in the community around the future of staking and what of these trade-offs we're happy with. Decide what failure case we're happy with, and then yeah, we could introduce orbit sampling in the current protocol, and then we could eventually move actually to 3SF or to some faster finality protocol. Thank you.
Okay. I'm gonna shuffle you along towards the center so everyone can look at your beautiful face. Thank you guys again. Give another round for Francesco. Perfect. So let's dive into the questions, starting from the top. Avalanche already has single block finality with sub-second block times where every validator votes on every block. Does this proposed system have any competitive edge against Avalanche consensus?
Yeah, so to my knowledge, and I mean, it might be outdated, but I don't think so. Avalanche does not have any accountable safety, so there's no way to actually say if there is a consensus failure, for example, let's say double finality, there's no way to say which validators exactly were responsible for it, because the way they reach consensus through this like subsampling mechanism that doesn't really get everyone to express an opinion on a block.
Okay, cool. Next, does 3SF work with lower slot times?
So 3SF is kind of built in a way that doesn't really change the way the slot works too much. So it would be a slot that it looks quite similar to today. There's some like minor things that I didn't talk about that kind of deviate from this. But generally speaking, most of what we could do with today's slot, we would also be able to do with 3SF, I would say.
Cool. It seems 3-slot finality provides both constant time finality and liveness. What hypothesis do you make to guarantee both?
So yeah, I'm not entirely sure what exactly I'm not entirely sure, but let's say like if by liveness you mean availability more specifically, then this is something that relates to this LMD ghost part of the protocol. And yeah, it's possible to have both of them, finality and availability, because we have these two different kind of chains in a way. We have like the available chain and then finality on top. Otherwise, there would be an impossibility result. Maybe you mean something else, in which case maybe we can chat about it later.
Cool. Does Orbit changes how aggregators are sampled from the beacon attester sets?
No, most likely you wouldn't, I would say. Yeah, we could just, one way to do this is that we could just reuse all of the aggregation infrastructure that we have now, including the specific way the aggregators are selected.
The majority of home staker reward actually from the attestation. Does this change would, I'm not speaking English correctly. Does this change would make home stakers suffer by a lot and just withdraw on being a home staker and go to liquid staking or something. Oh, okay, no, it's not me. It's a question.
So no, like the answer is like the rewards would actually be the expected rewards, but when we talk about attestations, expected rewards and rewards are kind of the same because you attest so frequently. Like even with Orbit, you still be attesting like once every 2 epochs. Yeah, you would not suffer because of that, because the expected rewards are still proportional to stake. So whether you stake 64 ETH in one validator or you have 2 validators of 32 ETH, your expected rewards are the same. You might have a little bit more variance, but it's attestations that we're talking about. You attest so often, then the variance is essentially irrelevant.
Cool. Okay. Would this change the staking APR, as not all validators are testing anymore, only the selected set?
Same kind of answers before. Like it wouldn't. Like when you're not in the set, you don't get paid. But when you're in the set, you get paid a constant amount. So whether you are a 2000 ETH validator or a 32 ETH validator, when you're in the set, you get paid the same. So you can think about it as like, once you're in, you get paid way more than you should, like based on your stake. Like you're not paid proportionally to stake. So overall, the two things balance each other.
Okay, well, I just got the sign, so I think that's all the time we have today.
All right, cool.
Thank you so much, Francesco.
Thanks, everyone.
We have another 5-minute break until it's actually 4:10 this time, from pure DAS to full DAS towards massive scalability with 32 milliblock blocks and beyond.
Oh, that's yours. See?
Okay, hello. We are now up for our next session from Chaba, from pure DAS to full DAS towards massive scalability with 32 millibyte blocks and beyond. Wow, that's a lot of words. Again, before I start, there's going to be a QR code. Ask lots of questions, scan it, collect a card, and I guess we'll bring our speaker on stage.
Hi, hello. So, yes, I have a long title. So I will be speaking about data variety sampling. And it's a long title, and I didn't want to make it longer, but actually I have to make a small remark. It's not even blocks. It's data variability space that we are speaking of. So let's see who we are first. I'm Chaba. I'm from the research team from Codex. We are working on a decentralized storage network, providing high durability guarantees. And our research team is also working with the EF on data variety sampling, and also the client teams. Okay, so I think you are all familiar with this chart. You have seen it like 10 times during this Devcon, I suppose. We had the IP 4844, and the transaction fees on L2 went down, right? And on the right side, we see those little ones. That's very good. That's very nice of 4844. But I hear that we have a problem. Yeah, to see that problem, I have to zoom in, sorry. So if we zoom in, we see this problem. So there is a slight increase in L2 transaction fees. And actually, there's a problem. L2 transaction fees are driven by blob space, by data variety space, and that's running out. It is really a problem. And if that happens, prices can rise fast. There are other data variability solutions. In Codex, we are also building one. But here I am to speak of the Ethereum data variability solution. So we should scale that Ethereum data variability solution. So yeah, let's look a little bit behind these numbers. What you see here, maybe you have already seen this one as well. This is the daily average size of blocks on the network. And you see that it was rising, and then after the merge, it started to rise. And then with 4844, it reduced. So this looks fine, right? Now, you see this less often. This is the problem. So this is what our node operators are seeing. This is the blobs. So this is the blocks and the blobs cumulative plot together. So this is the data amount that they are seeing. And now we can start worrying, right? There is more data to handle. But we are scientists. We can look at this different way. So let's see it on a log scale. And then it's not that bad, actually. Like, it's like, just like Moore's law. It's actually a different exponent, but we are better than those CPU guys, so why would worry? Okay, we just have to do that little technology evolution which keeps this running. And then we have a solution, right? We can draw that line. We just need more blob space, and that's a plan. And here's a plan. We need PIRDAS and then FURDAS. And we just have to be a bit lousy about the scale. So it's an unknown scale here, an unknown scale there. And then we solve the problem. What we want is more blob space. And what we want is less node traffic for our operators. Yeah, we just have to work out these little networking details. So let's see those little networking details that we have to work out. But first, let me have a quick detour, networking. But this is, I was speaking of average block size till now. But average was a daily average. And in the day, many things happen, right? Every 12 seconds, something is happening. So what you see here is the tail distribution of block size during a long period. You don't even see the small blocks. You just see the large ones. And this was before 4844. And what you see that there were blocks beyond 2 megabytes. And our nodes have to handle those. What if 2 blocks of such come one after another. And you have to handle that. So our technology have to handle these things as well. And we were measuring whether you can handle that. And the good news is that you can handle that. So the network was running and live. And what you see here is for different block sizes. These are the bins, so small up to 32 kilobyte blocks, and then between 1 megabyte and 2 megabyte. How much time nodes need to get the blocks. And the bigger the block, the more time is needed. This is a distribution, so the nodes which are receiving it only here, and there are many nodes which are receiving it before. Almost everyone is receiving it before 4 seconds. So things are fine. But clearly, it doesn't scale very well. As you've seen, if we want to increase the block size, then it would go to the right. So we arrived to a point how to scale layer 1 from the networking side. And we can do different things. First of all, we can change the slot time, the slot timing window and the internal timers. We can change resource requirements. It's a good discussion. It's a bit controversial. We have small gains, we have a lot to lose, so let me not go into that one. Then we can change the gossip sub, the protocol, the networking protocol. We can do improvements on gossip sub for large messages, and this is in the making. It's important, but this is not my talk today, and it's relatively small gains compared to what we need, still important. Then we can do sharding and database sampling, and this is my talk today. This is large gains, I hope. And then there's the fourth thing. We can do distributed block building. This is kind of intertwined with many things, but promises large gains. But basically, that would mean resyncing the whole data flow of the block transaction from submission of the transaction until the end. OK, so let's focus on point 3, the sharding and data sampling over the network. So data sampling, let's just key concepts. So you need to prepare the data. We were speaking of blobs. There are blobs. There's a package of blobs. And then we need an encoding. We need an encoding because we want to sample from it. And for the sampling to be effective, we need erasure coding. For the erasure coding, we need segmentation. So we need to segment it, chop it to pieces. We need to extend it with erasure coding. Then we have to commit to it so that it cannot be, nodes cannot send false pieces, basically. And once we've done this, we are ready with the data preparation. Okay? And here we have different structures. We have what we call the one-dimensional PILDA structure, where you have blobs which are extended and committed to. Or we have the two-dimensional structure, where you have blobs which are extended in 2 dimensions. If you look carefully, you see that actually this is also 2-dimensional. The difference is that it's not extended by an erasure code in this dimension, and that has consequences. Okay, and then you just have to sample. It sounds easy, right? The question is where you are sampling from and how you do this sampling. So I wasn't saying anything about that. So let's just see that. Okay, so we were typically speaking of DAS, but it's actually a DA plus an S. So there is the DA part, which is a property of the network. It's a global property. The data is available, the data is not available. And to have the data available in the system, I have to disperse it in the system. So I have to send it out, different pieces to different nodes, which are custodying it. And only then I can start sampling. So this is the DA part. It's ensuring data availability. It is doing the sharding. Nodes are only receiving pieces. And then there is the sampling part. Once the data is in custody at different nodes, you can start test sampling, asking for pieces, and getting pieces. Little graphical representation. So you have a builder. It does, here in the example, I was doing it with the 2D encoding. So it does the 2D encoding. And then you have those beacon nodes in the system. And what you are doing, you are sending out these things, pieces of this, actually rows and columns, to different nodes. Someone is getting only 2 rows and 2 columns. Someone is getting a bit more. Someone is getting the whole thing because he's running 100 validators and he's securing so much money, but it's better for him to get the whole thing. Plus, doing that, he can support the system. That's one side. That's just the data availability. Now you have to sample, and that's an individual node. And actually, every individual node has to sample. That's his own view. So he's picking a few pieces, and then asking for those from custody. So you're getting this piece from here, that from there, and if it manages to sample, then things are good. Okay. So we have this kind of two sides of things, and you can see that on the network, these are a little bit different. And we need them to behave differently. So we need them to be secure, robust, fast, and cheap. And we need sampling to be secure, robust, fast, and cheap. So we need the same properties for the two things. It's just different protocols. Okay. So I was saying that there is PIRDAS and there is FURDAS, and there is difference in the data structure. Actually, there are a number of differences. If you scan that QR code, we have a write-up on FURDAS, which is starting from PIRDAS. And some of these techniques apply to PIRDAS, some of them to FURDAS. So what you see here is PIRDAS. And in PIRDAS, you have one-dimensional extension. And that also means that when you are sampling, you cannot just get a small piece, because it would not tell you probabilistically enough. You have to get a full column. So your sample is a column, which is more data than a cell that you can sample if you have this two-dimensional extension. But to make this work, you need changes in the networking, changes in the erasure coding, changes in many things. Okay? So let me just give you a comparison of PIRDAS and FURDAS. Actually, let me go back and just go through this list. So we have different techniques here. The first category is about sampling, is about how I'm selecting what to sample, how I'm selecting those small pieces that I will be looking for. Then the second category is about erasure coding and the using of the erasure coding. Because what I can do is, if the data is erasure coded, I can use that as part of the transmission. So when I'm sending the data, I can already use the erasure coding to recover the data and then send it on to others. And that's a very important property. We are always using erasure coding when we are doing transmission, actually. Take your mobile phone, take whatever. Here, we can use erasure coding very efficiently to send data. And when we are sending a row, we can take a piece and we can send it on a column. And when we have received half of a row, we can extend it to the whole row, for example. And then there are techniques which are protocol changes. And I'm not going through all of them. Just showing you the comparison. So PIRDAS and FURDAS. So one is cheap, robust, fast, and secure. And the other is cheaper, more robust, faster, and more secure. And I was inclined to stop here. But let's see a little bit more in detail. OK. So FURDAS is cheaper. It's cheaper because it's, as I've shown, it's sampling at the cell level. And the cell is 512 bytes. Actually, it's 590 bytes because it's the data plus the proof, which is still much smaller than a whole column. So whenever we are, so the sampling becomes cheaper. It's more robust because it can do erasure coding, which is allowing what I was calling local repair. But what local means is important to understand. Local means in the sense of the code, in the sense of, let me go back here, in the sense of this square. So I only have a few data. I only have half of a column, and I can repair something. I can generate these. Or I have these, and I can generate these. Or I have half of the pieces here, and I can generate this one. I cannot do that up there. And that's a huge difference. That's a huge difference because that means that every single node can do repair. Not just big nodes who are having old data, but every single node. Actually, in that construct, we don't need big nodes which, by the way, we have in Ethereum, so it's not like we don't have them. But we are not relying on them doing the repair in the data structure. And it's faster. Why it's faster? Because we are working on new protocols, and both for the PubSub part and both for the sampling part. So, and yes, is it more secure? So the right size is still in research. Should it be more secure, actually, when this is secure enough that we are changing to this? Actually, it doesn't. It shouldn't be less secure. That's still in research. This is still in specification and changing. So let me not do more comparisons, because this will change, and actually this is still in changing. OK. Sorry. Last slide. As I said, it is not just PIRDAS and FURDAS, but we can go beyond. And to go beyond, we have to rethink the data flow. So how is this data flow? What is happening? What I was speaking about is what's happening in the consensus layer. So when a block is generated, how that's distributed. But actually, these blobs are coming as transactions from the world. OK? So let's say one blob is coming in. And that goes to the execution layer. And the execution layer has the mempool, and the mempool is redistributing this, sharing this blob between nodes. Actually, when it's blobs, it's not shared like when it's normal small transactions. When it's normal small transactions, these transactions are pushed to others. When it's blobs, it's just information that I have this blob, and then the others are pulling it. Overall effect, these blobs are spreading in the network. Let's see, there is another blob that's spreading also in the network. And then there is one node which is selected as block proposal. Takes the blobs, packages them, does the encoding, and then the encoded version is getting spread in the consensus layer. Everyone is getting his pleas. I think you start to see the problem, right? It's not the problem, it's an inefficiency. We have an inefficiency in the system in which we are distributing the data here, and then we are actually redistributing the data there. And it's the same data. So we can optimize it a lot, which is good, right? We need these optimizations for Moore's Law to happen. So we found another place where we can save a lot and have that curve go up. So what you can do in first instance is that we do the distribution up there, but whenever the node is realizing that he has a piece, he would need this and this, but he has the blobs, he has the data. He can just pop it up from the execution client, because the data is also there. Now, of course, this plot is optimistic, because I was putting this white blob almost everywhere, and I was putting this red blob almost everywhere in the network. In reality, you don't have every blob everywhere in the execution layer. Because if we could do that, like now you actually have, but when we are scaling, we will not be able to do that, because if we can do that, then we don't have a problem. Every node can handle all the data which is there. We want to scale beyond that. So in reality, you would have some blobs here, some blobs there, some blobs there. But then when you do that distribution, data can pop up. And that's one of the optimizations. Of course, that's a simple one. We can do much more complex ones where we have interaction between the two, and we are avoiding some of these duplications. But for that, we have to rethink the networking stack here, which is that P2P, here, which is using libP2P. They are doing different kinds of gossiping distribution. This is using Gossip Sub, this is using other protocols. So this is all, this can all be listening. But that's just starting. Okay, thank you.
Okay, we are now here to take some Q&A. So starting from the top, there are blob fees that play blah, blah, blah. Blob, blob, blob. There are blob fees that pay for blob storage, but is this verified at all? What happens if I get the fee but don't actually store the blob data?
Okay, block fees that pay for blob storage. I don't know. Yeah. I'm not sure what the question is about.
No worries. Question answer, question asker. If you have the question still,
feel free to clarify.
Clarify,
Then
but I'll mark this as answered. What are standing problems that hinder current adoption?
Okay, so it's just in implementation. So the PIRDAS is in implementation. It's still compatibility problems. PIRDAS will be here very soon. It will not be in Pacta, but it will be in the next fork. For FUDAS, we still have to figure out many things. So there was that question mark on the security, and we have to work on that to make sure that there are no issues with that.
Cool. Why do we need 2D erasure coding? Can't we put all of the points on one polynomial and extend it?
So putting them all on one point and extending it would be one huge erasure code, one-dimensional. And that would be very bad for repair in the sense that then you can only repair if you have all the data. And that just means that you have difficulties repairing. The 2D has this advantage of having this code local repair property so that the code distance is small, and you can repair pieces. So you can repair a single column, you can repair a single row, and that gives nodes the possibility to start repairing and contributing even before getting the full data.
If full DOS is way better than pure DOS, why not choose to implement it in the first place?
So as I said, pure DOS itself is changing. We were thinking of techniques for full DOS, then we realized that they are actually applying to pure DOS, and then they are part of pure DOS. We are still changing that. FUDAS is still much more research. It's a simple fact of life that there's too much pieces still moving in FUDAS to implement that.
Cool. And to cap us off, it seems full DOS approach are much, much better than pure DOS. Should we skip pure DOS and implement the full DOS? Is there any other trade-off?
So FUDAS is using many things that pure DOS does. So skipping is not a direct skip. It's not fully different. It's giving the 2D erasure code. So it has advantages, but it has also complexities. Whether we skip or not might save something on the implementation. When we are introducing it, it might also skip something, but we are losing also the graduality. So overall, I'm not sure it's good to skip, but we can think of it once FUDAS is fully evaluated.
What are open research questions?
So the open research questions is, so the last slide was fully open research question, or everything around that. On FUDAS, there are several questions around the sampling, how we can do the sampling safely in the sense that Sybil nodes cannot attack the system, for example. So there are still things to clarify there, especially attacks, network partitioning, and other things, how they affect security.
There's some fighting in the upvoting going on. This is fun. If 2D is better, would there be any benefits of 3D?
Absolutely. Multidimensional encoding is fun, but no, actually not. So we just need the local repairability property, and we have enough of that in 2D. 3D would not contribute to that too much.
Can full DOS be implemented progressively?
I think so, but we didn't define the progress. So it's something to think of, but we didn't define it yet.
Cool. And then I think this question was already answered.
I think we already had that.
Right, yeah, unless someone's aggressively, or I just forgot to mark as answered. Cool, so we have 1 minute and 34 seconds left.
I was actually spending time.
Yeah,
cool.
No, but so I guess there's one piece to this.
Questions.
You can give him feedback on the QR code, so we'll give you some time to tell him how great he did. Collect a card. But other than that, I think our next session, well, I guess, yeah, let me start over. Thank you so much. Cool, so we have a bit of time, so our next session is going to be 4:40, a fast confirmation rule for Ethereum. Okay, cool. So we have our next session, a fast confirmation rule for Ethereum. So let's welcome to the stage Luca and Roberto. And don't forget to ask questions when the QR code scans.
Hi everyone, I'm Luca Zanolini, and today, together with Roberto Saltini, we are going to give you an overview of our fast confirmation rule for the Ethereum consensus protocol. This is a joint work with Aditya, Francesco, and Cheney. So let's start by answering this question: what is a confirmation rule? Before that, let me give you a quick definition that will be useful throughout the course of the presentation. What is a canonical chain? A canonical chain, very roughly speaking, is the chain that is followed by the honest validator, so the honest participants in the consensus protocol. For more technicality, is basically the output of the fork choice function, but let's just stick with the chain followed by the honest validator. Our fast confirmation rule is an algorithm that enables nodes that run this algorithm to identify blocks that will never leave the canonical chain, assuming good network conditions. Basically, this algorithm outputs whether a block is confirmed or not. And it satisfies these two properties. One is safety, meaning that if a block is confirmed by a validator at a given time, it will always remain in the canonical chain forever, basically. Moreover, we have also monotonicity, meaning that if a block B is confirmed at a given time, it will always remain as confirmed, meaning that if we confirm a block today, tomorrow it will remain confirmed. Sorry? Sorry, something is going on with the presentation. Okay, sorry. Today we will focus only on safety property, given that monotonicity actually requires some technicalities that are out of the scope for this overview. Okay, why do we need a fast confirmation rule in the first place? So today, the way to know whether a block will always be in the canonical chain is through finalization, right? The problem is that with the currently implemented protocol, finalization takes up to 13 minutes in the best case scenario, and for some kind of users, this might be too long to wait to get a confirmation in some sense. Moreover, we cannot really use block confirmations as we were used to do with proof of work, for example, where the more blocks are appended on top of a block, the higher was the likelihood that this block remained confirmed. Because in the current protocol, we have seen some attacks called balancing attacks, where the adversary could manipulate, in some sense, the view of honest validator, making them believe that they were participating in a chain. So in some sense, this might not be the real chain under this attack, so block confirmation doesn't really say anything about whether a block will always remain in the real canonical chain, in some sense. So with a fast confirmation rule, what does a fast confirmation rule give us? For sure, it gives us improvement on the user experience in Ethereum, because for having faster confirmation rule implies that small values transaction can, in some sense, don't have to wait for finality, but they can already immediately be assumed as confirmed, implying that they will eventually get finalized. Moreover, it reduces also risk trade, basically trade reversal, made by for exchanges that allow to optimistically trade immediately upon deposit. And moreover, it improves also reliability of some wallets. In particular, there are wallets that tell user that a transaction is already confirmed upon entering, upon including in the block. But as we said before, because of this possibility of a balancing attack, this doesn't really tell us anything meaningful. So having a fast confirmation rule can really improve also reliability of wallets in general. It's also useful for PBS in the sense that it provides block builders with an indication whether the block that they are building upon is actually not going to be reorged. So in some sense, this fast confirmation rule can give us more reliability and can help users that want faster confirmation time instead of having to wait finality. Before going into details of this confirmation rule, let me very quickly give you an overview of Gasper. This because Roberto will introduce some technical terms that is better if we are all synchronized on that. Gasper is the name of the consensus protocol. This is a proof-of-stake protocol that can be seen as made by two sub-protocols. One is LMD Ghost, which is a synchronous consensus protocol that determines the canonical chain. And Casper is the finality gadget on top of this that finalizes blocks that are outputted by this LMD Ghost. Basically, it finalizes blocks on this canonical chain. The time unit in Gasper is a slot. A slot lasts 12 seconds. 32 slots define an epoch. For every epoch, the set of validators is partitioned in 32 disjoint committees. And at the beginning of a slot, a proposer is randomly selected from a committee, and it proposes a block on top of the canonical, on top of the head of the canonical chain. And the other validators in the committee will just cast a vote, ideally for the block that has just been proposed. How validators choose which is the head of the canonical chain? They do it through the fork choice function. Fork choice function select all the latest messages ever cast by validators, and it chooses the heaviest chain in terms of stake that these messages carry. So for example, with this image, this is the canonical chain, and proposers will just append a block on top of B9, for example. One last thing, in case of a validator sending two conflicting votes for the same slot, we do not count these votes for determining the weight of this chain. So we discount equivocations. Now let's dig into the technicalities of the confirmation rule, and Roberto, thank you.
Thank you, Luca, for setting the stage with all the concepts we need to understand how the confirmation rule works. So let's start with some assumptions we rely on. The first one, we rely on the fact that votes sent by validators are received by other honest validators by the end of the slot. The second assumption is that we assume that there exists a maximum beta fraction of dishonest stake across any set of committees. So take any set of committees, we assume that maximum beta of the stake of this committee is dishonest, and 1 minus beta is for sure honest. Okay, as Luca mentioned, we cannot rely on chain depth at all. We do need to rely and look at the weight of the LMD Ghost votes. So how do we do this? Well, let's start by assuming this block B10 is canonical for now. For our example, we use beta 0.2, 20%. And then we assume also for simplicity that the weight of a committee is 100. Now, what we're going to require is S represents the support, the weight of LMD Ghost that goes towards block B11. We require that the S is larger than W multiplied by half plus beta. We'll see why. But just running through the examples, in our case, this means S of B11 more than 70, and we pick 71. We know that any other block for this slot that is conflicting with B11 has no more than, actually it has less than half W votes. So, which means less than 50, let's pick 49. What is the worst case scenario? Well, the worst case scenario is that beta of the stake equivocates. If beta of the stake equivocates, then 20 basically weight of 20 is subtracted from 71. We have 51 for B11 and 49 for anyone else. well, B1 wins the fork choice. So yes, with this rule, we can say B1 is canonical. But are we done? No, we are not done. All we can say is B11 is canonical in this slot. We want to say B11 is canonical forever. And we can do that, but we see why we can't do that just right now. So what happens, for example, if we move to the next slot? Let's start with progress with our example. When we go to the next slot, the committee weight goes to 200. Everybody, every honest one, votes for B13. These votes, 80, go also to B11. Now we have B11 as a weight of 131, but what we need is higher. We need 200 multiplied by beta plus half. We need 140. So we're not quite there, and what does this mean? Is B still going to be canonical? Well, the answer is yes, it is. But in order to prove it, we need to do some clever trick. This clever trick is assuming that we somehow, for now, we know who is honest. So we are going to use this H. H represents the votes for B11 that are from honest validators. Bear with me, we'll go over this honest thing later. And J represents the validator, the stake in the committee that is honest. What you're going to require is that H of B11 is larger than half the total weight of the committee. Clearly, honest validators never equivocate. Clearly, this will make B11 win the fork choice. But we are going to work with something a bit more complex, which is this. We are going to require that H of B11 is larger than J, which is the honest committee, multiplied by half divided by 1 minus beta. We'll see why this matters. The thing is that this second condition implies the first one. Can show you by running, using our numbers, we get HB11 more than 50. We just pick 51 for now. So what happens when, okay, sorry, I forgot this. We define an indicator, P, for usefulness of the fraction of H over J, which in our case turns out to be around 0.63, which is larger than half divided by 1 minus beta. So what happens when we go to the next slot? Let's have a look. Okay, the committee increases to 200. The honest committee increases to 160. Now, everybody that is honest votes for B13. This weight goes to B11 as well. If you now calculate P, we have 131 over 160, which is roughly 0.81, which is larger than our target of 0.625. That's exactly what we wanted. As we showed before, this actually implies that the B11 is at least more than half of the possible votes. So B11 will be canonical. Now, for those who actually know intimately Gasper, they might ask, well, but when you cross the epoch, things are not exactly like that. But I show you that that's not a problem. So what happens when you cross the epoch is that it's possible you have a new validator set that is sampled, but it's possible that in the new slot, you have validators that have already voted before. So in this example, we assume that the honest committee only increases by X, some X of some sort. So in the new slot, 80, all the honest one will vote in support of B13. And because X stake is new, they have not voted before, so the support for B11 will increase by X. Now, if you calculate P, is 51 plus X over 80 plus X. Because X is added both above and below the line, and 51 is less than 80, we know this is larger than 51 over 80, which already shown is larger than our target. So what we have achieved, what we have shown is P, this indicator P, never decreases. So once it's higher than our target, which is half divided by 1 minus beta, we know B1 will be canonical forever. But now, how do we measure P? Well, lucky for us, if we use our initial fraction, which is S over W to be larger than half plus beta, actually this implies the threshold that we want for P. So we're left with one last thing. So basically what we have is that if you have this, the Q, which it's what we mean to be defined to be S on W, to be more than half plus beta, this implies that our threshold on P and that B11 will be canonical forever. One last thing, how do we assume that B10 was canonical. How do we solve the problem? That's very easy. We ask, the question is Q more than half plus beta for B11, then we go back to B10, to B9, until we get to the finalized block. So in terms of LMD cost, that's all we need in terms of confirmation rule. Things get a bit more complex when we add FFG GASPA. So with FFG GASPA, the fork choice gets a bit more complex. We start from the latest justified checkpoint, which is roughly the checkpoint that is ready to become finalized. We remove some blocks that are problematic, and then we apply the fork choice that Luke explained before to the remaining blocks. So what we need to do to ensure that B and some block B is canonical forever, we apply the rule that we saw before for LMD Ghost, and then we need to work out a series of conditions that ensure that B will never be filtered out by by the effect of integrating LMD Ghost with GASPA. This amounts to, in our case, we require that the checkpoint justified by block B is from the previous epoch. This ensures that in the current epoch, block B is not going to be filtered out. And then we have this more complex condition, which I'll break down soon, which ensures that B will not be filtered out in any future epoch as well. So what we're going to do in this condition, we look at the weight of FFG votes for the checkpoint of B. We remove the maximum amount of those votes that can be slashed, because then perhaps they're Byzantine. So this corresponds to beta, the weight of the committee from the beginning of the slot to the current slot. And then we add the minimum amount of weight that will keep voting for the checkpoint of B, which is the 1 minus beta, the remaining weight between the next slot and the end of the slot. And we require this to be more than 2/3 of the total stake. What this gives us, the checkpoint B has enough votes to be justified. So through a kind of quite weak assumption, this checkpoint of block B will be justified over the next epoch. And then because we know that every honest validator only votes for a descendant of B, if there is any checkpoint in a future epoch which will be justified, that for sure will be a descendant of B, which means that B will never be filtered out and therefore will be canonical forever. Just going through some initial experimental results. They are due to Circle, so thank you, Circle, for running them. There is a blog post actually coming out soon, so stay tuned. The setup was, they ran the confirmation rule over 6 days. They detected over these 6 days 56 blocks that were reorged. Some also were 2-block reorgs. The implementation was a proof of concept. There were some approximations. So for example, they were polling beacon nodes every 10 seconds rather than running the confirmation rule at the beginning of each slot. Also, they were estimating the FFG weight using just the LMD weight. However, the results are very encouraging. First of all, none of the reorgs were ever confirmed, no matter the value of beta. So this gives quite good confidence of the security provided by this rule. Second, in terms of performance, what they saw was that if you fix beta to be around 20% of the stake, you could see confirmation in 4 or 5 slots. If you go up to 30%, you get to 8, 9 slots. However, we think, this has to be proved in practice, that if the rule is implemented by running it at the beginning of a slot, then we should be able to confirm a block in 12 seconds. So this leads me to the last slide. So if you are interested in testing this and you're interested in implementing this confirmation rule on a beacon node, reach out to us. Our contacts are in the talks description. Also, One is the QR code for the paper, which is also linked to the talk's description. And the second QR code is to the Ethereum consensus spec PR, if you are interested. That's all. Thank you.
Okay, cool. I'm going to approach from behind and push you towards the middle as we address questions. So we'll start from the top. Seems like confirmation rule will get obsolete with single slot finality. Does it make sense to work on it at this time?
Seems a question we asked ourselves.
Yeah, the point is that we still don't know exactly when single slot finality will come out. And the confirmation rule is something that we already have. So it can already be helpful in some sense while waiting for single slot finality. But yes, once single slot finality will be out, probably there will not be, it's not needed anymore. But yeah.
Also, it's not, it's, in our opinion, not too difficult. Doesn't require any hard fork. It's not that difficult to, I wouldn't be the one implementing it, but I don't think it's that difficult to implement, or wouldn't take that long, and provides good benefit in the meantime, yeah.
Okay, cool. The UI is not updating. How do you estimate beta? Is it a new parameter?
It's user subjective belief on the value of beta. So the user picks their beta that they believe that is the maximum, and they query. And according to what they believe is, they get the result accordingly.
Well, can a confirmed transaction still be affected by a reorg?
So this, as I said, one of the assumptions is that votes are delivered by the end of the slot. If there is an actor partitioning, this is not true anymore. Yes, it can be affected by reorg. So it's not as safe as finality, but it's quicker. It's a sort of trade-off.
What is the recommended value of beta you suggest? Is it 0.2, and how does it impact security?
That's a very good question. Of course, beta cannot be larger than 30%. In other aspects, and some, for example, that work on EPBS that's been researched out, usually 20% tend to be what people are comfortable with in setting beta, so that seems like a good, reasonable value.
What are the security guarantees? Do you have any probabilistic assumptions?
We have some probabilistic assumptions, which is the one that said, we have this assumption saying we take any sequence of slots and the maximum beta of the stake is dishonest. As you know, the committee is sampled randomly. And so when you cross actually the epoch, you have some also probability measure that if you assume that, over the entire stake, say beta 1 is dishonest, the fact that over some set of committee this is less than beta is a probabilistic measure, but it goes, the probability goes up very sharply. So there is some probability in there from that perspective, yeah.
Can you explain validators' honesty scoring more?
I'm not sure I fully understand the question.
If not, we can move on, and whoever asked the question can, I guess, re-clarify. And we have, the example has an honest amount of validators quite optimistic. What about a more pessimistic scenario? Can validators be honest most of the time until they find something they vote adversarial?
Okay, that's right. If I understand the question correctly, I mean, if this is the behavior you're thinking about, that should be accounted in the beta. So this rule relies on belief that one minus beta, they're honest and they will vote according to the rule. If some point, if in the future some of them become dishonest, they should have counted into this beta.
Okay, cool. That looks like all of the questions we have. Give them another big round of applause. Thank you so much.
Thank you.
And then our next session will be at 5:10, State Contention Rules, Everything Around Me. Okay, get ready for our next speaker, James Prestwich, talking about how state contention rules everything around me.
Oh, I got a nice little cover screen. All right. Hi, everybody. I'm James. I'm going to be talking about state contention. State contention is, you kind of understand it intuitively. Like your Uniswap trade can fail, but your token send can't, right? So it seems really simple on the surface. There's some things that fail and some things that don't. And sometimes it's not your fault. And if your token send fails, it is your fault. So I'm James. I work at Init4. Init4 is a research collective building next-gen Ethereum tooling. You can follow me on Twitter, GitHub, whatever you like. And we're talking about state contention. So this talk is not well laid out. I talk very fast. It's going to be a lot we can cover in Q&A at the end. All right, so this is the state. This actually looked very different on my laptop, so I'm going to be a little confused by the trees throughout this talk. This is the state. Don't ask questions, just roll with it. The state is a tree. The tree goes in the header. So when you access the state, multiple people are accessing the state at the same time. Ethereum can't do concurrent access, so we have to linearize. We have to put people in order. With state contention, reordering people changes outcomes. So if it's this order, we get this tree. If it's that order, we get a completely different tree. This is contentious state. Changing the order changes the outcome. So look, like, we have about 50 years of managing contentious access to state in computer processes and things, and the main thing to know about it is that the OS and the CPU mediate concurrent access. So typically when you're writing programs, you have this thing called Linux, and it runs on this thing called a processor, and they handle what happens when multiple people, or threads or processes or whatever, want to access the same resources. The only problem with this is that the Ethereum OS hates you and has a knife, right? Like, it wants your money. The Ethereum OS is designed to deprive you of as much money as possible. Okay. We call this MEV, which I forget what it stands for, but you know, whatever. So I want to talk for a second about the mail. You want to talk about the mail, Mac? Let's talk about the mail. I've been dying to talk about the mail all day, right? When I send a transaction on Ethereum, I want something from it, right? Like, I want to send tokens. I want to transact on Uniswap. I want some NFT PFP for some reason. I don't know. Like, I want something. That's why I'm sending the transaction. So I stamp up my letter, I address it, I send it off into the network. This looks completely different. So some slides are going to be broken. Don't worry about it. It's fine. So I define my scoring function. I have something that says how much I like the state that is the outcome of my transaction. When I'm sending tokens, I want those tokens to move. So if they move, I'm happy. If they don't, I'm sad. So in this case, I really like this nice evergreen tree. So it's 10 of 10, perfect, no notes. I may or may not like palm trees or deciduous trees, but I love evergreens, right? So builders, they make blocks. There are two builders that make all the blocks. If you don't know their names, you should learn them because they control everything around me. So builders decide what order state access goes in. This is how Ethereum, as a OS, CPU, whatever, virtual machine, mediates concurrent access to resources. It linearizes them, and the builders are the ones responsible for doing that. So the builders decide the order, right? And the order decides the outcome. It's perfectly deterministic. So you can kind of shortcut this and say builders decide outcomes. This is an important asterisk. We'll come back to it later. The builder chooses which transactions go in the block, what order they occur in, and therefore the builder selects outcomes from a set of possibilities. So that means, because my scoring function is deterministic on the outcome, which is deterministic on the order, which is totally controlled by the builder, that the builder decides whether I'm happy or not at the end of a block. It decides whether my tokens move. There are two block builders that decide whether we are happy at the end of every block, Right. So that's the mail. Builders mediate concurrent access to resources to decide outcomes for users. And here's where we get back to the asterisks, right? They can decide outcomes if they can affect the state, and if they can simulate that state accurately. So this is two different very important caveats on the ability of a builder to select state from the outcome of possible states at the end of a block. So one, there are some states that a builder cannot affect. They can easily affect Uniswap, because anyone can trade on Uniswap, but they can't easily affect my token send. They can't send my tokens for me. They can't take those tokens away from me. They can't take Ether out of my account. All they can do is decide not to include my transaction. So in some sense, my transaction is what we call order invariant. I don't care where in the order it goes as long as it gets in. So we talk about scoring functions. There are many classes of scoring function. There are many choices of scoring function. Typically, it's connected to what application you're running, what you're trying to do. Some of these are order independent. Order independent scoring is when I need my transaction in the block, but I don't care where in the block. So in this case, I don't care if my transaction is first or third. I'm happy either way. My scoring function is order independent. So examples of this, like I need to send Yaz 1 ETH, like I don't care if it's top of block, bottom block, I just got to send Yaz ETH. If I need to recollateralize a loan, I don't care if that's top of block, bottom of block, as long as it happens before I'm liquidated. And if I'm recollateralizing a loan in the same block I'm liquidated, that's just my fault, that's on me. And if I'm transferring my NFT PFP that I bought earlier, like 10 slides ago, I don't care where that transfer goes in the block. They can't deprive me of that NFT, which means I can transfer it regardless of what the builder does as long as my transaction gets in. So if the state's not contentious, like the outcome may not change for me. With all of these order invariant transactions, scoring functions, goals, intents, if you want. This isn't to talk about intents. When the builder rearranges things, you still end up happy. But with things like Uniswap trades, you may not. You usually don't, in fact. So there's a distinction between these two classes of transaction. One where the builder can exercise a large degree of freedom over the outcome, and one where they can exercise a much smaller degree of freedom over the outcome. Another important example here is that if the builder doesn't include my token send, that transaction's still valid and it can go in the next block. If the builder changes the outcome of my Uniswap trade, that transaction is no longer valid, can't go in this next block, and I have to reattempt the trade again, and I have to pay the gas fee again. So this comes back to simulation. When I send that Uniswap transaction, I have to look at Ethereum state and I have to simulate the outcome of my Uniswap transaction so that I can appropriately gas the transaction, so I can sign it, submit it to the network, whatever, so I know what I'm getting from the Uniswap transaction. The builder also needs to be able to simulate my transaction. A builder won't include a transaction in the block that it can't simulate. And you might be thinking, James, you just said a minute ago that the outcome is a deterministic result of the order, right? So how could the builder not be able to just simulate that deterministic function? And the answer is that we're actually in a pretty complex world now, and there are some times when the builder doesn't know things in advance. So if the builder can't determine the outcome, they don't get to decide the outcome, which, should be pretty obvious. I don't get to decide something I don't know. So simulation relies on perfect knowledge. They need to know all inputs to the state transition function when they simulate the block. Simulation allows the builder to censor me or to interfere, but it's actually good too. It's necessary. We can't really function very well without it. I need to be able to gas my transaction, which means I need to simulate it to know what it'll cost. And when I'm transacting on Ethereum, what I'm doing is functionally paying the builder to get the outcome I want. My gas fee goes to the block builder, and the builder gives me the thing I wanted out of it. That's the good version of the relationship. That's what most users go through all the time. So in order to get what you want, you pay the builder. And if the builder can't simulate the transactions, they don't know if they're giving you what you want or not. And so you might just get wrecked through nobody's fault at all. Simulation is critical for interacting with the chain. We don't want to get rid of it. So in what cases does a builder not have perfect knowledge of the future? You'd think like the builder is creating the Ethereum block. They must know the current Ethereum state. They must know what's in the block. They should be able to produce the next state too, right? So sometimes we reference new and unpredictable information. These slides look very different. They look great because Tom made them. This is from a blog post that we wrote recently about reorgs in rollups. Not something people talk about very often. So Tom made these slides. This is Tom. He's great. We love Tom. Tom is an example of unpredictable input. You didn't really expect me to be putting Tom up over a slide about reorgs. And rollups are the key example of unpredictable information controlling state while a builder is simulating a block. So this is what optimism looks like. The H blocks are host blocks, the R blocks are rollup blocks, and rollup blocks reference some older state, some older host block, some older Ethereum block. This is because optimism and every other modern rollup does what we call run-ahead sequencing. The sequencer is progressing the rollup faster than Ethereum progresses. So that means that they can't reference new Ethereum state. Because if Ethereum reorgs, you go from some old Ethereum header to some new Ethereum header. The rollup, if it referenced the reorg state, is now invalid. So the rollup needs to reference only state it believes will not be reorged. Optimism waits 3 to 4 minutes, which seems fine. Arbitrum waits for justification, which if you watched the last talk, you'll probably have a pretty good idea of what justification is. That's closer to tens of minutes. And they do this to ensure that the rollup sequencer has perfect knowledge, that the state of Ethereum referenced by the rollup will not change. So this delayed reference to Ethereum delays all entrance to the rollup. The rollup can't reference modern Ethereum blocks because that would mean the information is not perfect. So it references old Ethereum blocks. Right, I just said this part. This is when I get my slides out of order because I'm not a very good builder. So Optimism and Arbitrum's pre-confirmation system that the sequencer runs that gives you a trusted stamp on every transaction requires simulation. And therefore, it time lags host references in order to preserve simulation. Their entire fast confirmation system, which is a trusted stamp from a central authority, relies on simulation and relies on time lagging. So they can never reference current Ethereum state, only some view of the past. And that's the trade-off. I'm getting myself all out of order this talk. So with a based rollup, it's slightly different. Based rollups can reference current Ethereum state. But the based rollup builder doesn't know what Ethereum state will be in the next block. If the rollup and the host are producing block 10, the based rollup builder doesn't know what the state of Ethereum will be after block 10 while constructing rollup block 10. So these links are much tighter, but there's still a 1 block delay in based rollups because you can't reference the current Ethereum state because you don't know what it is, right? So this is where we come back to if builders can simulate things accurately. When something like a rollup references the host chain, it references information that the builder doesn't know. So if the rollup state transition function references anything in the host state, the builder doesn't know what that state is and doesn't know how to simulate the rollup block. So that's why we time lag optimism and Arbitrum sequencing so that they can reference past Ethereum state instead of current Ethereum state. And so now I stole a bunch of slides from earlier in the presentation, and I'm going to pull it back and tie everything together. The builder chooses outcomes, and it chooses whether I like those outcomes or not. Okay. Some outcomes are order invariant, where it doesn't matter where in the block they go, as long as they're included. Nothing can interfere with those transactions and change the outcome via contention, because they are fundamentally non-contentious, or the contention is permissioned, like in the case of a token send. Okay, so when the builder includes an order invariant action, they know the outcome, even if they can't perfectly simulate the state. So you can have a portion of the state that is simulatable, even when the remainder of the state is not. So in the case of a based rollup, when it references Ethereum state, if it references only the outcomes of order invariant actions, you can have a 0-block time lag on communication between Ethereum and the rollup. This is the only case in which you can do that. And so we're going to go through the takeaways real quick. All right, this is, again, what I said. I'm getting ahead of myself every time. So when the rollup block is submitted atomically with order invariant actions, the rollup state transition can read those. So when the rollup block going to Ethereum is alongside token sends, then the rollup can know that those token sends occurred and to whom the tokens were sent, and that those tokens definitely confirmed. Because the alternative, if the token sends reverted, then the rollup also reverted. Right? So the rollup knows that either those token sends occurred or that rollup block didn't occur either. They're atomically linked, and therefore the rollup can reference those token sends in its state, in the same block that they occurred on Ethereum, and maintain simulatability. It allows the builder to construct cross-chain transactions within a single block. So, we learned a little bit about how fast I talk and that we have a bit too much coffee around the venue. It's free. It's not very good, but I like it. We learned simulation allows censorship, right? If the builder can simulate your transaction, you access contentious state, they can censor you. We wrote a whole blog post about this. We showed that the optimism sequencer can always censor Aave withdrawals or any lending market withdrawals, regardless of whether you use forced inclusion or not, because they can use state contention to prevent the market from having liquidity when your withdrawal is processed by the rollup. They can do that when they're sequencing. They can do that with forced sequencing. It doesn't matter. So on modern sequenced rollups, you have no guarantee that you can ever leave an Aave market if you piss off the sequencer. Okay. Simulation is necessary for pre-confs. It's necessary for gas estimation. It's necessary for using the chain. We need to know how much things will cost and what they'll do in advance. Pre-confs, like Optimism, Arbitrum, everyone does, require delaying communication between Ethereum and the rollup by a significant amount, minutes to tens of minutes, depending on your security parameter. Simulation is absolutely necessary for the only way we know of to do same block host to rollup communication. Pre-confs are inherently incompatible with same block communication because they require delaying the state reference. You can never have both a totally reliable pre-conf and same block communication. So we're kind of walking a mechanism tightrope where we have two sequencer designs that are out deployed, run ahead and based. There's likely other better designs that give us things like same block cross-chain communication, but we just haven't found the right path through the middle. So, you know, this is the kind of stuff I work on all day. Thanks for listening to my talk.
Okay, cool. I'm going to shuttle you along to the middle. And then, okay, I guess we had one question, which was an exclamation that said, super cool talk, which is amazing. So thank you so much. I guess we're shuttling you off. So give another round of applause. Oh, wait, no. Okay, no, there are questions. People forgot to submit them. Come back, come back. Okay. Super cool talk. Thanks for your talk. Doesn't angry sequencer need liquidity to block Aave withdrawal? How angry can it get?
The angry sequencer does need temporary access to funds to block the Aave withdrawal. But because they control the duration of their own borrow, they can make that duration effectively 0 because they control the timestamps, and therefore they control what the Aave market charges them in interest. So they do need liquidity in order to borrow and drain the liquidity of the market you're in. That doesn't seem to be a big challenge. Sequencers tend to be controlled by entities that happen to have a lot of cash lying around in the form of some sort of token, or just a lot of cash lying around.
Okay. What alternative designs do you think could be cool aside from base and run ahead?
I recently talked about this on the Gwart show. I think that we might be overcomplicating things a bit with sequencing. Like the Optimism Arbitrum run-ahead sequencer model is complicated. Like you saw how much more complex that graph was than the base roll-up graph, right? Like you have to manage state references. You should go read the docs on this because it's a real pain. And then base sequencing is basically just making your rollup a part of the modern MEV pipeline. And if there's one thing we kind of really hate just terribly, it's the modern MEV pipeline. Like the PBS auction is one of the worst, most toxic things going on in Ethereum. It's why there's only 2 builders and they decide what happens to your transactions. It's not good. So rather than trying to just design a mechanism from scratch, I think there's room to just simplify. Why not just have round-robin sequencing? Like, get 5 people together, make them take turns, don't have an auction. You're already more decentralized than Ethereum. If you get 5 of your closest friends, you are more decentralized than Ethereum block production, and that's a problem.
Okay, did you expect that we will end up with just 2 builders?
The first time I wrote about MEV was in 2017. I think we published it early 2018. And that blog post was called Miners Are Not Your Friends. Back then, we modeled this as miners interfering with transactions by reordering, inserting, dropping, censoring, whatever. And the metaphor we used was a treadmill. The miners are constantly racing each other on treadmills, and the treadmills speed up to the point of the fastest runner. So you are constantly racing everybody else, and if you fall behind for more than a few minutes, you get kicked off the network. You stop being able to mine effectively, and you stop winning blocks, and that means you stop being able to pay your bills, and you go out of business. Anything that's hyper-competitive like this will be a race to the bottom and will cause market aggregation. The PBS auction, from the very beginning, obviously caused market aggregation. We knew this when we built it.
I guess this may be a follow-up question. Wouldn't the 5 friends also delegate to the 2 builders eventually?
How much do you like your friends? It sounds like you don't like your friends very much. With something like this, we have tried an unmanaged market. It doesn't work. Trying a managed market where someone decides who's allowed to build blocks is a reasonable stopgap until someone proposes a mechanism that is better than the PBS auction. Decentralization is a means, not an end. You're not supposed to be decentralizing random computer stuff. You're supposed to be decentralizing power and control. We have constructed a market that is very free and decentralized, but leads to aggregation of power and control. If we instead construct something that is centralized, but leads to distribution of power and control, that is better.
Okay, well, I got the sign that Q&A is up. Thank you so much for joining us today. We have around 5 minutes until our next session at 5:40, which will be L2 EVM Common Core, a path beyond EVM equivalence. Hello, everybody. Welcome to the stage, Ansgar Dietrichs. We're going to talk about L2 EVM Common Core, a path beyond EVM equivalence. Before we begin, remember there's going to be a QR code on the screen. Scan it, ask questions, upvote, and heart. Without further ado,
hey everyone. Yeah, I'm here to talk about the L2 EVM Common Core. And is basically this initiative, that's a recent initiative that came out of the roll call process. And so if you've never heard of the roll call process, that's something we started earlier in the year, and it's basically a L2 coordination effort. We have a monthly call where many of the major L2s on Ethereum send representatives, and it's basically for now mostly used as like both coordination across them, also a bit of a trying to be a bit of a connective tissue to the L1. I'm personally spending most of my time in L1 core development. And then we also have what we call RIPs, roll-up improvement proposals, and the idea there is basically that they are similar to EIPs. EIPs, you might be familiar, that they are proposals to add new features to the EVM on L1, and so that the IPs are the equivalent for the L2 side of things. And yeah, the process was originally kind of started the roll call by Carl, who can't be here today, unfortunately, Yoav, and me, and then more recently, Nico also started joining us more actively. And yeah, I want to basically talk a little bit about EVM equivalence in general, and then kind of the specific kind of direction that we see the EVM equivalence go in the future. And I wanted to start a little bit with history. It's going to be a bit more of like an easy kind of beginner-friendly talk, at least in the beginning. I like pictures, so I have some pictures. In principle, the way I always think about scalability for blockchains is basically as this fundamental trade-off between the cost to run a full node and the throughput you get, right? And so Bitcoin, Ethereum, two early examples. Ethereum has more throughput than Bitcoin, but it's also a bit harder to run an Ethereum full node than it is to run a Bitcoin full node, right? And I call these kind of trustless chains because the important thing is everyone on Earth who wants to can verify the chain. At least that is the goal, and we are sticking at least pretty close to that. And then there is the kind of the approach of just going further up the diagonal and just picking Solana as an example here of chains that basically just say, okay, we want higher throughput, and how do we get there? Well, we basically go up and we accept that now it is harder to run a full node, but we get more throughput. And of course, the trade-off is that now you actually need to have a quite beefy machine to be able to still trustlessly participate. Otherwise, you have to trust the majority of nodes. Now, ideally, we want to go there, right? The ideal chains, like they have very low cost to run full node. Everyone can verify, but they have high throughput. So how do we do this? We basically, this is the key roll-up trick, right? We realize that actually what matters is the cost to verify the chain. And if there's a way to verify the chain cheaper than running a full node, that's sufficient. And that's basically how we get to roll-ups, because roll-ups are basically a way to compress verification of a chain. And so what you can do now is, once you get to that place, you can do either, you know, basically the thing you could immediately think of is just, hey, take the high performance chain and just run it as a roll up. And there are some projects now on Ethereum that do this, that are Solana VM based. It's a bit of a challenge though to adapt them for L2s. Then of course what you can do is as well, you can just take the EVM and you can really scale it to high throughput. People sometimes have this mistaken conception that like the EVM is fundamentally not able to go to similar throughput levels as the SVM. That's really not the case. The reason why Ethereum runs on lower throughput is specifically because we want this trade-off. We want to be verifiable by everyone on Earth in a trustless way, right? It's a choice. It's not a technical constraint. So once you go into the roll-up, you can actually push the EVM to its limits. But the variant of this that we've seen the most is actually what I call, I don't know, the multi-rollup cluster, which is just like many smaller, like lower throughput individual rollups that basically together form like a very high throughput system. So that's kind of like the background of how the ecosystem evolved, like as Ethereum went basically through its rollup-centric roadmap. And if you zoom into like now the chain itself and then eventually the EVM, I have some more pictures. I call basically this just like the execution chain. That's just a symbol that's representing chains where actual activity happens, right? Like chains that actually offer execution, where you can build apps on top. And the most basic version of a chain is just like a self-contained chain. It's like an L1 with just normal apps on top. But now you want to turn it into a rollup. How do you turn it into a rollup? Well, you need settlement and data availability. And those two things can be provided in a combined way by a settlement chains. So then, once you have a settlement chain, you can just take your chain there and just turn it into a rollup. And the nice thing there is that now you inherit the security of the settlement chain, but you can still now yourself run with much higher throughput, right? But because you have that security that you inherit from that low throughput but high security chain. That's kind of like how this best of both worlds solution works. And that's kind of how you get to this world, right, where you have a settlement chain and you have a bunch of rollups on top. Now, this was basically the original vision for what people back then called ETH2. You might remember before the merge, people used to call kind of like the beacon chain ETH2. And we moved away from that name, and that has a specific reason. Why? Because ETH2 was this vision that we would basically give this new chain some fancy new execution and settlement system, and we would take the old ETH1 chain and the old EVM on top, and we would retire it. Back in the day, there were a bunch of different thought experiments. You could turn it basically into some sort of roll-up on top of the new ETH2 chain. You could just have it parked somewhere on the side with some, either like proof of work forever with some bridges to the new system, or just even over time deprecated or something. But then at some point, basically, as we moved closer to the merge and to these ideas, people realized that, hey, actually, the ETH1 chain is kind of good enough for what we need for the settlement chain. And so that's why then instead the plan became, let's merge the existing system into this new ETH2 chain. And that's why we kind of stopped calling it ETH1 and ETH2 and instead just call it Ethereum again. And so that's why today what we have on Ethereum is this hybrid settlement and execution chain, right? So like down there, that's what Ethereum is supposed to be like. That's both the settlement thing, settlement and data availability, but we also still have execution. You can, have your UA on L1, you can use Uniswap on L1, all of that still works on L1. And it's all still powered by the original EVM that we used to have on Ethereum from the early days. Right. So that's basically like how the role of the EVM evolved, and how for a long time the EVM was basically supposed to have like an expiry date, and then it turns out it actually didn't. Now, how do L2s and their execution systems fit into this? Well, actually, when we first pivoted from sharding to rollups, the idea was, well, this is going to be amazing because now all the L2s can go on this wild exploration and see what type of new fancy execution system works best for them. But then it turns out we have seen a little bit of that, and I said that earlier. We now see experimentation with the SVM and MoveVM and like more fancy high throughput EVMs and whatnot. That happens a little bit, but the vast majority of L2s actually basically followed the network effects, and they were like, well, there's already a lot of dApp developers for the existing EVM today, so what we are going to do is we're going to just copy the EVM, right? We're going to copy the EVM, and we're specifically not going to make changes to it, because otherwise apps would not be compatible. It doesn't mean that the L2s were not innovative. I would say quite the opposite. I think we've seen like 3-4 years of pretty rapid innovation in this space, but that was very much focused on the specific new challenges for L2s. So that was focused on like new functionality and like fault proofs, ZK proofs. Of course, in the ZK space, the innovation has been amazing to see. And then when it touched the EVM, it was more like extension. So I'm not sure how many of you are familiar with Arbitrum Stylus. That's an example of an extension to the EVM that left the core of the EVM unchanged and just added something on top. And then one more wrinkle to this, the consequence of the EVM equivalence was also that most L2s ended up just going with the dominant L1 EVM client, which at the time was Geth. Of course, Geth is still the most popular one. By now, there are also others that are a bit more on equal footing, but back in the day, really, Geth was the only main one, and so it, for that reason, is still the very dominant client in the L2 space. So that brings us to the present, and this also brings us to the point where like the pictures part of the presentation ended, but because I got so much feedback in the past that my presentations don't have enough pictures, I decided to just add one extra picture to every slide from now on, so you'll get a few bonus pictures, starting with this cat. But let's focus mostly on the content. So today, where are we at? We have the EVM on L1, and it basically, if you look at the kind of new features that we've shipped on the L1, we have roughly one hard fork a year. You will see that we don't really ship new features to the EVM that often, right? Like it's a pretty low frequency. We've had a few more what I would call ambitious features in the past. And by the way, this is a good point to briefly mention. I say EVM a whole lot throughout this talk. What I mean is technically not just the EVM, like the core EVM itself, but like the execution system as a whole, which is a little bit more expansive. Some people are always like, oh, but state expiry is not technically part of the EVM. Yeah, so basically when I say EVM, think execution in general. But we've had basically a few of these more ambitious features that we worked on and actually basically got all the way down to specs and the ability to, in principle, ship them, and then rejected them. So that was two of them that I worked on in the past were state expiry to manage the state size on Ethereum and native account abstraction. And both of those were ready like 3-4 years ago, and we just decided, hey, it's just not a priority for L1. And then even when we ship new features to the L1, which we still do, admittedly, and like some of them are actually quite exciting, we still very much focus on what the L1 needs, right? And so that's specifically, for example, ERP 7702, which I'm quite excited about as one of the co-authors, which is giving some smart account functionality to existing user accounts. That is EOF, which is upcoming, which also I think is actually a little bit underhyped. I mean, I guess you have probably heard the term, but I think it's going to be quite amazing. And then a little bit further down the road, something like Verkle trees. It's not 100% decided if it's quite going to be Verkle trees or some variant of it, but basically that is in the pipeline, but it will take several years to arrive. And it's very much something that primarily is interesting and nice for the L1. So where does that leave the L2? Well, it turns out that most of the L2s that started out as equivalent to L1 basically now are stuck in that position, right? The point is that you don't want to be the only chain that starts deviating, starts implementing features that no one else has, because then none of the wallets, none of the tooling, none of the dev tools are compatible with you, right? And so what that means is like now these L2s in a way are stuck with the EVM of L1 and are stuck with the kind of the slow speed of these new features that are being shipped. And in particular, it's not just clearly the L1 is very conservative, ships features in general, not quite as fast as L2s, but it's also a fundamental difference in constraints and priorities. So it's about throughput ambitions, the difference in full node requirements, that comes back hopefully to the graph, right? If you remember how basically the rollups give us this best of both worlds, you can run these very high, very demanding, very high throughput chains and still inherit the security of the L1. Well, but that also means that you are building a system for very different requirements. Block building works very different on L1 versus L2. And then, of course, for the ZK rollups, ZK basically changes everything in terms of how expensive different operations are and how the VM should ideally work. So basically, all of this means that like the EVM is just not an ideal fit for what the L2s need. Also, Geth is still the main client on the L2 side, but Geth is very much focused on the L1. Like the team very much has made it clear over the last few years that while they are, they're very happy that they get so much adoption on the L2, that they have very limited bandwidth to basically try to provide L2 specific features. But that's the silver lining here. We have seen several L2s, several other clients gain more adoption in the L2 space that are more willing and more focused on that use case natively. So where do we go from here? How can we basically make sure that we give L2s the best way to really make the most of this kind of this best of both worlds trade-off space there, where they are in this unicorn range of basically high throughput with low trust requirements? Like how can they have an optimal system designed around this? Well, two pillars basically, that we have been focusing on. First one is just make sure that all L2s have a client that actually is willing to focus and support the L2 use case more natively. And so that specifically tried to identify it and try to eliminate this bottleneck of the L1 focus. And out of that came the collaboration with Nethermind, which is what we call the rollup Geth team, or what they call the rollup Geth team, which is a fork of Geth. It starts out identical, but over time we'll add more and more L2 native and L2 specific features, and we'll basically join the set of L2 focused clients, right? Like Nethermind also, they have their own clients, so Nethermind now has the Nethermind client and the rollup Geth client, both of them happy to support L2s. Then there's also Reth, there's Besu, there's Aragon. So we have now is basically an entire team of clients that are willing to basically support L2s. And basically, ideally, that way we can basically leverage the existing kind of skill set that we already had in the Nethermind team and really kind of help L2s there. So that's pillar one. Pillar one is make sure that all L2s have a client that is willing to support rollup specific features. Now, as I was saying, that is basically joining the kind of the broader set of clients, and now we can basically start to ship more IPs, more ambitious IPs, because the clients can support them. The problem is that on its own, it's only one of two pillars, because that on its own does not get rid of this kind of fundamental lock-in of the EVM equivalence, the equivalence to the L1 constraints. And so that's where the second idea comes in. That admittedly is a bit more opinionated. This one might or might not play out. That's something that we've proposed to rollups just over the last month or so. And there's a lot of interest in this idea, but it's not clear that will actually play out. So that's basically the proposal that I wanted to talk about here today. The idea is, we call it the L2 EVM Common Core. And so the idea here is to just say, hey, basically, let's just start, like what you really want as L2s is you want to be equivalent to each other, right? Because that is where the network effect is. And you don't really care so much that what you are equivalent to is exactly the L1. So what we want to do is we want to take the L1 EVM and over time extend it more and more and have that be the shared target that everyone focuses on, everyone supports. And that way, tooling, Solidity, all wallets, all these kind of, the full stack can now start supporting this L2 common core as the base feature set, and we can really start shipping more ambitious features over there. And just to illustrate, I count that as an image. That's basically like how you can think of the feature set of a rollup, right? So you have the L1 EVM as the core. Everyone supports all the features of the L1 EVM. In the future, there would be this extra ring, which is the L2 EVM common core that also everyone on the rollup side would support. Then, of course, you have stack-specific features. So if you are on one of the OP stack chains, then that would be OP stack features. If you're on Polygon, that's the Polygon features, etc. And then every chain also has some features that make it unique, right? And so that's kind of the outermost ring. And so what kind of features are we talking here? Like, what could we bring? Well, basically, the idea is really just let's open the design space again, right? Now that we have a platform to basically ship more ambitious features, let's just look into what we have there. So in the short term, that could just be things like basic repricing that to make it, for example, more ZK native. A 2D transaction type, that's something that I think would be really nice. Right now, the way L2s charge users for the settlement cost differs from L2 to L2, which doesn't make for great UX. I've sent a transaction on Optimism once, and my wallet said, at most it's going to be 1 cent. I sent the transaction, and it's 10 cents. And I mean, yeah, it's still only 10 cents, but imagine if that would be factor 100, you know, like all of a sudden it would be not so funny that basically that doesn't work. So having a native transaction type for L2s would actually be quite fun. Delayed state root computation is maybe a bit nerdy. It's a feature that people have been talking about a little bit that could basically make block processing more streamlined. And then in the long term, that's what I'm really excited about, these kind of features. So that would be things like native account abstraction. I'm not sure how many of you all have a smart account, have heard of ERC 4337 in the past. There are proposals to basically have that be natively embedded into the protocol. Eventually, I think this will also come to L1, but it will take years and years. We can ship it in the meantime on L2. Transaction parallelization, state expiry, statelessness, state rent, like basically figure out a way for how we can basically manage state and state growth more aggressively. And then something I personally am very excited about because I've been working on that in the past is multidimensional pricing. I think we're basically out of time. Let me see. I think I only have like 2 quick slides, so let me just rush through them. Next steps, again, the Common Core is a bit more unclear yet. Like, that's a proposal. We will have to see how much interest is there really and how much willingness to commit to this across the L2s. Figure out a governance, because given that that would be a shared set of features that everyone would commit to supporting, that requires governance among the participants. And then have a research process across the teams. And that also would mean that for roll call, in the season 2 of roll call, we would basically focus also on facilitating that side of things more. So that's all. I hope that gave you some intuition around why that is at least an interesting direction and why there is some use in trying to eliminate this bottleneck of the equivalence to the L1, which really has very different constraints from the L2s. Thank you.
Okay, cool. Let's scurry towards the middle because we have some questions that need to be answered. So starting from the top, can you quickly explain why EOF is underrated?
Yeah, that might be a question from an EOF hater. I can already feel that, which is fine. You know, I think EOF is one of those features where not everyone loves it. I personally am the most excited about it specifically in the L2 context, actually, and I guess that goes a little bit counter to the slide that said it's a L1 specific feature, but because the nice thing is it gives you version bytecode. So far on Ethereum, we only have one type of contract code, so if you deploy something, it will always behave the same way no matter what. With EOF, contracts can now have a specific version, which means you can basically have different behavior depending on a version. And so that means you can have like backwards incompatible breaking changes, new types of new features. We have Dano in the audience. Dano is like the expert on EOF. So if anyone has like actual good faith questions about EOF, go talk to him afterwards. He's like the Bible on EOF. But I'm a fan.
Okay, what is the best alt VM from your view?
Ooh, spicy. I mean, I don't really have an opinion. I think I'm very, very excited that we now have this Cambrian explosion of L2s. I know that some people on Twitter are like, oh, you know, yet another L2, yet another L2. I actually think there will be, like, we'll look back at this time and we'll be like, oh, we only had 100 L2s. You know, now we have 10,000. So I think we'll get a lot more L2s before we get fewer. And I think that's a good thing. I have no idea. Some of them will work really well. Most won't. And then we'll see which winners emerge. I mean, of course, I do think, of course, one interesting direction is SVM-based ones, just because, you know, Solana is a very interesting kind of alternative network. I think as an L1, it doesn't make so much sense. I want to actually be able to verify that someone is not stealing my money. But as an L2 software stack, I think it's an interesting direction to explore.
Do L2s also, oh, it's changing, upvotes are happening. But I'll start, I guess, 2 votes win. Will L2s remain able to execute contracts written for L1, or will compatibility be lost?
Yeah, that's great, because that question shows me that the person actually was thinking during the presentation about like the edge case, like the implications of this idea. Like, that's actually exactly like a really interesting question. Like, will we be able, like, how close will L1 and L2 Common Core, if it starts to diverge, how close will they remain? I would predict that for the next foreseeable while, probably you can write the same code for L1 and L2. I think at some point we might reach the point where L2 might want to ship features that unlock new capabilities like parallelization, like asynchronous communication within the same block or something that might just make it impossible to keep the compatibility. But we will see if it's worth to break. My prediction would be long term L1 and L2 will probably diverge to the point where you have to write L1 specific code if you want to deploy on L1.
Interesting. Do L2s also, oh my God, things keep changing. Will Nethermind make rollup Nethermind?
Well, the fun thing is that rollup Nethermind is just Nethermind. Like, the Nethermind client is very willing to actually focus on shipping features that are useful for L2 specifically. So the only client that needed a rollup upgrade was Geth specifically.
Okay, we'll finally get to this one. Do L2s also aim to have client diversity?
Yes, great question. And that is also, even though, say, for example, more and more rollups are starting to adopt Geth and Nethermind and these other clients, and you could just say, well, why even bother with rollup Geth? Because you could just wait until they all switch over to one of those clients that is more natively aimed at the challenges and the kind of the features that the L2s want. But the answer is, actually, it's very, very valuable, even if they start supporting these other clients, to keep Geth compatibility so that you can go to this multi-client world. Because, say, for example, I mean, already for fault proof, it's very nice. But then also with ZK proofs, it's very nice if you have multiple kind of independent paths that you can prove something from. So then you can have like a 2 out of 3 ZK kind of disagreement rule or something. All of that is unlocked by multi-client. And I think L2s are on a path towards multi-client.
Okay, perfect. That wraps it up. Thank you so much. Next, we will have state minimized layer 2s and why Ethereum's better than EVM at 6:10 p.m. So catch you later. Okay, hello. We're ready for the next session. Please welcome to the stage Nick Dodson for State Minimized Layer 2s and why Ethereum is greater than EVM. I believe this is a lightning talk, so be ready with your questions immediately. The QR code is going to be there, and we're gonna light it up, I guess. Cool.
All right. Okay. So I'm going to be very, very fast. I have like more than 30 slides, and there's 5 minutes. So I'm gonna have to make this work. It's fine though. A lot of this I can kind of skip. So today we're going to be doing state minimization and why Ethereum is greater than the EVM. So, okay. So components of a blockchain, just to review quickly. You have this area of a blockchain node that would be, you could think of as state. State being, these things that you need to both verify things and propose new blocks into a blockchain. Then you have things like execution, largely what we do with the CPU and RAM, sometimes a GPU if you're going to do GPU acceleration. Then you have data, and in this case I'm just calling it data, which is just sort of the data you communicate over the internet to basically get everyone else in sync and kind of progress things forward and ensure that it's actually a system we can all use. So in many senses, on the data side, we have some solutions. On the execution side, we also have a lot of solutions. On the state side, though, you don't really hear about this problem very much, and you don't hear about it because a lot of people don't really have any good solutions. So that's why this talk is kind of interesting and also fun. So on the execution side, we've got all kinds of things coming out. Parallel transaction execution is becoming more normalized. You have the SVM. You have as well things like stylus, dropping into WASM, stuff like that as well. My project FuelVM, we have our own virtual machine that helps with this. And there's all kinds of different ways we can alleviate execution. Data has also been somewhat solved as well. So we post data now as rollups. We can post them over Ethereum, right, on EIP 4844. There's all kinds of sharding designs. There's all kinds of different kinds of DA layers that are coming up. So there's lots of solutions in that camp. But with state, there isn't really a lot of solutions. And so when we're talking about state, you kind of have a bunch of information that you really need to store in order if you want to progress things forward, right? So with Bitcoin, you have like the active UTXO set, the unspent UTXOs. With Ethereum, you have things like the account balances, smart contract code, smart contract state, token balances, etc. So there's a lot of stuff there. And Ethereum's state system is it's quite interesting, but it's very, very what you could say is really difficult to deal with, and it's very difficult to optimize around. So if you'll see, there's a lot of different layers to how we're actually both taking this sort of key value store we have with Ethereum that we call like S-store, et cetera, when you're in contracts, and how that filters all the way back up to single state roots, succinct state roots within block headers. And it's quite enormous, the amount of state that's accrued here. So when we talk about like scalability and we talk about state, a lot of people just like blame the clients, they blame Geth, they blame these kinds of things, like why don't we just up the gas and like screw everything, let's do it. And the thing is, like Peter's already addressed this quite well, which is effectively that you can't just do this, and it's not slow because of Geth. Quite frankly, it's not slow because of our clients. It's slow because we're all actually, or some people, are very, very concerned about the state growth itself, right? And the requirements that puts onto things. And one way you could even look at state growth here is just like, I believe this is just the accounts on Ethereum, but you can just see that like you have a ballooning of information, and all of these accounts have to be Merkleized. So it's really, really intense in terms of the amount of storage that we need to hold within Ethereum. So how can we address state growth? Basically, there's a bunch of different solutions for this. We can go on and on about it, but some ones that have been proposed before, right? State rent. There's also like statelessness, which is like sexy to say, but there isn't really a lot of great things underneath the hood for it. Unmerkleizing the state, so you just YOLO it like Solana does. As well, app level compression, so doing things at the application level. You can also just like let it grow, and maybe we just keep adding hard drives. Vertical trees. You also have some nice things here, right, where they kind of compress a certain amount of state using other techniques, but still pretty messy. And then we have another option, which I'll talk about at the end, which is bandwidth. So basically with state rent, we've all kind of heard this one before. Use state, you rent it out, etc. Statelessness, just trying to do more things, just kind of away from Ethereum state system. Unmerkleizing the state, it's not really a great approach. As well, application level techniques, you can do things more in call data, more things at the application level, but it's still not a great system in general. Here's Tolly basically saying, I don't know, here's a bunch of options, but I'm not really sure. Here's Verkle trees, and again, Verkle trees not really the best solution because there's still a ton of state that gets accrued, right? So alt VMs, again, Tolly's system, not that great. Fuel state philosophy, we'll go into it like 2 minutes or like 1 minute, and then we'll go to questions. Thanks. So fuel state philosophy is very different. We actually don't have any global state trees. We also use a system of native assets. We use UTXOs. We have as well different kinds of models to use state, but use it in the right way. We try to move a lot of the state that's typically within Merkle trees into an area which you would consider bandwidth. And in bandwidth, we actually have a lot more room to play with because everything, once you've moved it over bandwidth and kind of done the proving, then effectively you can just trim it. So there's a lot of really nice things you can do. So applications can be designed in a new technique that we have, which is called native state rehydration. And this really means that across our system, we have different techniques to basically create applications and different techniques to effectively remove state from the system and keep it very lean. These are basically in our system scripts, predicates, native assets, and a transaction model. I only have 3 seconds left, so I'm just going to skip through this. Again, UTXO model is very, very powerful in this setting, and it provides a lot of different options. And this is why in my super crazy lightning talk, I hope you guys enjoyed that. Ethereum, Fuel is on Ethereum, it's a layer 2, and Ethereum is much greater than the EVM with all these state problems. So thank you.
Okay, cool. We have 40 seconds for one question. What about state expiry? Would also keep state in check?
Yeah, so kind of, but again, you have this sort of intense problem of a massive run-up of state. And the problem with state expiry is that it's not so much that you can or can't do it, it's that basically once it expires, you would need a good system to then refill that state. And it helps, but I would say that there are better techniques where, again, you can use bandwidth. Over bandwidth, you kind of store things, and then once you've kind of consumed that or other people consumed it, then they can bring it back only whenever they need it. You could say that's kind of like expiry, but I think expiry is too simple. You need a way to both kind of use state and then rehydrate state and then basically take it away. So in Fuel, we have really nice systems for this, and again, it's a lot more sustainable by design. So thanks.
Okay, cool. Thank you so much for your time.
Thanks, everyone.
Yeah. Thanks that way. And then at 6:20, we will have our next and final speaker, gas metering, comparing app chain rollups versus general purpose rollups. Okay, cool. It's the last talk. Everybody gets so excited for this guy. Oh! Okay. We're welcoming to the stage Felipe Argento. We're going over gas metering, comparing app chain rollups versus general purpose rollups.
So hello everyone, I'm Felipe, and it's an immense pleasure to be here, so thanks for everyone involved. At Cartesi, we've been talking about app chains for a very long time, and something that's quite surprising is that we don't hear a lot about gas metering. So I only have 5 minutes, but this is my attempt to kickstart the conversation and maybe give you some intuitions about it. So there are some reasons behind the gas metering system. The one that we're interested in this presentation is gas metering as a defense against resource exhaustion attacks. And what do I mean by that? So imagine that Ethereum is being attacked. There's a malicious transaction that is trying to halt the network, or either halt it or slow it down. What would you do? Well, you cannot know that the transaction is malicious beforehand because of the halting problem. Normal servers deal with this with the wall clock. So basically, you start executing a transaction. If it's taking a long time, you just bin it or you schedule it for later. Unluckily, the wall clock, unlike our legal system, is not deterministic. So we cannot use it because nodes would get confused about the validity of transactions. So that's a bummer. That's why we have the gas metering system, which is basically associating a gas cost to each OP code or each instruction that a EVM transaction executes. And this gas cost aims to correctly infer the cost of running that OP code on a real computer. Then we give each transaction a gas allowance and each block an upper gas limit. And we expect the node, the reference node, to be able to execute a block of gas limit X on time Y. But what can go wrong? Because it sounds very simple. The problem is that these estimations are quite hard to do, especially when the architecture that you're emulating differs a lot from the architecture that you're emulating it on, which is the case with the EVM. Also, it doesn't help that mispriced OP codes are quite dangerous. And the average case for executing an OP code, it's quite different than the worst case for executing it. Also, a quick reminder, you have to use the worst case because otherwise there's a huge security problem on your chain. What went wrong? So in 2016, I was not around at the time, but during Shanghai Devcon, there was a massive DDoS attack on Ethereum. Part of the attack was malicious actors using the self-destruct OP code to trigger empty accounts, and that OP code was mispriced. What made it worse was that attackers were able to deploy custom code to specifically trigger the scenario in which the OP code was mispriced. And then we had to ask the miners to reduce the gas limit. That hurts scalability, and we had to hard fork and increase the gas cost of some OP codes. So let's talk a little bit about app chains. So the difference between app chains and shared rollups regarding the threat model is quite simple. On shared rollups, we have two possibilities of malicious agents. You have users that can send malicious data, and you have applications that can send malicious code. For application-specific rollups, the application and the chain are the same thing. So the only possibility of attack comes from the malicious users, which can only send malicious code. And this is a very important distinction. Just summarizing it real quick, on shared chains, you have adversarial metering. So the granularity is per OP code. So you're charging money per OP code, which is a very small granularity that has a big overhead, as you can see on the slides. The threat is data and code. So that means that it's quite hard to estimate the OP code cost, and also that the worst case is much worse than the average case. So you can see there, the worst case and the average case, there's a big difference there, and your block size has to be small. Also, the reference computer is quite idle even when the blocks are full, in average, because you have to go with the worst case when your average case is much better. On app chains, you can actually charge gas per interactions. So attack a goblin, gather some loot. And the interactions, they actually contain millions of instructions. So the overhead is much smaller, because you don't have to calculate the gas cost every single OP code. The threat model is much easier to deal with, because you can only have malicious data and not malicious code. So the worst case is much closer to the average case, which in turn means that we have a much better block size and therefore even more scalability. So that's it. Thank you so much. And yeah.
Okay, cool. There was only one question, which was, how did you become so damn handsome?
Oh.
I don't know if you're supposed to answer that.
I think I know who sent that.
Oh, okay, cool. What about using, oh, sorry, I got distracted. What about using average NR of computer cycles? Validators could post them periodically.
Yeah, so the cool thing about app chains is that you can actually customize the best gas metering system for your specific chain. So you can even do stuff like cool stuff like subsidized transactions that help the ecosystem. You can charge differently if there's a lot of transactions coming of that type, and etc. So that's a possibility for app chains, yeah.
Okay, cool. I think that's everything.
Thank you so much.
Thank you. Oh, closing up? Do I close? Oh. Okay, cool. Yeah, so that's everything, guys. Have a great rest of the night. Stay safe. Take the bikes. They're faster than the taxis.